Modern DevOps Production Incidents, 100 Real-World Failures.
DevOps interviews have moved far beyond questions like what is CI and CD or what is Kubernetes. Modern interviewers want to know how you think when a release fails, when automation behaves unexpectedly, when infrastructure changes partially succeed, and when a production system is caught in a state you did not expect. In this series, we are going through 100 modern DevOps production incidents designed around those real operational failure patterns. This is not a collection of textbook definitions or generic troubleshooting questions. Each incident is built around a production failure, the evidence you would see, how you would investigate it, the actual root cause, the immediate recovery, prevention, and the follow-up questions an interviewer can use to test how deeply you understand the situation.
How we divided these 100 production incidents.
To keep the series practical without losing depth, these 100 incidents are divided into two parts of 50 incidents each, following the natural life cycle of modern DevOps. Part 1. The delivery engine, how code gets built, versioned, provisioned, packaged, and deployed. Part 2. The production reality, what happens after changes reach the live cloud environment and interact with networking, security, identity, databases, observability, cost, reliability, and AI-assisted automation. Together, the two parts follow the complete journey from source code all the way to production behavior. Let's dive into Part 1.
Part 1. The Delivery Engine, Incidents 1 to 50.
Part 1 focuses on the systems that actually move a change toward production. Category 1, CI and CD, and Pipeline Engineering Incidents 1 to 15. Build pipelines, artifacts, runners, caching, identity federation, retries, shared templates, release capacity, and emergency delivery failures. Category 2, GitOps and Release Management Incidents 16 to 25. GitOps reconciliation, release branches, mutable references, configuration sources, shared changes, and production release governance. Category 3, IaC and Infrastructure Automation Incidents 26 to 37. Terraform state, destructive plans, provider and module changes, drift, partial applies, locking, dependency races, and infrastructure rollback limitations. Category 4, containers, Kubernetes and deployment mechanics incidents 38 to 50. Image identity, registry replication, image pull behavior, architecture compatibility, admission, configuration, scheduling, storage, node capacity, API load, and GitOps delivery scale. Part 1 follows the delivery engine from code, commit to a running production workload. Let's dive into Category 1 incidents.
Category 1, CI and CD, and Pipeline Engineering.
We start at the first point where a production change can go wrong, the delivery pipeline itself. A green pipeline does not always mean the correct code was built, the correct artifact was promoted, or the release can actually reach production. Pipelines can collide, runners can disappear, caches can produce the wrong binary, identity federation can fail only at the production boundary, retries can duplicate infrastructure, shared templates can break hundreds of repositories, and emergency changes can become blocked by unrelated dependencies. These incidents establish the foundation for the entire series. In modern DevOps, the delivery system is itself production infrastructure and must be engineered with the same discipline as the applications it delivers.
Category 1 Incidents, CI and CD and Pipeline Engineering, 1 to 15.
Here are the first 15 modern DevOps production incidents we will cover in this category. Incident 1, green pipeline, wrong commit deployed. Incident 2, parallel pipelines overwrite the same artifact. Incident 3, CI runner capacity exhaustion. Incident 4, spot-based CI runners suddenly disappear. Incident 5, build cache produces an incorrect binary. Incident 6, CI pipeline works everywhere except production. Incident 7, OIDC token expires during long Terraform deployment. Incident 8, pipeline retry creates duplicate infrastructure. Incident 9, partial deployment leaves production in a mixed state. Incident 10, shared pipeline template breaks hundreds of repositories. Incident 11, CI runner image upgrade breaks previously working builds. Incident 12, pipeline matrix explosion delays critical release. Incident 13, third-party build dependency disappears. Incident 14, CI or package registry rate limit blocks release. Incident 15, emergency hotfix blocked by an unrelated pipeline dependency. Let's start with production incident 1. Green pipeline, wrong commit deployed.
Production Incident 1. A production deployment completed successfully, but users report that a critical bug supposedly fixed in the latest release is still present. CI is green, and the deployment shows healthy. Production is running the wrong code. What's your response?
Answer: my first priority is to determine whether the problem is in the build, the artifact, or the deployment path. Since the pipeline and deployment are both green, I would trace the exact release artifact from Git to production and eliminate each possibility using evidence. I will follow a structured response plan like Phase 1, Symptoms. 1. CI and CD pipeline shows success. 2. Deployment and pods show healthy. 3. Production behavior still matches the older version. What these symptoms are telling us: the deployment mechanism appears operational. Suspicion shifts toward the artifact being deployed rather than deployment failure. Phase 2. Investigation. 1. Verify the Git SHA associated with the release and confirm that the CI build actually used that commit. 2. Compare the image digest produced by the CI build with the digest running on every production replica. 3. Trace the image tag through the container registry history and deployment configuration to determine whether another build changed what the tag referenced. What this investigation is revealing or leading to: the intended Git commit was successfully built, but production is running a different image digest. The evidence therefore points away from the source code, or CI build, and toward an artifact promotion or image tagging problem. Phase 3. Root cause. 1. The production deployment referenced a mutable image tag that was overwritten by another build after the intended artifact was created, causing the same tag to resolve to an older image in production. Why this is the exact root cause, and why not others. The CI artifact matches the intended Git commit, while the production digest matches the overwritten tag. That directly explains the version mismatch and rules out a failed build, failed deployment, or unhealthy production pod as the primary cause. Phase 4. Immediate fix. 1. Identify the exact image digest produced by the CI build for the intended Git commit. 2. Deploy that immutable digest directly to production instead of relying on the mutable tag. 3. Verify the digest running on every production replica and confirm the reported application behavior has been corrected. Expected outcome: by doing the above steps, production is restored to the exact artifact that was tested and approved, eliminating the version mismatch and returning application behavior to the expected release. Phase 5. Long-term prevention. 1. Deploy production workloads using immutable image digests rather than mutable release tags. 2. Configure the container registry to prevent overriding of production release tags. 3. Record the Git SHA, CI build ID, image digest, and deployment ID together as release metadata. Expected outcome: by doing the above steps, every production deployment becomes traceable from the running container back to one exact CI build and Git commit, making artifact substitution or ambiguity immediately detectable. Pro tip: in production, treat the image digest as the actual release identity. Tags are human-friendly references and can change, while the digest identifies the exact immutable artifact. If your deployment metadata records the Git SHA, build ID, and image digest together, you can trace any running production container back to the exact source and build that created it.
Follow-up 1. If the git commit SHA is used as the Docker tag, is that enough to guarantee the correct artifact reaches production?
Answer: it is significantly safer than using a generic mutable tag, such as latest, because the tag identifies a specific source revision. However, the tag can still be overwritten unless the registry enforces immutability. For production, I would promote the already tested image by digest and enforce immutable release tags, so the artifact cannot silently change between environments.
Follow-up 2. How would you automatically detect an artifact mismatch immediately after deployment?
Answer: during the build, Record the expected image digest as part of the release metadata. After deployment, query the running production replicas and compare their actual digests against that expected value. If any replica differs, the deployment verification should fail, stop further rollout, and trigger the defined remediation or rollback process.
Follow up 3 curveball. You discover that 30% of production pods are running the old digest and 70% are running the new digest, while the application appears healthy. What do you do?
Answer: I would first stop further rollout activity and determine whether the two versions are actually compatible and safe to serve together. Then I would identify why the deployment produced a mixed artifact state, converge all replicas onto the intended immutable digest, and verify application behavior after convergence. Finally, I would investigate the rollout and registry history to determine whether tag mutation, caching, or deployment configuration caused the inconsistency.
Production Incident 2. 2 release pipelines run concurrently and publish artifacts under the same production tag. One release is approved, but production ends up running the other branch's build. How would you isolate the releases and determine which artifact actually belongs in production?
Answer: my first priority is to reconstruct both pipeline executions and determine whether they were allowed to share the same artifact identity. I would correlate their Git commits, build IDs, publication times, image digests, and deployment records to establish exactly where the concurrent releases interfered with each other. I will follow a structured response plan like Phase 1. Symptoms: 1. Both release pipelines show success. 2. The production deployment completed, but the deployed application contains changes from the other branch. 3. Both pipelines published an artifact using the same production tag. What these symptoms are telling us: both pipelines appear individually healthy, but they are competing for the same artifact identity. The problem is more likely a release isolation or concurrency issue than a failed build or deployment. Phase 2. Investigation. 1. Compare the Git SHA, CI build ID, image digest, and publication timestamp from both concurrent pipelines. 2. Inspect the container registry history to determine which pipeline pushed the shared tag last and which digest the tag referenced when production deployment began. 3. Trace the approved release from its pipeline execution through artifact publication and deployment to determine where the other branch's artifact entered the release path. What this investigation is revealing or leading to: both pipelines produced valid but different artifacts, yet the shared tag provided no unique release identity. The later publication changed what that tag referenced, allowing the concurrent pipelines to interfere with each other's release state. Phase 3. Root cause. 1. The release pipelines were not isolated from each other and were allowed to publish the same production artifact tag concurrently, creating a race condition in which one pipeline could replace the artifact reference expected by the other. Why this is the exact root cause and why not others? The two builds have different Git SHAs and image digests, while the shared tag changed during their overlapping execution window. That timing correlation directly explains why a valid release ended up consuming another branch's artifact. Phase 4. Immediate fix. 1. Stop further promotion from the competing pipelines and identify the digest belonging to the approved release. 2. Deploy the approved artifact using its immutable digest rather than the shared production tag. 3. Verify the running digest on every production replica and confirm that the unintended branches changes are no longer present. Expected outcome by doing the above steps: production is restored to the exact build approved for release, and the competing pipeline can no longer influence the artifact being deployed during recovery. Phase 5. Long-term prevention. 1. Give every build a unique immutable artifact identity and promote the exact digest associated with the approved build. 2. Prevent concurrent pipelines from publishing or overriding the same production release tag. 3. Introduce pipeline concurrency controls or release locks where multiple pipelines can target the same production environment. Expected outcome by doing the above steps: parallel pipelines can build independently without interfering with each other's artifacts, while production promotion remains tied to one explicitly approved release. Pro tip: do not solve a pipeline race condition only by adding a deployment lock. A deployment lock can prevent two releases from entering production simultaneously, but it does not stop two pipelines from overriding the same artifact before deployment. Isolate the artifact identity first, then control concurrency at the promotion stage where shared production state is actually being changed.
Follow-up 1. If every pipeline uses a unique image tag, do you still need to control pipeline concurrency?
Answer: unique artifact identities eliminate the risk of one pipeline overriding another pipeline's image, but they do not automatically make concurrent deployment safe. Two releases can still modify shared infrastructure, database schemas, configuration, or production state in incompatible ways. I would therefore separate artifact isolation from deployment concurrency and control each risk independently.
Follow-up 2. How would you design the pipeline so an approved release cannot accidentally consume a later build from another branch?
Answer: the build stage should create the artifact once and record its immutable image digest as release metadata. The approval and deployment stages should carry that exact digest forward, rather than resolving the image from a shared tag later. Registry, immutability, and deployment validation should then verify that the artifact being deployed is exactly the one associated with the approved pipeline execution.
Follow-up 3. Curveball. Both pipelines are already running, and one is halfway through production deployment when you discover they are competing for the same artifact tag. What do you do?
Answer: I would immediately stop further promotion from both pipelines, so the production state does not become more inconsistent. Then I would identify which release was approved, determine the digest currently running on each replica, and establish whether either version introduces risk. Once the intended artifact is confirmed, I would converge production on that immutable digest, and only then investigate the pipeline race and implement the required concurrency controls.
Production Incident 3. A major release surge triggers hundreds of CI jobs at once. All available runners become occupied, and a critical production deployment remains queued while the release window is closing. How would you restore deployment capacity without disrupting the running builds?
Answer: my first priority is to determine whether the deployment is actually failing or simply waiting for execution capacity. I would correlate the release surge with runner utilization, queue depth, job duration, and runner availability to identify whether capacity exhaustion is the real bottleneck and restore only the capacity needed for critical releases. I will follow a structured response plan like Phase 1. Symptoms: 1. A large number of CI jobs are queued without starting. 2. All available runners are busy processing release and validation workloads. 3. Critical production deployment jobs are waiting behind lower priority builds. What these symptoms are telling us: the pipelines themselves are not necessarily failing. The delivery system has reached its available runner capacity, making execution capacity rather than application or deployment health the immediate bottleneck. Phase 2. Investigation. 1. Check runner utilization, queue depth, active jobs, runner labels, and the time each queued job has been waiting. 2. Identify whether a release surge, unusually long-running jobs, blocked runners, or excessive parallelism consumed the available runner pool. 3. Compare the critical deployment's runner requirements with the runners currently available to determine whether it is waiting for a specific runner type or general capacity. What this investigation is revealing or leading to: runner capacity is fully consumed by concurrent workloads, and the critical deployment cannot start because the available runner pool cannot satisfy its scheduling requirements. The evidence points to a CI capacity and workload prioritization problem, rather than a deployment failure. Phase 3. Root cause. 1. A sudden release surge created more concurrent CI workload than the configured runner pool could handle, while critical deployment jobs had no dedicated capacity or effective priority isolation. Why this is the exact root cause, and why not others. The queued jobs begin once runner capacity becomes available, and the runner metrics show the pool saturated during the release surge. This rules out a broken pipeline definition or failed deployment target as the primary cause. Phase 4. Immediate fix. 1. Increase available runner capacity or provision an additional runner pool for the critical deployment workload. 2. Prioritize the production release and prevent non-critical jobs from consuming the newly available capacity. 3. Confirm the critical pipeline starts, completes successfully, and reaches the intended deployment stage. Expected outcome by doing the above steps. The critical production deployment gets execution capacity and proceeds without unnecessarily terminating healthy builds that are already running. Phase 5. Long-term prevention. 1. Configure runner autoscaling based on queue depth, workload demand, and job wait time. 2. Separate critical production deployment workloads from general-purpose CI workloads using dedicated runner pools or appropriate scheduling controls. 3. Establish capacity limits and concurrency policies so release surges cannot consume all execution capacity required for production changes. Expected outcome by doing the above steps. CI capacity scales with demand, while critical production delivery retains predictable execution capacity during large release surges. Pro tip: do not size CI runners only from average daily workload. The real capacity risk appears during release bursts, incident fixes, and large parallel test suites. Track queue wait time and runner saturation during peak periods, and reserve or prioritize capacity for production delivery so a sudden increase in developer activity cannot block an urgent release.
Follow-up 1. Would you simply terminate some running CI jobs to free runners for the production deployment?
Answer: not immediately. First, I would identify which jobs are safe to interrupt and whether they can resume without losing significant work. I would prefer adding capacity or prioritizing the critical workload, because indiscriminately terminating active builds can create another surge when those jobs restart and can waste already completed CI work.
Follow-up 2. How would you decide whether to add more permanent runners or use auto-scaling?
Answer: I would examine queue depth, runner utilization, peak versus average demand, job duration, and how frequently release surges occur. If demand is consistently high, additional baseline capacity may be justified. If saturation occurs mainly during short-lived bursts, auto-scaling is usually more efficient because capacity expands when the queue grows and contracts when the workload returns to normal.
Follow-up 3. Curveball. Auto-scaling is enabled, but new runners take 10 minutes to become available, and the production release must begin immediately. What do you do?
Answer: I would first determine whether existing runners can safely be reprioritized, or whether an already provisioned runner pool can handle the release. If additional capacity is still required, I would use an approved emergency capacity path rather than waiting for normal auto-scaling. After the release is stabilized, I would investigate the runner startup time and determine whether warm capacity, faster provisioning, or a dedicated production runner pool is needed.
Production Incident 4. Cost-optimized CI runners are suddenly reclaimed during a cloud capacity event. Active builds are interrupted, new runners cannot be provisioned quickly enough, and critical production deployments are now blocked. How would you recover the delivery pipeline without compromising the release?
Answer: my first priority is to determine whether the pipeline is failing because of a CI configuration problem, or because the underlying runner capacity has disappeared. I would correlate runner termination events with cloud capacity signals, and then establish a safe path to restore critical build and deployment capacity, while protecting the release from partial execution. I will follow a structured response plan like Phase 1. Symptoms. 1. Multiple CI jobs suddenly terminate or move back into the queue. 2. Spot-backed runners disappear and replacement runners are not becoming available. 3. Critical build and deployment pipelines remain blocked despite the pipeline definitions being healthy. What these symptoms are telling us: the CI control plane is still accepting jobs, but its execution capacity has disappeared unexpectedly. The immediate suspicion shifts toward the underlying spot capacity rather than the pipeline definitions themselves. Phase 2. Investigation. 1. Check cloud interruption or reclamation events, runner termination timestamps, and the availability of the selected spot capacity pool. 2. Compare the affected runner's instance type, availability zone, region, and capacity pool with alternative capacity that is currently available. 3. Determine whether interrupted jobs are safely retrievable and whether any build or deployment step was interrupted after making a partial external change. What this investigation is revealing or leading to: the runner instances were reclaimed by the cloud provider and replacement spot capacity is unavailable or delayed. The delivery outage is therefore caused by dependence on a volatile execution pool, with additional risk around jobs that were interrupted mid-execution. Phase 3. Root cause. 1. Critical CI workloads were dependent on spot capacity without sufficient fallback capacity, so a provider-driven reclamation event removed the execution capacity required to continue builds and deployments. Why this is the exact root cause and why not others. The timing of runner termination matches the cloud interruption events, while the CI control plane, job definitions, and source repositories remain operational. The failure is therefore the lack of resilient execution capacity rather than a broken pipeline. Phase 4. Immediate fix. 1. Move critical CI workloads to available on demand or alternative runner capacity. 2. Rerun interrupted jobs only after confirming that their previous executions did not leave partial builds, deployments, or infrastructure changes behind. 3. Resume the critical production release and verify the resulting artifact and deployment state before proceeding further. Expected outcome by doing the above steps: critical CI execution capacity is restored, interrupted work is safely recovered, and the production release can continue without depending on the unavailable spot pool. Phase 5. Long-term prevention. 1. Maintain a fallback runner pool using on-demand or alternative spot capacity across suitable instance types and availability zones. 2. Configure workloads so critical production builds and deployments can automatically move to fallback capacity when spot interruption rates or capacity availability become unsafe. 3. Make build and deployment jobs retry safe and ensure interrupted jobs cannot accidentally publish duplicate or inconsistent artifacts. Expected outcome by doing the above steps: spot capacity remains a cost optimization rather than a single point of failure, allowing critical delivery workloads to continue even when the preferred cloud capacity is reclaimed.
Follow-up 1. Would you completely stop using spot instances for CI after this incident?
Answer: no. Spot capacity can provide substantial cost savings for workloads that tolerate interruption, especially parallel tests and non-critical builds. I would instead classify CI workloads by criticality and interruption tolerance, keeping fallback capacity for production critical paths. The goal is not to eliminate spot usage, but to prevent spot reclamation from becoming a delivery outage.
Follow-up 2. How would you design fallback capacity without keeping an expensive, on-demand runner fleet running all the time?
Answer: I would keep a small baseline of reliable capacity for critical workloads and use auto-scaling to provision additional on-demand or alternative spot capacity when the queue increases. Runner pools can also span multiple instance types and availability zones to improve capacity availability. This gives critical pipelines a reliable execution path without paying for peak capacity continuously.
Follow-up 3. Curveball. A spot runner disappears halfway through a production deployment, and the pipeline automatically retries the job on another runner. Do you allow the retry to continue?
Answer: not blindly. I would first determine what the original runner completed before interruption and whether the deployment operation is idempotent. If the first runner may have partially changed production, an automatic retry could create an inconsistent state or duplicate an operation. I would establish the actual deployment state, reconcile it with the desired state, and only then allow the retry or resume from a known safe point.
Pro tip for this production incident 4.
Do not treat spot capacity as simply a cheaper replacement for on-demand runners. Treat it as an interruptible capacity tier. Keep critical release execution capable of falling back to another capacity source, and make the job itself safe to retry. The most dangerous failure is not losing a runner. It is automatically retrying an interrupted deployment without knowing whether the first runner completed part of the operation.
Production Incident 5. A release pipeline completes successfully, but production contains behavior from an older dependency version. The source commit and deployment are correct, yet the binary was built using cached artifacts from an obsolete dependency or compiler configuration. How would you determine whether the cache produced the wrong binary?
Answer: my first priority is to establish whether the source code, dependency resolution, and compiler configuration actually produce the binary being deployed. Since the pipeline is green and the deployment is correct, I would compare a clean build against the cached build and trace exactly what the cache contributed to the final artifact. I will follow a structured response plan like Phase 1. Symptoms 1. CI and CD pipeline shows success, and the expected Git commit was built. 2. The deployed application exhibits behavior associated with an older dependency or compiler configuration. 3. Rebuilding with the same source can produce a different binary when the cache is bypassed. What these symptoms are telling us: the source and deployment path appear correct, but the build is not deterministic. Suspicion shifts toward dependency resolution, compiler inputs, or stale cached build outputs. Phase 2. Investigation. 1. Compare the dependency lock file, compiler configuration, build inputs, and cache key between the affected build and a clean build. 2. Run the same commit with the cache disabled and compare the resulting binary checksum, dependency versions, and build metadata. 3. Inspect the shared cache contents and determine whether artifacts generated under the obsolete configuration were reused by the current build. What this investigation is revealing or leading to: the clean build produces the expected dependency and binary, while the cached build reuses outputs created under an older build configuration. The evidence points to an incomplete or incorrectly scoped cache key, allowing incompatible build inputs to share cached artifacts. Phase 3. Root cause. 1. The shared cache key did not include all inputs that affect the build, such as the dependency state or compiler configuration, allowing an artifact generated under an obsolete configuration to be reused by a newer build. Why this is the exact root cause, and why not others. The same source commit produces the correct binary when the cache is bypassed, while the cached build reproduces the incorrect binary. That isolates the difference to cached build state rather than the source code, deployment, or runtime environment. Phase 4. Immediate fix. 1. Invalidate the affected shared cache and run a clean build using the intended dependency and compiler configuration. 2. Verify the new binary checksum and embedded build metadata before promoting the artifact. 3. Redeploy the newly generated artifact and confirm that production now exhibits the expected behavior. Expected outcome: by doing the above steps, the incorrect cached artifact is removed from the release path, and production is running a newly verified binary built from the intended inputs. Phase 5. Long-term prevention. 1. Include all material build inputs in the cache key, such as dependency lock file state, compiler version, build configuration, and relevant toolchain versions. 2. Separate incompatible cache namespaces and automatically invalidate caches when build tool or dependency changes require it. 3. Add reproducibility checks that periodically compare cached and clean builds before an artifact is promoted to production. Expected outcome: by doing the above steps, cache reuse remains fast without allowing artifacts produced under incompatible build conditions to contaminate future releases.
Follow-up 1. Why not simply disable the build cache permanently if it can produce an incorrect binary?
Answer: disabling the cache would reduce the immediate risk, but it would also increase build time and resource consumption, and would throw away a useful optimization. The better solution is to make cache reuse safe by correctly including all material build inputs in the cache key and isolating incompatible cache namespaces. I would use a clean build as a diagnostic and validation mechanism, not as the permanent answer to every cache problem.
Follow-up 2. How would you prove that the cache was responsible before invalidating it?
Answer: I would reproduce the build from the same commit with caching enabled and disabled, then compare the dependency graph, compiler inputs, binary checksum, and build metadata. If the cached build consistently produces the incorrect artifact, while the clean build produces the expected one, the cache becomes the control difference. I would then inspect the cache key and cached object metadata to identify which incompatible input was omitted.
Follow up 3 curveball. Clearing the cache fixes the problem once, but the incorrect binary appears again several releases later. What would you investigate next?
Answer: I would assume the cache invalidation problem still exists, rather than treating the successful cache clear as a permanent fix. I would compare the cache keys across the affected releases and look for a build input that changes without changing the current key. I would also check whether multiple branches, operating system runners, compiler versions, or dependency states are sharing the same cache namespace and reproducing the collision.
Pro tip for this production incident 5.
A cache hit is not automatically a good thing. For production builds, the cache key should represent the complete set of inputs that can change the resulting artifact. If changing the compiler, dependency lock file, build flags, or toolchain can change the binary, those inputs need to participate in cache invalidation. Otherwise, the cache can silently turn a valid source commit into a non-reproducible release.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 6. The release pipeline succeeds in development and staging, but fails only when it tries to assume the production cloud identity. The artifact is valid, and lower environments are healthy. How would you isolate the production-only failure?
Answer. My first priority is to determine what changes at the production authentication boundary, because the same pipeline already works in lower environments. I would compare the identity, trust conditions, and authentication context used by each environment and trace the production authentication attempt until I find the exact point of rejection. I will follow a structured response plan like Phase 1. Symptoms. 1. CI and CD pipeline succeeds in development and staging. 2. The production deployment fails specifically while assuming the production cloud identity. 3. The application artifact and lower environment deployments have already been validated successfully. What these symptoms are telling us: the build and general pipeline logic are working. The failure is isolated to the production identity or authorization boundary rather than the application artifact. Phase 2. Investigation. 1. Compare the production role, trust policy, identity provider configuration, and authentication parameters with the configuration that works in staging. 2. Inspect the authentication failure to determine whether the CI identity is rejected before role assumption, or whether the assumed identity fails on its first production API call. 3. Compare the repository, branch, workflow, audience, and other identity claims presented by the production job against the conditions allowed by the production trust policy. What this investigation is revealing or leading to: the CI authentication mechanism is functioning, but the production identity rejects the claims presented by the production workflow, narrowing the failure to a production-specific trust or federation. Configuration. Phase 3. Root cause. 1. The production cloud identity's trust policy does not accept the identity claims presented by the production CI workflow, so role assumption is rejected even though the same authentication path works. In lower environments, why this is the exact root cause and why not others. The CI workflow authenticates successfully against lower environment identities, while the production identity rejects the specific claims presented by the production job. This rules out a general CI authentication failure and points to the production trust configuration. Phase 4. Immediate fix. 1. Correct the production trust configuration so it accepts the intended CI identity and required claims. 2. Re-authenticate through the normal federated path and verify that the pipeline can assume the intended production identity. 3. Resume the deployment and verify that the approved artifact reaches production successfully. Expected outcome by doing the above steps: the approved CI workflow can securely assume the intended production identity and continue the release without bypassing the existing security controls. Phase 5. Long-term prevention. 1. Manage production identity and trust policies through version-controlled infrastructure and peer-reviewed changes. 2. Add an automated pre-deployment identity check that validates the production authentication path before the release begins. 3. Alert on unexpected trust policy or federation changes that could block production deployments. Expected outcome by doing the above steps. Production authentication becomes predictable and testable, allowing identity failures to be detected before they block a critical release.
Follow-up 1. The production role has all the required permissions, but the CI job still receives an access denied error while assuming it. What would you check next?
Answer: I would check the trust relationship before changing the role permissions. Permissions determine what an already assumed identity can do, while the trust policy determines who is allowed to assume that identity. I would compare the actual claims presented by the CI workflow with the conditions in the production trust policy and identify the first condition that rejects the request.
Follow-up 2. How would you safely validate the production identity configuration without performing an actual production deployment?
Answer: I would separate identity validation from resource modification. The CI workflow can authenticate through the same production trust path and perform a tightly scoped read, only check to confirm the expected cloud account and identity. Once that authentication path is proven, the deployment stage can use the same verified identity without making a test change to production.
Follow-up 3. Curveball. The production identity worked yesterday, but today the same pipeline fails immediately after a repository or workflow change. No cloud identity configuration was changed. What would you investigate?
Answer: I would compare the identity claims from yesterday's successful run with today's failed run, particularly the repository, branch, workflow, subject, and audience values. A repository or workflow change can alter the claims evaluated by the production trust policy, even when nothing changed on the cloud side. I would use the last successful authentication as the baseline and identify the changed claim before modifying the production trust configuration.
Pro tip for this production incident 6.
When authentication works in staging but fails only in production, do not immediately add broader permissions to the production role. First, compare the exact identity claims being presented with the conditions in the production trust policy. A role can have every required permission and still reject the CI workflow before those permissions are ever evaluated.
Production incident 7. A Terraform deployment runs successfully for nearly an hour, but fails near the end when the federated cloud credentials expire. Some infrastructure changes have already been applied, while the remaining resources are still pending. How would you recover safely?
Answer: my first priority is to determine exactly what infrastructure Terraform changed before the credential failure, and whether the authentication mechanism can refresh credentials during a long-running operation. I would correlate the failure timestamp with the credential lifetime and Terraform state before deciding whether to resume, retry, or recover the deployment. I will follow a structured response plan like Phase 1. Symptoms. 1. Terraform successfully creates or modifies resources for an extended period before failing with an authentication or authorization error. 2. The failure occurs near the federated credential lifetime rather than at the beginning of the deployment. 3. Terraform state shows that some resources were completed while others remain pending. What these symptoms are telling us: the Terraform configuration and initial authentication are working. The timing and partial infrastructure changes shift suspicion toward credential expiration during the long-running operation. Phase 2. Investigation. 1. Compare the credential issuance time, configured lifetime, and Terraform failure timestamp with the cloud authentication logs. 2. Review Terraform state and execution logs to identify which resources were successfully applied and which operation failed when the credential became invalid. 3. Verify whether the CI authentication mechanism and cloud provider SDK support automatic credential refresh, or whether the pipeline supplied a fixed short-lived credential to Terraform. What this investigation is revealing or leading to: the deployment authenticated successfully at startup, but the credential used by the long-running Terraform process expired before the remaining API operations completed. The investigation points to a credential lifetime and refreshability problem, rather than a Terraform configuration failure. Phase 3. Root cause. 1. The pipeline supplied short-lived federated credentials to a Terraform operation that outlived those credentials. Without a reliable refresh mechanism, available to the running process. Why this is the exact root cause, and why not others. The failure occurs at the credential expiration boundary. While previously executed Terraform operations completed successfully, and the same configuration works when the operation finishes within the credential lifetime, this directly connects the outage to credential expiry rather than an invalid resource definition. Phase 4. Immediate fix. 1. Stop blindly retrying the entire deployment and inspect the current Terraform state and actual cloud resource state first. 2. Re-establish valid federated credentials with sufficient lifetime or a working refresh mechanism. Then run Terraform against the existing state. 3. Confirm that already created resources are recognized correctly and allow Terraform to complete only the remaining changes. Expected outcome by doing the above steps. The partially completed infrastructure is preserved. Terraform reconciles the existing state safely, and the remaining deployment changes are completed without unnecessarily recreating resources. Phase 5. Long-term prevention. 1. Configure the CI authentication path so long-running Terraform operations can obtain refreshed credentials rather than depending on one fixed short-lived credential. 2. Set deployment safeguards that detect when expected execution time may exceed the available credential lifetime before starting a production change. 3. Design long-running infrastructure changes to be restartable and verify Terraform state after interrupted executions. Expected outcome by doing the above steps. Long-running infrastructure deployments can continue beyond a single credential lifetime without unexpectedly losing authentication or leaving partially applied changes difficult to recover.
Follow-up 1. Would you simply increase the federated credential lifetime to several hours to solve the problem?
Answer: not as the only solution. A longer lifetime may reduce the probability of expiration, but it increases the exposure window of the credential and does not address the underlying refreshability problem. I would first determine whether the Cloud SDK or CI authentication mechanism can refresh credentials safely, then choose the shortest practical lifetime that supports the deployment.
Follow-up 2. Terraform failed after applying 70% of the resources. Would you destroy everything and start again?
Answer: no. I would first inspect Terraform state and the actual cloud resources to establish exactly what was successfully applied. After restoring valid credentials, I would run Terraform against the existing state so it can calculate the remaining changes. Destroying and recreating everything could introduce unnecessary downtime, resource replacement, and additional risk.
Follow-up 3. Curveball. The Terraform apply normally takes 20 minutes, but today it takes 2 hours because one cloud API becomes extremely slow. Credentials normally last 1 hour. What would you change?
Answer: I would not rely on the normal 20-minute duration as the credential design assumption. I would verify that the authentication mechanism supports credential refresh throughout the Terraform process and test that behavior under an intentionally long-running operation. I would also investigate the slow API separately, because the immediate credential failure and the underlying infrastructure latency are two different problems that need independent remediation.
Pro tip for this production incident 7.
Never design a long-running infrastructure deployment around the assumption that its initial federated credential will remain valid until the operation finishes. The important question is not simply how long the token lasts, but whether the process performing the work can safely obtain refreshed credentials when required. For production Terraform, test credential refresh behavior under a deliberately long-running operation, rather than discovering the limitation halfway through a real infrastructure change.
Production incident 8. A Terraform deployment times out while provisioning infrastructure. The pipeline automatically retries, but the first attempt actually created some resources before the timeout. The retry provisions duplicates, and production now has conflicting infrastructure. How would you recover without making the situation worse?
Answer: my first priority is to determine what the timed-out deployment actually completed before allowing another execution to modify infrastructure. I would reconcile Terraform state with the real cloud resources, identify the duplicate resources, and establish which resources belong to the intended deployment before making any cleanup changes. I will follow a structured response plan like Phase 1. Symptoms. 1. The deployment reports timeout, even though infrastructure creation started successfully. 2. A retry creates additional resources, instead of recognizing the resources from the first attempt. 3. Production now contains duplicate resources with overlapping configuration or ownership. What these symptoms are telling us: the pipeline timeout does not prove that the infrastructure operation failed. The evidence suggests the first execution partially succeeded, and the retry treated the existing work as if nothing had been created. Phase 2. Investigation. 1. Review the first Terraform execution logs, state, and cloud audit events to determine which resources were created before the timeout. 2. Compare Terraform state with the actual cloud resources and identify resources created by the first attempt versus the automatic retry. 3. Check resource names, tags, IDs, creation timestamps, and dependency relationships to determine which resources are intended and which are duplicates. What this investigation is revealing or leading to: the first deployment successfully created part of the infrastructure, but the pipeline interpreted the timeout as a failed operation and started a second execution. The duplicate resources therefore came from an unsafe retry, rather than Terraform intentionally requiring additional infrastructure. Phase 3. Root cause. 1. The deployment retry was triggered without first establishing the outcome of the timed-out operation, allowing a second infrastructure execution to run against incomplete or stale state. Why this is the exact root cause, and why not others? Cloud audit records confirm that the first attempt created resources before the timeout, while the retry created additional resources for the same intended deployment. This rules out a simple provider duplication issue and identifies the missing outcome verification before retry as the primary cause. Phase 4. Immediate fix. 1. Stop further retries and freeze additional infrastructure changes until the actual resource state is understood. 2. Reconcile Terraform state with the resources that were successfully created and determine which duplicate resources can be safely removed. 3. Validate dependencies and production traffic before deleting any duplicate resource. Then run Terraform again only after state and infrastructure are consistent. Expected outcome by doing the above steps: the duplicate infrastructure is safely identified and removed where appropriate. Terraform state reflects the real environment, and the intended deployment can resume without creating another set of resources. Phase 5. Long-term prevention. 1. Make deployment retries state aware and require verification of the previous execution before starting another infrastructure apply. 2. Use idempotent resource definitions, stable resource identities, and reliable remote state locking to prevent concurrent or conflicting applies. 3. Distinguish execution timeout from confirmed infrastructure failure and require reconciliation before automatically retrying infrastructure changes. Expected outcome by doing the above steps: a timeout no longer automatically triggers a second infrastructure operation against an unknown state, making retries safer and preventing partial success from turning into duplicate production. Resources.
Follow-up 1. Why cannot you simply run Terraform apply again and let Terraform determine what needs to be created?
Answer: that may be safe only after confirming that Terraform state and the real cloud environment are consistent. After a timeout, I cannot assume the state was fully updated or that every provider operation completed cleanly. I would first reconcile the state and inspect the actual resources, then allow Terraform to calculate the remaining changes from a known state.
Follow-up 2. How would you make an automatic infrastructure retry safer?
Answer: I would separate a timeout from a confirmed failure and introduce a reconciliation step before retrying. The system should inspect the previous execution state, provider operation status, and cloud resources before deciding whether another apply is safe. Retries should also use stable resource identities and state locking, so a second execution cannot blindly compete with the first.
Follow-up 3. Curveball. The duplicate resources are already serving production traffic. Deleting them immediately could cause an outage. What do you do?
Answer: I would not delete anything simply because it is identified as a duplicate. First, I would determine which resources are serving traffic, compare their configuration and dependencies, and establish which set should become authoritative. I would then migrate or drain traffic safely if necessary, remove the unintended resources only after validation, and reconcile Terraform state so the final configuration accurately represents production.
Pro tip for this production incident 8.
A timeout is a statement about what the pipeline knows, not necessarily what the infrastructure actually did. A cloud API call can continue or complete even when the CI process stops waiting for its response. Before automatically retrying infrastructure changes, establish the real outcome through provider state, audit events, and Terraform state. Treat unknown execution state as a reconciliation problem first, and a retry problem second.
Production incident 9. Infrastructure changes complete successfully, but the application deployment fails midway. Production now contains a mixture of old and new application components, and some requests behave differently depending on which component handles them. How would you stabilize the release?
Answer: my first priority is to establish exactly which infrastructure and application components changed before making another deployment or rollback decision. I would map the current production state against the intended release and determine whether the old and new components can safely coexist before choosing the safest path back to a consistent state. I will follow a structured response plan like Phase 1, Symptoms. 1. Infrastructure, provisioning, and configuration changes completed successfully. 2. The application rollout failed after only part of the new version was deployed. 3. Production contains both old and new application components, with inconsistent behavior across requests. What these symptoms are telling us: the infrastructure layer has reached the new state, but the application layer has not converged. The immediate risk is not simply a failed deployment. It is an inconsistent production state where old and new components may interact unexpectedly. Phase 2. Investigation. 1. Identify which infrastructure resources, application instances, configuration values, and routing rules were changed before the deployment failed. 2. Compare the old and new application versions for a PI, configuration, database, and dependency compatibility. 3. Trace affected requests to determine whether failures correlate with old versus new components, routing paths, or specific infrastructure changes. What this investigation is revealing or leading to: infrastructure has successfully moved to the new configuration, but the application rollout stopped before all components were updated. The mixed state is producing behavior differences because the old and new application components are not fully compatible with the resulting production configuration. Phase 3. Root cause. 1. The deployment process allowed infrastructure changes to become effective before the dependent application rollout had successfully converged, leaving production with incompatible old and new components. Why this is the exact root cause, and why not others. The affected behavior began only after the infrastructure change and partial application rollout, and requests routed to consistently matched component versions behave normally. This ties the incident to the incomplete deployment sequence rather than an isolated application defect. Phase 4. Immediate fix. 1. Stop further rollout activity and stabilize traffic on the known compatible application version. 2. Restore compatibility between the application and infrastructure by either completing the rollout safely or reverting the infrastructure changes that cannot support the current application. 3. Verify request behavior, application health, configuration, and component versions after production converges on one known safe state. Expected outcome by doing the above steps: production returns to a consistent and compatible state, eliminating the unpredictable behavior caused by old and new components operating against different infrastructure assumptions. Phase 5. Long-term prevention. 1. Design deployment sequencing so dependent infrastructure changes cannot become active before the application is ready to consume them safely. 2. Use progressive delivery, compatibility checks, and deployment gates to prevent an incomplete application rollout from exposing incompatible component combinations. 3. Make deployment and rollback procedures explicitly account for partial failure and define how infrastructure and application state are reconciled. Expected outcome by doing the above steps. A failed application rollout no longer leaves production unknowingly split between incompatible states, and every deployment has a defined path to either a compatible new state or a known safe previous state.
Follow-up 1. Would you immediately roll back the infrastructure changes when the application deployment fails?
Answer: not automatically. I would first determine whether the infrastructure change is backward compatible with the currently running application. If the old application can safely operate with the new infrastructure, completing or stabilizing the application rollout may be safer than reversing infrastructure under production load. I would choose the recovery path based on actual compatibility and blast radius rather than treating rollback as the default.
Follow-up 2. How would you prevent infrastructure and application deployments from becoming inconsistent in the future?
Answer: I would establish explicit dependencies between infrastructure readiness and application rollout, rather than treating them as independent successful steps. Compatibility checks and deployment gates should verify that the application can operate against the new infrastructure before exposing it broadly. For high-risk changes, progressive delivery allows the new infrastructure and application behavior to be validated incrementally before full rollout.
Follow-up 3. Curveball. The new infrastructure includes a database schema change that is backward compatible, but the new application version failed halfway through deployment. Would you roll the database back?
Answer: I would avoid rolling back a schema change simply because the application rollout failed, especially if the migration is designed to be backward compatible. First, I would stabilize the application on the compatible version and determine whether the schema can safely remain in place. I would then either complete the application rollout or use the defined backward compatible migration strategy rather than performing a risky database reversal under production traffic.
Pro tip for this production incident 9.
Treat infrastructure and application changes as one release dependency chain when one depends on the other. A successful infrastructure deployment does not mean the overall release is successful if the application cannot safely operate against that new state. For high-risk changes, design the sequence around backward compatibility so that a failed application rollout can safely coexist with the infrastructure change long enough to recover, rather than forcing an emergency rollback of everything.
Production incident 10. A centralized CI and CD template is updated to support a new release process, but hundreds of repositories begin failing in their production pipelines immediately after the change. Individual application code has not changed. How would you isolate the shared template failure and restore affected releases safely?
Answer: my first priority is to establish what changed globally and whether the failures began immediately after the shared template was updated. I would compare a failing pipeline with the last successful execution, identify the common template change responsible, and determine how to restore release capability without losing the benefits of the new template. I will follow a structured response plan like Phase 1. Symptoms. 1. Multiple unrelated repositories begin failing their pipelines around the same time. 2. The affected repositories have different application code, but their pipelines consume the same centralized CI and CD template. 3. Reverting or pinning the shared template to the previous version causes previously failing pipelines to succeed again. What these symptoms are telling us: the failures are correlated across otherwise unrelated repositories, and the shared template is the common dependency. The strongest suspicion, therefore, shifts toward a centralized pipeline change rather than individual application code. Phase 2. Investigation. 1. Compare the last successful and first failing pipeline executions to identify the exact shared template version and configuration changes introduced between them. 2. Test the affected repositories against the previous and new template versions to determine whether the failure reproduces independently of application code. 3. Identify which template stage, shared action, variable, runner requirement, or deployment behavior changed and determine how many repositories consume that affected path. What this investigation is revealing or leading to, the application repositories remain unchanged, but the new template version introduces a common failure in a shared pipeline stage. Reverting the template removes the failure, isolating the incident to the centralized pipeline dependency. Phase 3. Root cause. 1. A centralized CI and CD template change introduced an incompatible behavior that was automatically consumed by hundreds of repositories without repository-level validation against their existing pipeline assumptions. Why this is the exact root cause and why not others. Unrelated repositories fail through the same shared template change, while restoring the previous template version immediately returns the pipelines to their previous behavior. That evidence rules out widespread application defects and identifies the template change as the common failure mechanism. Phase 4. Immediate fix. 1. Pin affected repositories to the last known good template version, or roll back the centralized template to restore release capability. 2. Identify production-critical repositories and verify their pipelines complete successfully before resuming blocked releases. 3. Preserve the failed template version and collect the failing pipeline evidence before making further changes. Expected outcome by doing the above steps. Affected production pipelines regain their previous working behavior, critical releases can resume, and the faulty template version remains available for controlled investigation. Phase 5. Long-term prevention. 1. Version shared pipeline templates explicitly and require controlled promotion instead of automatically exposing every repository to the newest version. 2. Test template changes against representative repositories and critical pipeline patterns before broad adoption. 3. Provide a documented rollback or pinning mechanism so individual repositories can quickly escape a faulty shared template release. Expected outcome by doing the above steps. Centralized pipeline improvements can be introduced safely without allowing one template change to create an organization-wide production delivery failure.
Follow-up 1. Shared but pipeline template hundreds of locally so changes repositories cannot begin effect failing in their hundreds of production pipelines repositories at once. Immediate.
Answer: that removes the centralized blast radius, but creates a different operational problem. Template duplication, version drift, and inconsistent security or deployment practices across repositories. I would keep centralized reuse but make versions explicit, test changes against representative consumers, and give teams a safe pinning and rollback mechanism. The goal is controlled centralization, not eliminating reuse.
Follow-up 2. How would you test a new shared pipeline template before releasing it organization-wide?
Answer: I would maintain a representative validation suite containing critical production repositories, different application stacks, deployment patterns, runner types, and security requirements. The new template should run against that matrix and compare key outputs such as build behavior, artifact generation, security checks, and deployment stages with the known good version. I would then promote the template progressively, rather than exposing it to every repository at once.
Follow-up 3. Curveball. The new shared template fixed a critical security vulnerability, but it also breaks 200 production pipelines. Would you roll it back?
Answer: I would not choose between security and delivery blindly. First, I would determine the exact vulnerability and the exposure created by reverting. Then isolate the template change responsible for the pipeline failures. If possible, I would keep the security fix while disabling only the incompatible behavior, or release a corrected template version quickly. The objective is to restore production delivery without knowingly reopening the security issue that motivated the change.
Pro tip for this production incident 10.
Treat a centralized pipeline template like a production platform dependency, not just a reusable configuration file. A change to that template can have the blast radius of a platform release, because hundreds of repositories may consume it automatically. Keep explicit template versions. Maintain a small set of representative consumer pipelines for pre-release validation, and make rollback to a known good version a one-step operation. This gives you the benefits of standardization, without turning every template change into an organization-wide delivery risk.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 11. A standard CI runner image. is upgraded to a newer runtime and toolchain version. Hundreds of previously successful builds now fail, even though the application repositories and source commits have not changed. How would you isolate the runner image change and restore reliable builds?
Answer: my first priority is to determine what changed in the build environment rather than immediately changing application code. Since previously successful commits are now failing without source changes, I would compare the old and new runner environments and identify the exact runtime, compiler, dependency, or toolchain change responsible. I will follow a structured response plan like Phase 1. Symptoms 1. Previously successful commits begin failing after the standard runner image is upgraded. 2. Multiple unrelated repositories experience similar build or test failures. 3. Rerunning the same commit on the previous runner image succeeds. What these symptoms are telling us: the application source has not changed, while the build environment has. The failure therefore points toward a runner image compatibility change rather than a new application defect. Phase 2. Investigation. 1. Compare the old and new runner images for runtime, compiler, operating system, package manager, and pre-installed tool versions. 2. Rerun the same failing commit on both runner image versions and compare the first failing build or test step. 3. Inspect the runner image release notes and dependency resolution to identify a changed tool or runtime behavior that affects the failing repositories. What this investigation is revealing or leading to: the same source commit succeeds on the previous runner image but fails on the upgraded image, and the first failure correlates with a changed runtime or tool version. The evidence points to an incompatible runner environment change rather than application source changes. Phase 3. Root cause. 1. The standard runner image was upgraded without validating compatibility with existing repositories, and a changed runtime or build tool introduced behavior that invalidated previously working build. Assumptions: why this is the exact root cause and why not others. The source commit is identical. The failure appears only with the new runner image, and the previous image reproduces the successful build. That isolates the regression to the runner environment rather than the application or deployment. Phase 4. Immediate fix. 1. Pin affected pipelines to the last known good runner image while the compatibility issue is investigated. 2. Rerun the critical production builds and verify that the expected artifacts are generated successfully. 3. Preserve the failing runner image version and its logs so the regression can be reproduced without repeatedly changing production build conditions. Expected outcome by doing the above steps: previously working builds regain a stable execution environment, allowing critical releases to proceed, while the incompatible runner image is investigated safely. Phase 5. Long-term prevention. 1. Version and pin standard runner images, instead of allowing production pipelines to consume an untested moving image. 2. Validate new runner images against a representative build matrix before organization-wide rollout. 3. Introduce staged runner image adoption with a documented rollback path for pipelines affected by runtime or toolchain regressions. Expected outcome by doing the above steps: runner image upgrades become controlled infrastructure changes, allowing toolchain improvement without unexpectedly breaking large numbers of previously working production pipelines.
Follow-up 1. Why not simply update every application's dependencies to work with the new runner image?
Answer: I would not immediately modify hundreds of application repositories to compensate for an unvalidated platform change. First, I would determine whether the runner upgrade introduced a genuine compatibility requirement or an unintended regression. If the new image is correct, affected applications can then be migrated deliberately. Otherwise, the runner image should be corrected or rolled back rather than pushing unnecessary changes into application code.
Follow-up 2. How would you safely roll out a new standard runner image across hundreds of repositories?
Answer: I would first validate the image against a representative set of repositories covering different languages, runtimes, build systems, and deployment patterns. Then I would release it progressively to a small group of repositories and monitor build success, failure patterns, and execution time before expanding adoption. The previous runner image should remain available, so affected pipelines can immediately revert if a regression appears.
Follow-up 3 curveball. The new runner image fixes a critical security vulnerability, but rolling it back restores vulnerable tooling. What would you do?
Answer: I would avoid treating rollback as the final solution, because it would knowingly restore the security exposure. I would first isolate the specific tool or runtime causing the build regression and determine whether the security fix can remain, while that component is corrected or pinned. If necessary, I would temporarily provide a controlled exception for critical builds while producing a corrected runner image that preserves the security update.
Pro tip for this production incident 11.
Treat the CI runner image as a version production dependency. An upgrade to the runner is effectively a platform change because it can alter runtimes, compilers, operating system behavior, package managers, certificates, and pre-installed tooling without any application repository changing. Pin the image, test upgrades against representative builds, and keep the previous image available for rapid rollback, so a runner upgrade never becomes an uncontrolled organization-wide change.
Production incident 12. A new architecture and runtime version matrix is added to the CI pipeline, multiplying the number of build and test jobs. A normally fast production release now takes several hours, and the release window is at risk. How would you regain delivery speed without losing the required coverage?
Answer: my first priority is to determine whether the additional matrix combinations provide meaningful release confidence or are simply multiplying redundant work. I would measure where the pipeline time is being spent, identify the combinations that actually require full validation, and separate critical release checks from broader compatibility testing. I will follow a structured response plan like Phase 1. Symptoms. 1. A pipeline that normally completes within the release window now takes several hours. 2. The new architecture and version matrix has multiplied the number of concurrent and sequential jobs. 3. The critical production deployment remains blocked, while non-production matrix combinations continue running. What these symptoms are telling us: the release is not necessarily failing. The delivery system has created excessive validation work, and pipeline execution time has become the bottleneck. Phase 2. Investigation. 1. Compare the previous and current pipeline graphs to quantify how many jobs the new matrix added and which combinations consume the most execution time. 2. Determine which architecture and runtime version combinations are production critical, supported, duplicated, or already covered indirectly by other tests. 3. Analyze runner utilization, queue time, test duration, and dependency relationships to determine whether the delay comes from excessive matrix size, serialized stages, or insufficient runner capacity. What this investigation is revealing or leading to: the matrix has multiplied validation combinations far beyond what is required for the current production release. While several jobs provide overlapping coverage, the pipeline is spending most of its time validating compatibility combinations that do not need to block the critical deployment. Phase 3. Root cause. 1. The pipeline introduced a broad architecture and runtime version matrix as a mandatory release gate, causing redundant and low-priority validation jobs to extend the critical production path. Why this is the exact root cause, and why not others? The release duration increased immediately after the matrix expansion, and the critical deployment is waiting on matrix combinations that are not required for the production target. This makes pipeline design and execution strategy the primary bottleneck rather than runner failure or application build performance. Phase 4. Immediate fix. 1. Separate production critical validation from extended compatibility testing, and allow only the required production combinations to gate the release. 2. Cancel or defer redundant matrix jobs that are not required for the current production target, while preserving their results for later validation. 3. Complete the critical release path and verify the production artifact before allowing the broader matrix to continue asynchronously. Expected outcome: by doing the above steps, the critical release returns to an acceptable execution time, while the broader compatibility coverage continues without unnecessarily blocking production delivery. Phase 5. Long-term prevention. 1. Classify matrix combinations by release criticality and define which combinations must block production versus run asynchronously. 2. Use change-aware matrix selection, so a release validates only the architectures and runtime versions affected by the change when broader coverage is unnecessary. 3. Monitor pipeline duration, queue time, matrix growth, and redundant test execution as release engineering metrics. Expected outcome by doing the above steps. The pipeline scales its validation coverage without allowing matrix growth to turn every production release into a multi-hour process.
Follow-up 1. Would you simply reduce the number of architecture and runtime combinations to make the pipeline faster?
Answer: not without understanding the coverage those combinations provide. Removing matrix entries blindly can create compatibility gaps that may only appear after release. I would first classify the combinations by production relevance, risk, and redundancy. Then keep mandatory gates for critical coverage while moving lower-risk combinations to asynchronous or scheduled validation.
Follow-up 2. How would you decide which matrix jobs should block a production deployment?
Answer: I would base the decision on the actual production support matrix, rather than treating every combination equally. The target production architecture and runtime should always be covered, along with combinations representing high-risk compatibility boundaries. Other combinations can run in parallel or asynchronously, when their failure would not make the current production release unsafe.
Follow-up 3. Curveball. The matrix is required by the organization because customers genuinely run all of these architecture and runtime combinations. You cannot remove any coverage. What would you change?
Answer: I would preserve the required coverage but redesign where and when it executes. Production critical combinations should remain on the release path, while independent compatibility jobs should run in parallel on appropriately scaled runners or continue asynchronously after the critical artifact is approved. I would also look for test sharding, reusable build artifacts, and incremental validation, so the same work is not repeated across every matrix combination.
Pro tip for this production incident 12.
A large CI matrix is not automatically better coverage. The important distinction is between coverage that must block a release and coverage that provides additional confidence but can run asynchronously. Before allowing a matrix to become a production gate, map every combination to a real supported environment or risk scenario. Otherwise, every new architecture or runtime version can silently increase the critical path duration until the pipeline itself becomes the release bottleneck.
Production incident 13. A CI pipeline downloads an external build tool directly from a third-party source. The dependency suddenly becomes unavailable, and a rebuild can no longer reproduce the artifact used by the previous production release. How would you restore deterministic builds?
Answer: my first priority is to determine exactly which external dependency disappeared, and whether the existing production artifact can still be traced to a known version of that dependency. I would identify the original build inputs, restore access to a trusted copy if possible, and then remove the external dependency from the uncontrolled part of the production build path. I will follow a structured response plan like Phase 1. Symptoms. 1. A previously successful pipeline can no longer download an external build tool or package. 2. Rerunning the same git commit fails because the required dependency is no longer available at the expected location. 3. The existing production artifact still works, but the organization cannot reliably reproduce it from source. What these symptoms are telling us: the source code has not necessarily changed. The build has become dependent on an external artifact that is outside the organization's availability and version control boundary. Phase 2. Investigation. 1. Inspect the historical pipeline configuration. Build logs, lock files, and artifact metadata to identify the exact third-party tool version and download location used for the production build. 2. Check whether the dependency still exists under another version or location, and verify the integrity of any recovered copy against the original build metadata. 3. Compare the existing production artifact's build metadata checksum, dependency versions, and git commit with a clean rebuild using the recovered dependency. What this investigation is revealing or leading to: the production artifact was built using an externally hosted dependency that was not stored or mirrored internally. The source remains reproducible, but the original build environment is not, because one of its required inputs has disappeared. Phase 3. Root cause. 1. The production build depended directly on an external, unpinned, or non-mirrored build dependency, making artifact reproduction dependent on the continued availability and contents of a third-party source. Why this is the exact root cause, and why not others. The same source commit can be rebuilt only when the original dependency is recovered, while the application source and deployment configuration remain unchanged. The missing external build input is therefore the direct reproducibility failure. Phase 4. Immediate fix. 1. Recover the exact dependency version from a trusted internal cache, previous build environment, approved mirror, or verified historical artifact. 2. Rebuild using the recovered dependency, and compare the resulting artifact against the known production artifact before promoting anything. 3. Preserve the recovered dependency and document its checksum and version, so further releases are not blocked by the same disappearance. Expected outcome: by doing the above steps, the build can be reproduced from a verified dependency, the production artifact remains traceable, and the release pipeline can resume without introducing an unverified replacement. Phase 5. Long-term prevention. 1. Mirror critical third-party build dependencies into an organization-controlled artifact repository. 2. Pin dependency versions and verify checksums or signatures instead of downloading and implicitly changing external artifact. 3. Record the complete build dependency set and artifact provenance alongside every production release. Expected outcome: by doing the above steps, production builds no longer depend on the continued availability or mutable contents of an external source, making historical releases reproducible and auditable.
Follow-up 1. If the third-party dependency is publicly available again, would you simply download it and rebuild?
Answer: not immediately. I would first verify that it is the exact version used by the original production build, and validate its checksum or signature against trusted historical information. Once the dependency is verified, I would rebuild and compare the resulting artifact before considering it suitable for production. Availability alone does not establish artifact identity.
Follow-up 2. How would you prove that the newly rebuilt artifact is equivalent to the original production artifact?
Answer: I would first compare the build inputs, including the git commit, dependency versions, toolchain versions, and build configuration. Then I would compare artifact checksums and relevant embedded build metadata. If the artifacts differ despite identical declared inputs, I would investigate non-deterministic build inputs such as timestamps, generated files, environment variables, or compiler behavior before promoting the rebuild.
Follow-up 3. Curveball. You discover that the third-party tool is available again, but its latest download produces a different checksum from the version used for the production release. What do you do?
Answer: I would not treat the newly downloaded file as the original dependency, simply because the file name and version appear identical. I would preserve the known production artifact, investigate the checksum difference, and determine whether the upstream dependency was replaced, repackaged, or compromised. Until its provenance is established, I would use a verified internal copy or previously trusted artifact rather than introducing an unknown build input.
Pro tip for this production incident 13.
If a production artifact matters, every input required to reproduce it matters too. A dependency being publicly downloadable today does not mean it will be available tomorrow, nor does the same version number guarantee the same bytes. For critical build tools, keep an internal immutable mirror and record the exact checksum or signature used during the build. That turns a third-party availability problem into a controlled artifact management problem.
Production incident 14. A large release triggers hundreds of parallel builds, causing the package or container registry to throttle requests. Builds begin failing or waiting for retries, and a critical production release cannot complete. How would you restore the release without simply overwhelming the registry further?
Answer: my first priority is to establish whether the build failures are caused by the registry itself, rather than application code or the CI runners. I would correlate the failures with registry throttling, identify which workloads are generating the request surge, and restore the critical release path while reducing unnecessary registry pressure. I will follow a structured response plan like Phase 1. Symptoms. 1. Multiple otherwise healthy CI jobs begin failing during dependency or image pulls. 2. Registry responses show throttling or rate limit errors, while runner capacity remains available. 3. The failures increase sharply when the large release triggers many builds in parallel. What these symptoms are telling us: the CI runners are available and the pipelines are executing, but they cannot obtain required packages or container layers. The timing and request pattern shift suspicion toward registry capacity or rate limiting. Phase 2. Investigation. 1. Inspect registry rate limit responses, request counts, throttling metrics, authentication activity, and the timestamps of failed package or image downloads. 2. Compare the affected builds to determine whether they are repeatedly downloading the same dependencies or container layers, instead of using local or shared caches. 3. Identify which release jobs, runners, repositories, or accounts are generating the highest request volume, and determine whether the registry limit is global, per account, per repository, or per client. What this investigation is revealing or leading to: the registry is receiving a sudden request surge from parallel builds, with repeated downloads of common dependencies and image layers consuming the available request allowance. The evidence points to registry throttling caused by release concurrency and inefficient dependency retrieval, rather than broken application builds. Phase 3. Root cause. 1. The release introduced more concurrent registry requests than the package or container registries allowed capacity, while the CI design lacked sufficient caching, request control, or registry capacity planning for large release bursts. Why this is the exact root cause, and why not others. The same builds succeed when registry pressure decreases, while registry throttling rises directly with the release's parallel request volume. Runner health and application source remain unchanged, making registry rate limiting the direct cause of the build failures. Phase 4. Immediate fix. 1. Reduce non-critical build concurrency and prioritize the production release jobs that require registry access. 2. Enable or increase appropriate package and container layer caching so repeated downloads do not continue consuming registry capacity. 3. Retry failed builds using controlled backoff, rather than allowing hundreds of jobs to retry simultaneously. Expected outcome by doing the above steps: registry request pressure falls below the throttling threshold, critical builds regain access to their dependencies, and the production release can continue without creating another request surge. Phase 5. Long-term prevention. 1. Use organization-controlled package and container mirrors or caching proxies for frequently consumed dependencies and base images. 2. Configure CI concurrency limits, retry backoff, and request-aware workload scheduling for large release events. 3. Monitor registry utilization, throttling rate, cache hit ratio, and peak request volume as part of release capacity planning. Expected outcome by doing the above steps: large releases can scale CI execution without overwhelming the dependency registry, while caching and controlled concurrency reduce unnecessary external requests.
Follow-up 1. Why not simply increase the registry rate limit if the organization controls the registry?
Answer: increasing the limit may help, but I would first determine whether the request surge is legitimate or caused by inefficient CI behavior. If every runner repeatedly downloads the same dependencies, increasing the limit only moves the bottleneck and can increase registry cost. I would combine appropriate capacity with caching, controlled concurrency, and retry backoff, so the system does not depend on an unnecessarily high request rate.
Follow-up 2. Why can aggressive automatic retries make this incident worse?
Answer: when the registry is already throttling requests, Immediate retries create another wave of requests before the registry has recovered. This can turn a temporary rate limit into a sustained request storm. I would use exponential backoff with jitter, limit concurrent retries, and prioritize production-critical jobs so recovery traffic is controlled rather than synchronized across hundreds of runners.
Follow up 3 curveball. The registry shows no global rate limit breach, but only one large release is failing, while smaller releases continue normally. What would you investigate?
Answer: I would look for a more specific quota or throttling boundary, rather than assuming the entire registry is overloaded. The release may be hitting a per account, per repository, per IP, authentication, or concurrent download limit. I would compare the failing releases request pattern with a successful smaller release and identify which boundary is being exhausted before changing global registry capacity.
Pro tip for this production incident 14.
When a registry starts throttling during a large release, do not look only at the registry's maximum request limit. Look at how many times your CI system is asking for the same thing. Hundreds of runners repeatedly pulling identical base images or dependencies is usually a caching and concurrency design problem as much as a registry capacity problem. A well-designed CI system should absorb release bursts through shared caching, controlled concurrency, and intelligent retry behavior, instead of turning every release into a registry traffic spike.
Production incident 15. A critical production defect requires an emergency hotfix, but the release pipeline cannot proceed because a mandatory security or compliance stage is unavailable. The application change is ready, but an unrelated pipeline dependency is blocking the release. How would you handle the hotfix safely?
Answer: my first priority is to separate the actual production risk from the availability problem in the delivery pipeline. I would determine whether the mandatory stage is validating something essential to this specific hotfix, or whether the release is being blocked by a shared dependency that is temporarily unavailable. Then use the organization's emergency change controls to restore delivery without bypassing security blindly. I will follow a structured response plan like Phase 1. Symptoms. 1. The production defect requires an urgent hotfix, but the release pipeline cannot reach the deployment stage. 2. The application build and required tests have completed successfully. 3. A mandatory security, compliance, dependency, or approval service is unavailable and is blocking the pipeline. What these symptoms are telling us: the hotfix itself is ready, but the delivery path is blocked by an external pipeline dependency. The immediate problem is release path availability rather than application readiness. Phase 2. Investigation. 1. Identify exactly which pipeline stage is unavailable and determine whether the failure is caused by the security tool, dependency service, approval system, registry, or shared pipeline. Infrastructure. 2. Determine whether the blocked check is required for this specific hotfix and whether a previously approved emergency change procedure defines an alternate validation or approval path. 3. Verify the hotfix artifact, source commit, test results, security evidence already available, and the production change scope before considering any exception. What this investigation is revealing or leading to: the hotfix is technically ready, but a shared mandatory service unrelated to the application change is preventing the normal release path. The evidence establishes that the real decision is whether an approved emergency path can provide equivalent risk control without waiting indefinitely for the unavailable dependency. Phase 3. Root cause. 1. The production release process has a mandatory dependency on a shared security or compliance stage with no resilient emergency execution path, so an unrelated service outage can block time-critical production remediation. Why this is the exact root cause and why not others. The hotfix passes the available application and release validations, while the pipeline remains blocked specifically at the unavailable shared dependency. Restoring that dependency, or using the organization's approved emergency path, removes the release blocker, identifying pipeline dependency coupling as the primary cause. Phase 4. Immediate fix. 1. Engage the appropriate incident, security, and change approval owners and determine whether the blocked stage can be restored quickly enough for the incident timeline. 2. If the normal dependency cannot be restored in time, use only the organization's pre-approved emergency release procedure, including the required compensating security and approval controls. 3. Deploy the hotfix through the controlled emergency path and immediately verify the production change, security posture, and application behavior. Expected outcome by doing the above steps. The critical production fix is released through an authorized and auditable path, without treating an emergency as justification for uncontrolled pipeline bypasses. Phase 5. Long-term prevention. 1. Define an emergency release path with explicit approvals, compensating controls, audit logging, and post-release validation. 2. Remove unnecessary single points of failure from mandatory pipeline stages by providing highly available services or controlled fallback mechanisms. 3. Classify pipeline dependencies by whether they are mandatory for every release, mandatory only for specific changes, or eligible for emergency compensating controls. Expected outcome by doing the above steps. A failure in an unrelated shared service cannot indefinitely prevent critical production remediation, while security and compliance controls remain enforceable during emergency releases.
Follow-up 1. Would you simply disable the security or compliance stage to get the hotfix into production?
Answer: no. Disabling a mandatory control without an approved process creates a second production risk and may violate the organization's security or compliance requirements. I would first determine whether the service can be restored quickly. If not, I would use the documented emergency change process with compensating controls, explicit authorization, and post-release validation.
Follow-up 2. What would you consider a reasonable compensating control if the normal security scan is unavailable?
Answer: it depends on the organization's approved emergency procedure, but I would use the strongest available alternatives rather than simply skipping the check. For example, the team could validate the exact source change, review the existing security scan history, verify dependency and artifact provenance, perform targeted security checks, obtain explicit security approval, and run the full scan immediately after the service is restored. The exception should also be documented and auditable.
Follow-up 3. Curveball. The security service is expected to remain unavailable for 4 hours, but the production vulnerability being fixed is actively affecting customers. What would you do?
Answer: I would treat the production impact and the security control outage as two concurrent risks rather than allowing one to automatically override the other. I would escalate through the emergency change process, involve the security owner, and determine whether the hotfix can be released using documented compensating controls. If authorized, I would deploy the narrowly scoped fix, closely monitor the change, and run the unavailable security validation as soon as the service returns.
Pro tip for this production incident 15.
A production pipeline should be secure by design, but security controls should not become an unplanned single point of failure during a critical incident. The mature approach is not to create a secret bypass. It is to design an explicit emergency release path in advance. That path should define who can authorize the exception, which compensating controls are mandatory, what must be logged, and which deferred checks must run immediately after the dependency is restored.
Category 1 Summary and Key Takeaways. What we mastered in pipeline engineering.
Core engineering principles proven in Category 1. 1. Artifact immutability. Never deploy by mutable tags. Always pin and deploy by unique SH, A256 image digests. 2. Determinism and caching. Treat build tools as version dependencies and hash all material inputs into cache keys. 3. Resilient execution. Separate production release capacity from general workloads and build idempotency into retries. 4. Controlled centralization. Version pipeline templates explicitly so a single change cannot break hundreds of repos. Mastering pipeline execution is the foundation of reliable continuous delivery.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Focus shift from Category 1, build pipelines, to Category 2, state reconciliation.
In Category 1, we mastered the delivery engine, proving how code is built, tested, packaged, and pushed through execution pipelines. But in modern cloud-native engineering, a green pipeline is only half the battle. Shipping a clean container image means nothing if an automated GitOps controller silently reverts your hotfix. A stale environment overlay deploys staging secrets to production, or a branch promotion. Mistake overwrites live cluster state. In Category 2, we undergo a fundamental mindset shift, moving from imperative execution building and pushing to declarative reconciliation, keeping cluster state in sync with Git. Welcome to the real world of modern release engineering.
Category 2, declarative state and release mechanics.
In a GitOps-driven architecture, Git is no longer just a code repository. It is the living, declarative source of truth for production infrastructure. GitOps controllers like Argo CD and Flux continuously reconcile cluster state against Git declarations. However, this paradigm introduces brand new, complex failure modes, automated reconciliation drift loops, split brain ownership between Terraform and Helm, stale configuration overlays, and release branch divergence. Category 2 equips you to diagnose and resolve production outages when state management and release boundaries break down.
Category 2 incidents. Incidents 16 to 25.
Here are the 10 modern GitOps and release production incidents we will cover in this category. Incident 16. GitOps immediately reverts an emergency production fix. Incident 17. Git revert does not restore runtime state. Incident 18. Stale GitOps overlay deploys an old production configuration. Incident 19. GitOps controller falls behind during a mass release. Incident 20. Terraform, Helm, and GitOps fight over resource ownership. Incident 21. Wrong branch reaches production. Incident 22. Release tag points to a mutable artifact. Incident 23. Hotfix branch diverges from mainline. Incident 24. GitOps secret reference points to the wrong environment. Incident 25. Shared configuration change triggers a mass deployment. Let's dive into Production Incident 16.
Production Incident 16. A critical production outage occurs. An engineer hot patches the live Kubernetes cluster directly to restore service, but minutes later the outage returns as the automated GitOps controller reverts the fix back to the broken state. Declared in Git. What's your response?
Answer. My first priority is to stabilize production by safely managing the GitOps reconciliation loop before applying a durable fix. I would determine whether to temporarily pause automated sync or immediately commit the emergency fix to Git, then bring the live environment and repository back into alignment. I will follow a structured response plan like Phase 1. Symptoms. 1. A live cluster hot patch temporarily restores production service. 2. Minutes later, the outage recurs without any human intervention. 3. The GitOps controller logs show an automated reconciliation event overriding the manual change. What these symptoms are telling us, the application failure itself was temporarily fixed, but the GitOps reconciliation mechanism treated the manual edit as drift and enforced the broken declared state. Phase 2. Investigation. 1. Inspect the GitOps controller sync status, event history, self-healing configuration, and commit history. 2. Compare the live cluster object manifest with the state declared in the target Git repository branch. 3. Verify whether automated sync or self-healing is active on the affected application. What this investigation is revealing or leading to, the GitOps controller is behaving as designed by enforcing the repository state. The investigation points away from a cluster failure and directly toward a process conflict between manual cluster editing and automated drift reconciliation. Phase 3. Root cause. 1. An emergency fix was applied out of band directly to the cluster, while automated self-healing was active, causing the GitOps controller to overwrite the manual patch during its next reconciliation. Loop. Why this is the exact root cause, and why not others. The outage recurs precisely when the GitOps controller syncs, and committing the fix to Git permanently stabilizes the cluster. That proves the failure was driven by the drift reconciliation loop, overriding manual cluster state. Phase 4. Immediate fix. 1. Pause automated sync or self-healing on the specific GitOps application resource to gain immediate operational control. 2. Apply the emergency fix to the cluster and immediately commit the exact change to the declarative Git repository. 3. Re-enable automated sync after verifying that the Git repository state matches the live cluster fix. Expected outcome by doing the above steps. Production is stabilized immediately, and the GitOps controller resumes continuous reconciliation against a repository state that contains the emergency fix. Phase 5. Long-term prevention. 1. Establish a documented break glass procedure that defines how to pause auto-sync or execute fast-track Git commits during an outage. 2. Enforce cluster access controls so out-of-band manual edits are restricted or flagged automatically. 3. Implement automated post-commit hooks or fast path PR workflows so emergency fixes can move through Git in seconds rather than requiring manual cluster intervention. Expected outcome by doing the above steps. Emergency changes reach production rapidly through version control, eliminating the need for unsynchronized cluster edits and preventing automated revert loops.
Follow-up 1. Why not simply leave GitOps auto-sync permanently disabled to avoid future revert loops?
Answer. Disabling auto-sync permanently destroys the core benefit of GitOps: automated drift detection, auditability, and self-healing. Leaving it off creates silent configuration drift, where the cluster no longer matches Git. I would keep auto-sync enabled, and instead implement a fast-track Git workflow or a controlled break glass pause mechanism strictly for active incidents.
Follow-up 2. If an engineer must edit the cluster directly during a severe outage, how should they coordinate with the GitOps system?
Answer. They should first disable automated self-healing or auto-sync on that specific application resource using the GitOps CLI or UI. Once the cluster is patched and service is restored, they must immediately push a matching commit to the Git repository before re-enabling sync. This prevents the controller from reverting the change when auto-sync is restored.
Follow-up 3. Curveball. You paused auto-sync, patched the cluster, and committed the fix to Git. But when you re-enable sync, GitOps still tries to overwrite your change with an older state. What happened?
Answer. The GitOps application target was likely pointing to a different branch, tag, or environment overlay than the one where the fix was committed. Alternatively, an automated pipeline overwrote the Git commit with a stale manifest. I would check the exact target revision and path configured in the GitOps application manifest to ensure the controller is syncing against the specific commit containing the fix.
Pro tip for this production incident 16.
In a GitOps environment, your cluster is a read-only projection of Git. Never treat manual cluster edits as a solution. Treat them as a temporary state override that will be destroyed by the reconciliation loop. If you must patch a cluster during an outage, the CLI command to pause auto-sync is just as important as the patching command itself. Always pair a cluster edit with a matching Git commit before turning self-healing back on.
Production incident 17. A bad deployment introduces errors. An engineer executes git revert and merges the PR. The deployment pipeline succeeds and application code rolls back. But production errors persist because database schema changes and queue state created by the failed deployment remain. How do you recover?
Answer. My first priority is to separate stateless application code from stateful runtime infrastructure. I would determine what persistent state database migrations, cache keys, or message queues was created by the bad deployment. Evaluate whether the reverted code is compatible with that state, and execute a state reconciliation plan. I will follow a structured response plan like Phase 1. Symptoms. 1. Code revert pipeline shows success, and deployment confirms old container image is running. 2. Application logs report database column missing errors, queue deserialization panics, or cache miss spikes. 3. Production remains unstable despite Git history, showing a clean rollback to the previous working commit. What these symptoms are telling us: the application code was successfully reverted in version control, but persistent runtime state operates under an independent lifecycle that Git code reverts cannot automatically undo. Phase 2. Investigation. 1. Compare the database migration history, schema state, cache contents, and message queue payload formats between the failed commit and reverted commit. 2. Inspect application crash logs to verify if the reverted code is attempting to read or write against incompatible persistent data state. 3. Identify whether the bad deployment executed destructive schema changes, unmigrated data transformations, or written incompatible queue messages. What this investigation is revealing or leading to: the application code is running the previous version, but the database schema and active message payloads reflect the newer, reverted version. The investigation isolates the outage to a data state compatibility boundary. Phase 3. Root cause. 1. A git revert only modifies stateless application code. In version control, persistent databases, message queues, and caches operate under independent lifecycles that Git cannot automatically roll back. Why this is the exact root cause, and why not others. The code deployment succeeded cleanly, but the reverted application panics specifically when querying database tables or queues altered by the bad version. That proves Git code history and persistent data lifecycles have diverged. Phase 4. Immediate fix. 1. Execute a targeted database down migration or schema reconciliation script to restore data compatibility with the reverted code. 2. Clear or dead letter queue messages and cache entries generated during the window the bad deployment was active. 3. Verify that application error rates return to baseline once code version and runtime data state are aligned. Expected outcome by doing the above steps: stateless application code and stateful runtime data are restored to a mutually compatible state, resolving production panics. Phase 5. Long-term prevention. 1. Enforce the expand and contract pattern for all database migrations, so schema changes are strictly backward compatible with previous application versions. 2. Require a documented state reconciliation runbook or down migration plan alongside any pull request modifying data schemas or queue structures. 3. Establish explicit deployment sequencing, where database migrations and application code rollouts are validated and executed as independent lifecycle gates. Expected outcome by doing the above steps: Git code reverts can be executed safely at any time without causing runtime data incompatibility or persistent database failures.
Follow-up 1. Why could not the automated pipeline execute a database down migration automatically when Git revert was merged?
Answer: automatic down migrations are dangerous because rolling back a schema can result in permanent data loss if new columns contained live customer data created during the incident window. A Git revert should trigger an alert for stateful changes, requiring engineers to explicitly decide whether to roll data forward or execute a safe, non-destructive schema cleanup.
Follow-up 2. How do you handle message queues when a reverted application can no longer parse messages produced by the bad version?
Answer: I would isolate the unparsable messages into a dead letter queue DLQ rather than purging them. This prevents the reverted application from crash looping, while preserving the payload data for later inspection, transformation, or replay once the schema logic is corrected.
Follow-up 3. Curveball. You reverted the application code, but an external SaaS feature flag service is still serving the new feature path to 50% of users. What happens?
Answer: the application will attempt to execute code paths that no longer exist in the reverted binary, resulting in runtime exceptions. External state managed outside Git like SaaS feature flags or external APIs must be updated or integrated into the deployment pipeline, so code reverts automatically disable or evaluate dependent flags safely.
Pro tip for this production incident 17.
Git code history is stateless, but production systems are stateful. Never assume Git revert is a complete rollback strategy for applications with persistent data. Databases, caches, queues, and external SaaS configurations operate under independent lifecycles. Always design database migrations to be strictly backward compatible with the previous application code version before merging.
Production incident 18. A repository restructuring moves, customize environment, overlays to a new directory, values in the new path, and continues syncing from the obsolete caches directory operate undunder. Production runs on stale configuration. How do you resolve the drift?
Answer: my first priority is to identify the precise directory path the GitOps controller is reading and align the controller's target path with the active repository structure. I would inspect the GitOps application manifest, verify the target path, and eliminate obsolete directory overlays. I will follow a structured response plan like Phase 1. Symptoms. 1. Git commit logs confirm configuration updates were merged into the repository. 2. GitOps controller reports synced and healthy, but live cluster resources retain old environment variables. 3. Developers report that changes to manifests have zero effect on running production pods. What these symptoms are telling us: the GitOps controller is successfully reconciling, but it is reconciling against the wrong desired state source, proving that a healthy GitOps status does not guarantee a correct GitOps configuration. Phase 2. Investigation. 1. Inspect the GitOps application CRD spec, specifically checking spec.source.path against the updated repository folder structure. 2. Compare the directory path modified in recent commits with the directory path configured in the GitOps management manifest. 3. Verify if obsolete overlay directories still exist in the Git branch and contain valid, but stale, YAML manifests. What this investigation is revealing or leading to: the directory restructuring created a new overlay path, but the GitOps application manifest was never updated to point to it. The controller is reconciling a valid, but orphaned and unupdated directory. Phase 3. Root cause. 1. The repository reorganization introduced a path divergence where application commits updated one folder overlay, while the GitOps controller remained configured to reconcile a legacy path. Why this is the exact root cause, and why not others? The controller reports healthy sync because the legacy directory still contains valid YAML. The failure is entirely path misalignment between developer commits and the controller's declared target source. Phase 4. Immediate fix. 1. Update spec.source.path in the GitOps application manifest to point directly to the new active overlay directory. 2. Delete or archive the legacy directory path in the Git repository to prevent future path ambiguity. 3. Trigger a manual sync or force reconciliation and verify that live cluster pods receive the updated configuration. Expected outcome by doing the above steps: the GitOps controller syncs from the correct active overlay path, applying the missing configuration updates to production. Phase 5. Long-term prevention. 1. Co-locate GitOps application manifests with the underlying customized overlays or manage them via an automated app of apps pattern. 2. Implement PR linting that flags orphaned or unreferenced manifest directories during repository restructurings. 3. Enforce automated integration tests that validate whether commit modifications in a path trigger an actual GitOps sync delta. Expected outcome by doing the above steps: directory path changes automatically update dependent GitOps application specs, preventing stale overlay syncs.
Follow-up 1. Why did not the GitOps controller throw an error when the new directory overlay was created?
Answer: because GitOps controllers do not automatically scan for new directories. They strictly reconcile the specific path declared in spec.source.path. As long as the old directory path still contained valid Kubernetes YAML, the controller saw no error. It simply reconciled the stale files at that specific path.
Follow-up 2. How does the app of apps pattern in Argo CD help prevent this type of path misalignment?
Answer: the app of apps pattern manages all GitOps application CRDs as declarative manifests inside Git itself. When a developer restructures a directory, they are forced to update the parent application manifest in the same commit, ensuring target paths and folder overlays are updated atomically.
Follow-up 3. Curveball. Both old and new overlay directories exist in Git, and 2 separate GitOps application CRDs are configured to sync them to the same cluster namespace. What happens?
Answer: a severe split-brain reconciliation loop occurs. Controller A syncs the old overlay, overriding live resources. Minutes later, Controller B syncs the new overlay, overriding them back. The cluster experiences constant API churn, pod restarts, and configuration flipping until one application CRD is deleted.
Pro tip for this production incident 18.
A green synced status in GitOps only proves that the controller reconciled something successfully. It does not prove it reconciled the right thing. When restructuring repository directories, remember that spec.source.path is a static string. Always delete obsolete overlay paths in the exact same pull request that introduces the new directory layout.
Production Incident 19. A monorepo commit updates 200 microservices simultaneously. The GitOps controller experiences a massive CPU spike, memory saturation, and reconciliation queue backlog. Production releases lag hours behind Git commits. How do you recover controller responsiveness?
Answer: my first priority is to relieve processing pressure on the GitOps control plane and prioritize critical production sync queues. I would inspect controller resource utilization, scale reconciliation worker processing, tune resync behavior, and shard workloads across controller instances. I will follow a structured response plan like Phase 1. Symptoms. 1. Git repository shows merged commits, but GitOps UI displays syncing queued for hundreds of apps. 2. GitOps controller pod metrics indicate 100% CPU utilization, and killed restarts. 3. Production cluster runs hours behind the declared desired state in Git. What these symptoms are telling us: the application microservices themselves are healthy, but the GitOps control plane is saturated, making reconciliation queue depth and processing capacity the immediate delivery bottleneck. Phase 2. Investigation. 1. Inspect GitOps controller pod logs. Queue depth metrics GitOps_len_work_queue and memory consumption. 2. Measure manifest generation latency across applications to determine if rendering complex Helm or customized templates for 200 apps is exhausting worker threads. 3. Check Git host API rate limiting metrics to see if excessive polling is amplifying request latency and queuing workers. What this investigation is revealing or leading to: the change burst generated concurrent reconciliation and templating workloads that exceeded the controller's processing capacity. Excessive polling acted as a secondary amplification factor. Phase 3. Root cause. 1. A single instance GitOps controller's processing capacity was overwhelmed by a 200-app monorepo change burst, creating a reconciliation worker backlog. Why this is the exact root cause, and why not others. Microservices and Kubernetes cluster APIs are healthy. The failure is strictly isolated to the GitOps control plane's inability to process state deltas at scale during burst change events. Phase 4. Immediate fix. 1. Temporarily increase CPU and memory limits on the GitOps controller pods and expand the worker thread pool size. 2. Pause automated sync on non-critical dev or staging applications to allocate processing capacity strictly to production releases. 3. Manually trigger syncs for high-priority production services to bypass the queued background reconciliation backlog. Expected outcome by doing the above steps: controller resource throttling clears, worker queues drain, and production applications reconcile to the desired Git commit. Phase 5. Long-term prevention. 1. Implement GitOps controller sharding, for example, Argo CD application controller sharding across multiple pod replicas. 2. Migrate from periodic Git polling to event-driven Git webhooks to eliminate unnecessary background request overhead. 3. Use path-based filters in application manifests, so commits only trigger reconciliation for services whose files actually changed. Expected outcome by doing the above steps: control plane resource consumption scales horizontally, preventing mass commits from choking release pipelines.
Follow-up 1. Why is periodic polling in GitOps dangerous for large monorepos?
Answer: if 200 applications poll Git every 3 minutes, the controller makes thousands of Git API calls per hour. During a monorepo commit, every app detects the change simultaneously and executes manifest templating at the exact same moment, causing massive CPU spikes and triggering Git host rate limits.
Follow-up 2. How does Argo CD sharding prevent memory exhaustion during large releases?
Answer: Argo CD controller sharding splits the total pool of application CRDs across multiple controller pod replicas based on cluster or app hash. Each replica processes only a fraction of the manifest generations and state checks, distributing CPU and RAM usage horizontally.
Follow up 3 curveball. You triggered a manual sync on a critical app via CLI during the queue backup, but it still sits in pending. Why?
Answer: manual CLI syncs are queued into the exact same work queue pool as automated syncs. If all worker threads are 100% utilized executing heavy manifest builds for other apps, the manual sync request must wait for an open worker thread unless dedicated break glass worker capacity is configured.
Pro tip for this production incident 19.
Control plane scalability is just as important as application scalability. When operating GitOps across hundreds of microservices, do not rely on a single controller instance or flat polling. Enable controller sharding, drive syncs via Git webhooks, and enforce path filtering so a commit to service A does not trigger manifest compilation for 199 unrelated services.
Production incident 20. A Kubernetes service and ingress are provisioned by Terraform, managed by a Helm chart, and reconciled by Argo CD. The tools continuously overwrite each other's fields and annotations. Cluster audit logs show non-stop API churn. How do you resolve ownership?
Answer: my first priority is to halt the competing reconciliation loop and establish a strict single-owner authority for the resource. I would freeze automated syncs, deliberately remove resource declarations from secondary tools, and migrate sole lifecycle authority to GitOps. I will follow a structured response plan like Phase 1. Symptoms. 1. Kubernetes API audit logs show non-stop update requests on the exact same resource every 30 seconds. 2. Argo CD flips continuously between synced and out-of-sync status. 3. CPU usage spikes on cluster control plane components and GitOps controllers due to constant reconciliation churn. What these symptoms are telling us: multiple automation control planes are managing the same resource fields without field-level coordination, causing a continuous overwrite fight. Phase 2. Investigation. 1. Inspect the resource's metadata.managed fields in Kubernetes to identify which managers, for example, Terraform, Helm, Argo CD, claim ownership of specific fields. 2. Compare the manifest values defined in Terraform code, Helm values.yaml, and GitOps Git repository. 3. Identify specific fields like dynamic annotations, labels, or status fields being mutated by one tool and reverted by another. What this investigation is revealing or leading to: Terraform created the base object, Helm injected dynamic chart labels, and Argo CD is enforcing a Git manifest that lacks those dynamic fields. All three tools are competing for field ownership. Phase 3. Root cause. 1. Architectural ownership collision caused by managing the same Kubernetes resource lifecycle across 3 independent automation systems: IaC, Package Manager, and GitOps Controller. Why this is the exact root cause and why not others? The resource itself is functional, but API audit logs confirm that each tool overwrites fields modified by the previous tool in a continuous loop. This isolates the failure to conflicting management boundaries. Phase 4. Immediate fix. 1. Pause automated sync on Argo CD and hold Terraform applies to freeze the active overwrite loop. 2. Update the Terraform code to explicitly remove the resource declaration and remove Helm chart tracking so future infrastructure runs do not attempt recreation. 3. Deliberately migrate sole ownership to GitOps by committing the full, authoritative manifest into Git and re-enabling Argo CD reconciliation. Expected outcome by doing the above steps: API churn stops instantly, resource state stabilizes, and GitOps becomes the single authoritative manager without risk of Terraform recreating the object. Phase 5. Long-term prevention. 1. Enforce strict architectural boundaries. Use Terraform strictly for cloud infrastructure and EKS cluster provisioning. Use GitOps strictly for in-cluster Kubernetes workloads. 2. Standardize on server side. Apply SSA in Kubernetes to enforce explicit field ownership management. 3. Ban the use of Helm CLI or Terraform Kubernetes, providers directly against clusters managed by GitOps controllers. Expected outcome by doing the above steps. Clear separation of concerns. Eliminates resource ownership conflicts across automation tools.
Follow-up 1. Why is executing Terraform state RM dangerous if you do not also remove the resource from the Terraform code?
Answer: because Terraform state RM only removes the resource from Terraform state. It does not remove the resource declaration from the Terraform configuration. Terraform will then see the resource declared in configuration, but absent from state, and will generally plan to create it again, unless another mechanism or configuration changes that behavior. Before transferring ownership to GitOps, I would first remove the resource declaration from Terraform configuration and verify the resulting plan so Terraform no longer considers itself responsible for that resource.
Follow-up 2. How does Kubernetes server-side apply SSA help prevent automation tools from overriding each other?
Answer: SSA tracks field ownership inside metadata.managed fields. When tool A tries to modify a field owned by tool B, the Kubernetes API server rejects the request with a conflict error instead of silently overriding it, forcing engineers to resolve ownership explicitly.
Follow-up 3. Curveball. You added ignore differences to Argo CD for a secret token field, but now a real security rotation in Git is not applying to the cluster. Why?
Answer: ignore differences tells Argo CD to completely ignore drift on that specific path. Because Argo CD ignores all differences for that JSON path, changes made in Git are treated as non-events and will never trigger an automated sync for that field until the rule is removed or a manual force sync is run.
Pro tip for this production incident 20.
Never attempt to transfer resource ownership simply by running Terraform state RM. State deletion without code deletion is a trap. Terraform will attempt to recreate the resource on its next execution. To safely transfer ownership to GitOps, pause reconciliation, delete the resource block from HCL, update Terraform state, and only then enable GitOps management.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, You do not need the entire master vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 21. A developer updates a GitOps application manifest, pointing target revision to a feature branch instead of an approved release. Unapproved experimental code deploys to production. How do you recover and secure release governance?
Answer. My first priority is to immediately revert the GitOps target revision to the last approved release reference and block unauthorized code execution. I would audit recent changes to GitOps application specifications, correct the target revision, and enforce immutable release governance policy. I will follow a structured response plan like Phase 1. Symptoms. 1. Unapproved feature code, experimental debug logs, or broken UI components appear in production. 2. Git commit history on main shows no recent deployment commits. 3. GitOps controller dashboard displays target revision, feature/login v2 for the production application. What these symptoms are telling us: production is healthy from a deployment mechanics standpoint, but release governance policy failed, allowing an unapproved, mutable Git branch to become the deployment source. Phase 2. Investigation. 1. Inspect the GitOps application CRD spec in Git and check commit history for spec.source.target revision changes. 2. Verify which git commit hash or tag is currently running in production versus approved release tags. 3. Check repository governance rules to determine how a PR modifying target revision to an unapproved branch bypassed release review. What this investigation is revealing or leading to: a configuration error or pull request oversight modified the GitOps application manifest, causing the controller to track an unapproved feature branch. Phase 3. Root cause. 1. Production release governance policy allowed a mutable, unapproved Git revision, a feature branch, to be defined as the deployment target source. Why this is the exact root cause, and why not others. The application containers built cleanly, and GitOps reconciled as instructed. The failure was entirely a release management governance failure in permitting an unvalidated Git target. Phase 4. Immediate fix. 1. Update spec.source.target revision in the GitOps application. Manifest back to the exact approved release tag or commit SHA. 2. Commit and push the fix directly to the control repository and trigger a hard sync in the GitOps controller. 3. Verify that live pods undergo a rolling update and confirm that production returns to approved application code. Expected outcome by doing the above steps. Unapproved feature code is evicted from the cluster, and production is restored to the validated release state. Phase 5. Long-term prevention. 1. Require production GitOps application targets to reference immutable release artifacts, such as signed Git tags, explicit commit SHAs, or validated SEM-ver release references. 2. Implement OPA, or contest policy checks in C, that fail any PR attempting to set target revision to a non-release branch pattern for production apps. 3. Enforce code owners and strict branch protection on all GitOps management repositories. Expected outcome by doing the above steps. Human error or unauthorized PRs cannot point production GitOps controllers to unvalidated branches.
Follow-up 1. Why is pointing a production GitOps application to a branch name like main considered a governance risk?
Answer. Pointing to a branch name means every commit merged to that branch instantly triggers a production deployment without an explicit release gate. It also makes auditing harder. Production should target explicit, immutable release references such as signed Git tags or exact commit SHAs.
Follow-up 2. How can OPA/gatekeeper enforce release target governance?
Answer. You write a REGO policy that inspects kind application manifests in CI or via admission webhooks. The policy asserts that if metadata.namespace is equal to production, spec.source.target revision must match an approved immutable pattern, for example, $v, $1 or more, $1 or more, $1 or more, $, or a 40-character commit SHA.
Follow-up 3. Curveball. A developer force pushes to main, overriding 10 approved commits with older code. How does GitOps react?
Answer. The GitOps controller sees that the git commit hash corresponding to main has changed to an older tree. It treats this as the new declared desired state and immediately executes a rolling update, rolling production back to that older code. This is why force push must be strictly disabled on production branches.
Pro tip for this production incident 21.
Release governance is a policy problem, not a YAML syntax problem. A manifest pointing to target revision feature/login v2 is 100% valid YAML, but it violates production safety. Never point production GitOps applications to moving branch names. Always enforce target revision constraints using policy engines like OPA or Kyverno to lock production targets to signed tags or explicit commit SHAs.
Production incident 22. A production release is deployed using tag v2.4.0. Days later, a developer overwrites the image tag in the registry. When production pods restart or scale out, nodes pull the overwritten image bytes, mutating production behavior without any GitOps manifest change. How do you recover?
Answer. My first priority is to isolate running workloads and lock down artifact identity, so production restarts cannot pull mutated content. I would trace the registry push history, identify the original digest, convert manifests to immutable digests, and enforce registry tag immutability. I will follow a structured response plan like Phase 1. Symptoms. 1. Git release tag v2.4.0 and GitOps application manifests remain 100% unchanged. 2. Production pods undergo restarts, node reschedules, or auto-scaling events and pull different image contents under the same tag name. 3. New, unreviewed code and runtime errors appear in an existing, previously validated production release. What these symptoms are telling us: this is a post-release artifact mutation. The release manifest was untouched, but the underlying container registry tag was overwritten, causing subsequent pod pulls to fetch modified bytes. Phase 2. Investigation. 1. Inspect container registry push timestamps and SHA-256 digest history for tag v2.4.0. 2. Compare the live pod container image digest image ID against the digest recorded in the original release pipeline build logs. 3. Check pod restart events and image pull policy configurations to verify which nodes fetch the mutated image digest. What this investigation is revealing or leading to: the container registry, allowed an overwrite of tag v2.4.0. Recent pod restarts or node scaling events caused nodes to fetch the new digest, proving a post-release tag mutation occurred. Phase 3. Root cause. 1. Lack of tag immutability enforcement in the container registry, combined with referencing mutable tag strings in manifests instead of pinning immutable digests. Why this is the exact root cause, and why not others. Manifests and Git history were untouched, ruling out a bad release promotion. The failure occurred entirely in the registry layer, because the tag string was allowed to point to a new SHA digest after release. Phase 4. Immediate fix. 1. Identify the exact original SHA-256 digest generated by the approved release build. 2. Update the production GitOps manifest to point directly to image at SHA-256 original digest and sync the application. 3. Enable strict tag immutability in the container registry settings immediately to block further overwrites. Expected outcome by doing the above steps. Production workloads are pinned to the original verified image digest, and the registry rejects any future attempt to overwrite published tags. Phase 5. Long-term prevention. 1. Configure release pipelines to resolve container images to immutable SHA-256 digests before writing GitOps release manifests. 2. Enforce registry-level, immutable repository policies across all production image namespaces. 3. Implement image signing and admission controllers, for example cosign or Kyverno, to reject unsigned or mutated digests at pod startup. Expected outcome by doing the above steps. Post-release artifact mutation becomes impossible because image references are mathematically pinned in version control.
Follow-up 1. How does this incident differ fundamentally from deploying the wrong artifact during a release pipeline run?
Answer. In a pipeline failure, the wrong artifact enters production during a release event. In a post-release tag mutation, an existing production release changes underneath you days or weeks later without any deployment activity, simply because a node rescheduled a pod or scaled out and pulled a mutated registry tag.
Follow-up 2. How can an engineer troubleshoot why only 30% of pods are running the mutated code, while 70% run the old code?
Answer. Nodes only pull an image when a pod is created, or if image pull policy always is set. The 70% of pods running old code were started before the tag was overwritten and retained local cached image layers. The 30% running mutated code were created after the registry tag overwrite via auto-scaling or pod restarts.
Follow-up 3. Curveball. You enabled tag immutability on your container registry, but now your pull request CI builds are failing globally. What happened?
Answer. The CI pipeline was reusing generic branch tags like :latest, :staging, or :PR12 across multiple commits. With tag immutability enabled, the registry rejects the second push to those tags. CI pipelines must be updated to publish unique immutable tags, for example, using git SHA or build IDs for every build.
Pro tip for this production incident 22.
Always ask yourself, how can production code change even though nobody modified the GitOps manifest? The answer is mutable artifact references. A string tag like v2.4.0 is just a pointer. In production GitOps, always pin your workloads to the immutable SHA-256 image digest image at SHA-256. That guarantees that node scale outs and pod restarts always pull the exact bytes that pass testing.
Production incident 23. An emergency fix is applied directly to a release branch and deployed to production. 2 weeks later, a routine deployment from the main branch overwrites production, reintroducing the original bug. How do you recover and fix the branching strategy?
Answer. My first priority is to immediately restore the hotfix to production and reconcile the code divergence between the release branch and main. I would trace the git commit graph, backport the emergency patch into the primary development line, and redeploy. I will follow a structured response plan like Phase 1. Symptoms. 1. A production bug that was successfully fixed 2 weeks ago suddenly reappears after a new feature release. 2. Git history on the main branch shows no record of the emergency hotfix commit. 3. The previous emergency deployment was executed from an isolated branch, for example release/v1.2.1, that was never merged back into main. What these symptoms are telling us: the hotfix was successful in isolation, but the branching workflow allowed the main release path to diverge, creating a regression during the next scheduled release. Phase 2. Investigation. 1. Compare the Git commit logs between main and the historical release branch, release/v1.2.1. 2. Identify the exact hotfix commit hash and verify if git merge base or git log --grep contains the change on main. 3. Inspect the team's release procedure to determine why the emergency patch was merged to the release branch without triggering a backport PR to main. What this investigation is revealing or leading to: the emergency fix existed exclusively on the legacy release branch. When the new release branch was cut from main, it lacked the fix, regressing production upon deployment. Phase 3. Root cause. 1. Process breakdown in release branch governance, where emergency hotfixes were permitted to merge into release branches without mandatory backporting to the primary main branch. Why this is the exact root cause, and why not others. The hotfix code itself was valid. The failure was entirely a Git lifecycle governance error that allowed code paths to diverge silently. Phase 4. Immediate fix. 1. Cherry pick or apply the emergency hotfix commit into main and open an urgent pull request. 2. Cut a new release tag from main containing both the new features and the backported hotfix. 3. Deploy the unified release tag to production and confirm the bug is resolved without rolling back new features. Expected outcome by doing the above steps: production is stabilized with both the new release features and the critical hotfix unified in a single release artifact. Phase 5. Long-term prevention. 1. Automate backport PR creation, for example GitHub backport action, whenever a hotfix PR merges into a release branch. 2. Transition toward trunk-based development with feature flags to reduce long-lived release branch complexity. 3. Implement CI branch divergence checks that block new release creation if unmerged commits exist on active release branches. Expected outcome by doing the above steps: code paths cannot diverge silently, ensuring hotfixes are permanently preserved in the primary development branch.
Follow-up 1. What is the main difference between Git cherry pick and Git merge when backporting a hotfix?
Answer: Git cherry pick applies the specific changes from a single commit onto your current branch with a new commit hash. Git merge combines the entire commit history of two branches. For isolated hotfixes on refactored branches, cherry picking is cleaner because it avoids pulling unwanted release branch noise into main.
Follow-up 2. How does trunk-based development eliminate the risk of hotfix branch divergence?
Answer: in trunk-based development, all engineers commit to main daily using feature flags. When production breaks, the fix is merged directly into main first and deployed. Because there are no long-lived release branches, code paths never diverge and backporting becomes unnecessary.
Follow-up 3. Curveball. You attempt to cherry pick the hotfix into main, but it fails with massive merge conflicts because main was heavily refactored. What do?
Answer: do not force a complex Git merge resolve under incident pressure. Instead, write a clean implementation of the fix tailored to main's new refactored architecture, pass full unit and integration test suites, and merge it via standard PR. The goal is logical equivalence of the fix, not forcing old code lines into refactored architecture.
Pro tip for this production incident 23.
An unbackported hotfix is simply a delayed production outage. Wherever an emergency fix is created, whether on a release branch or a dedicated hotfix branch, it must be propagated back to the primary development branch immediately and automatically. Automate backport PR creation so human memory is removed from release governance.
Production incident 24. Production manifests deploy successfully via GitOps, but pods fail at runtime with database authentication errors. Investigation reveals a customized overlay copied a staging secret vault reference into production. How do you remediate and prevent secret cross-contamination?
Answer: my first priority is to correct the production secret reference in Git and enforce IAM cross-environment isolation. I would inspect secret provider resources, correct overlay references, sync GitOps, and audit staging database connections. I will follow a structured response plan like Phase 1. Symptoms. 1. GitOps controller shows synced and healthy for the production application. 2. Production application pods start cleanly, but throw HTTP 5.0.0 runtime errors connecting to external services. 3. Application logs show database access denied errors using a username containing -staging. What these symptoms are telling us: deployment mechanics succeeded, but the application is consuming credentials belonging to another environment due to a manifest configuration error. Phase 2. Investigation. 1. Inspect the production secret store manifest in the production customize overlay folder. 2. Compare base configuration manifests against production overlay patches to identify overridden staging key vault references. 3. Audit staging database and secret manager access logs to determine if production pods attempted queries against staging resources. What this investigation is revealing or leading to: a copy-paste error in the production customize overlay left the secret reference pointing to the staging key vault secret name, KV staging DB pass. Phase 3. Root cause. 1. Lack of automated reference validation in GitOps overlays, combined with permissive IAM policies that allowed production workloads to read staging secret vaults. Why this is the exact root cause, and why not others. The GitOps controller in Kubernetes API rendered valid YAML. The failure was a secret reference string misconfiguration inside the environment overlay. Phase 4. Immediate fix. 1. Update the production overlay manifest to reference the exact production vault key name and sync GitOps. 2. Refresh the application secret consumption path, restarting pods if credentials are injected via environment variables, or verifying secret volume remounts. 3. Verify clean authentication to the production database and rotate staging database credentials immediately as a security precaution. Expected outcome by doing the above steps: production pods authenticate to the production database, and staging environments are isolated from potential credential exposure. Phase 5. Long-term prevention. 1. Enforce strict cloud IAM role boundaries, so production pods physically lack authorization to read staging key vaults. 2. Implement CI policy checks, for example OPA, or confdest that scan production manifests, and reject any file containing forbidden strings like *staging-star or staging vault ARNs. 3. Restructure secret store providers so environment boundaries are enforced at the IAM layer rather than relying on correct string naming in manifests. Expected outcome by doing the above steps: manifest configuration errors cannot pull staging secrets because cross-environment access is blocked at the IAM boundary.
Follow-up 1. Why did not Argo CD or Flux detect that the secret reference belonged to staging?
Answer: GitOps controllers only validate Kubernetes syntax and API schema correctness. They have no domain awareness of your business logic or key vault naming conventions. As long as the secret spec is valid YAML, GitOps considers the manifest valid.
Follow-up 2. How do environment-scoped IAM roles prevent this issue, even if the manifest is wrong?
Answer: using URSA in EKS or workload identity in GKE, you assign the production pod service account an IAM role that only has permissions to read production secrets. Even if a bad manifest points to a staging secret, the Cloud API rejects the request with an access denied error.
Follow-up 3. Curveball. Production pods successfully authenticated to the staging database and wrote production customer data there for 2 hours before detection. What is your recovery plan?
Answer: first, isolate the staging database from further production writes while preserving the affected data and audit evidence. Then identify exactly which production transactions were written to staging. Determine whether those records can be safely reconciled with production without creating duplicates or integrity issues, and involve the appropriate data owners before any migration or cleanup. After the data impact is understood, Restore the staging environment to a known good state if required. Rotate the exposed staging credentials, and verify that production can access only production resources.
Pro tip for this production incident 24.
Never rely solely on YAML linting to catch configuration bugs. A valid Kubernetes manifest can be a disaster if it points to the wrong environment's credentials. Always enforce cross-environment isolation at the cloud IAM layer. If your production Kubernetes pods lack IAM permissions to read staging key vaults, a copy-paste error in Customize fails safely with an access denied error instead of corrupting staging data.
Production incident 25. A platform engineer modifies a shared base configuration file in a monorepo. The GitOps controller detects the change in the base and simultaneously triggers a rolling restart across 300 microservices, exhausting cluster control plane resources. How do you halt and recover?
Answer: my first priority is to limit the blast radius by pausing automated sync globally across non-critical applications and letting active cluster operations settle. I would freeze reconciliation, stabilize cluster API servers, and resume in controlled waves. I will follow a structured response plan like Phase 1. Symptoms 1. Cluster monitoring reports massive pod churn, with thousands of pods simultaneously in terminating or container creating states. 2. Kubernetes API server latency spikes, and cloud load balancer provisioning quotas are exhausted. 3. GitOps controller reports hundreds of applications reconciling concurrently following a single commit to a shared base folder. What these symptoms are telling us: a single commit modified a globally inherited configuration base, triggering an unbatched mass deployment across all dependent applications. Phase 2. Investigation. 1. Inspect recent Git commits to locate the exact modified file in shared base folders, for example apps/base/customization.yaml or shared Helm global values. 2. Review GitOps controller event logs to count how many applications detected an active diff against their live cluster state. 3. Check cloud provider rate limits and Kubernetes control plane metrics to identify the primary bottleneck causing pod deployment stalls. What this investigation is revealing or leading to: a one-line change to a shared base file, cascaded down to 300 microservices. The failure is a blast radius control flaw in repository layout and GitOps deployment orchestration. Phase 3. Root cause. 1. Tightly coupled repository design where 300 microservices inherited a shared base file without GitOps sync waves, application grouping, or staged promotion controls. Why this is the exact root cause, and why not others. The shared base change is the single common parent commit across all 300 app diffs. The infrastructure collapsed under the simultaneous, unbatched reconciliation load. Phase 4. Immediate fix. 1. Immediately pause automated sync globally on the GitOps controller to stop new reconciliations from initiating. 2. Allow currently terminating pods and in-flight cloud API calls to settle until Kubernetes control plane latency normalizes. 3. Resume applications in controlled batch groups using GitOps sync waves and staged sync windows until all 300 services complete reconciliation safely. Expected outcome by doing the above steps: control plane pressure drops, cloud API quotas recover, and microservices reconcile in orderly, controlled waves. Phase 5. Long-term prevention. 1. Implement GitOps sync waves argocd.argoproj.io/sync-wave, combined with application grouping and staged promotion windows. 2. Decouple global base configurations and require explicit versioning or opt-in overrides for shared platform defaults. 3. Enforce pull request impact checks that calculate and display how many downstream applications will be touched by a base folder change. Expected outcome by doing the above steps: shared platform changes roll out progressively in controlled phases without triggering global cluster churn.
Follow-up 1. How do GitOps sync waves and application grouping prevent 300 services from restarting simultaneously?
Answer: they allow dependent applications to be deliberately organized into controlled deployment phases, instead of allowing every application affected by the shared change to reconcile at once. For example, Wave 1 could contain core infrastructure, Wave 2 backend services, and Wave 3 front-end applications. Argo CD can then process the configured waves according to their ordering and health conditions, reducing the blast radius and allowing the team to validate each group before moving to the next.
Follow-up 2. How can CI pull request checks prevent accidental mass deployments before merging?
Answer: a CI script executes customized build or Helm template against every application directory in the monorepo for both main and the PR branch. If the PR diff modifies manifests in more than X number of apps, for example, greater than 10 apps, the PR requires explicit approval from a senior release architect.
Follow-up 3. Curveball. You paused GitOps auto-sync to stop the mass deployment, but 150 pods are now stuck in terminating state because cloud load balancers are rate-limiting target deregistration. How do you recover?
Answer: do not force delete pods force grace period equals 0. Force deletion removes the pod object from K8s, but leaves orphan target registrations in the cloud load balancer, routing traffic to dead IPs. Request a temporary cloud API rate limit quota increase. Allow the ingress controller to process deregistration sequentially, and monitor target group health before proceeding.
Pro tip for this production incident 25.
In a GitOps monorepo, a one-line change to a shared base file is a 300 service production release. Never allow unbatched inheritance on global defaults. Always combine shared base configurations with GitOps sync waves, staged promotion windows, and CI pull request impact analysis, so you know exactly how many services will restart before you merge.
Category 2 Summary and Key Takeaways. What we mastered in GitOps.
Core engineering principles proven in Category 2. 1. Declarative state sovereignty. Cluster state is a projection of Git. Manual cluster edits will be overwritten by reconciliation loops. 2. Artifact mutation defense. Always deploy by immutable SH, a 256 image digests, not mutable tags that can change post-release. 3. Release governance and backports. Emergency hotfixes must be propagated back to primary development lines immediately and automatically. 4. Blast radius boundaries. Isolate secrets at the IAM layer and use GitOps sync waves to prevent shared config change churn. Mastering declarative release mechanics is essential for cloud-native governance.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions, and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire master vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Focus shift from Category 1 CI and CD and Category 2 GitOps to Category 3 IaC.
In Category 2, we mastered Kubernetes state reconciliation and release governance, proving how application manifests are synchronized into live clusters. But application workloads cannot run on thin air. They depend on cloud networks, managed databases, security groups, IAM roles, and storage buckets. In Category 3, we shift our focus down the stack to infrastructure as code IaC. Here, the blast radius of a mistake is not just a failing pod. It is an accidentally deleted production database, a state split brain, or an unannounced provider upgrade that destroys VPC routing. Welcome to the high-stakes world of cloud infrastructure automation.
Category 3 IaC and infrastructure automation.
Infrastructure as code tools like Terraform, OpenTofu, and Pulumi allow platform teams to manage cloud environments declaratively. However, managing cloud infrastructure through code introduces uniquely dangerous failure modes, destructive replacement plans, state file lock deadlocks, accumulative drift, and circular dependency loops. Category 3 equips you to diagnose, isolate, and recover from critical outages when IaC state management, provider updates, and module dependencies fail in production.
Category 3 Incidents. Incidents 26 to 37.
Here are the infrastructure as code production incidents we will cover in this category. Incident 26, Terraform plan accidentally replaces a production resource. Incident 27, Terraform state split brain. Incident 28, Terraform provider upgrade changes production behavior. Incident 29, shared Terraform module introduces a production regression. Incident 30, infrastructure drift accumulates until deployment failure. Incident 31, failed IaC apply leaves a half-built environment. Incident 32, IaC bootstrap dependency loop. Incident 33, Terraform state lock blocks an emergency change. Incident 34, IaC dependency ordering causes a production race. Incident 35, Terraform rollback cannot safely undo the infrastructure change. Incident 36. Resource removed from code gets destroyed unexpectedly. Incident 37. Shared network or IAM module causes cross-environment blast radius. Let's dive into Production Incident 26.
Production Incident 26. An engineer changes a single attribute in a Terraform file. During execution, Terraform forces the recreation of a production database, destroying data and causing a major outage. How do you recover and prevent destructive replacements?
Answer. My first priority is to stabilize the database outage, restore data from point-in-time backups, and prevent further destructive execution. I would inspect the plan execution log to identify the immutable attribute that triggered the force replacement symbol, protect stateful resources, and reconcile state. I will follow a structured response plan like Phase 1. Symptoms. 1. Severe production database outage occurs immediately following a pipeline run. 2. Cloud console logs confirm the original database instance was deleted, and a new empty instance was created with a different resource ID. 3. Terraform execution log shows a // destroy and recreate action indicator next to the database resource address. What these symptoms are telling us: Terraform executed a force replacement plan rather than an in-place update, treating the stateful database as ephemeral infrastructure. Phase 2. Investigation. 1. Inspect the Terraform plan diff output and schema documentation for the specific resource attribute modified in the pull request. 2. Identify the exact immutable API attribute, for example, changing DB instance identifier, KMS key, or engine version that triggered the forced recreation. 3. Review the pipeline approval gate to determine why a plan containing a destructive replacement symbol /+ was allowed to merge. What this investigation is revealing or leading to: a developer changed an immutable cloud attribute in code. Terraform's provider schema dictated that changing this value requires resource recreation, which was approved without detecting the replacement symbol. Phase 3. Root cause. 1. Modification of an immutable resource attribute that forced a recreation plan /+ combined with an absence of prevent _ destroy lifecycle blocks and automated pipelines that lack destructive plan validation rules. Why this is the exact root cause and why not others. The provider schema required recreation because an immutable attribute changed. The absence of prevent _ destroy and plan check policies permitted that destructive replacement to execute. Phase 4. Immediate fix. 1. Restore the production database from the latest automated snapshot or point-in-time recovery PITR backup. 2. Add a lifecycle prevent _ destroy equals true block to the Terraform code for the stateful database resource. 3. Import the newly restored cloud database instance back into the Terraform state file using Terraform import to align IaC tracking. Expected outcome by doing the above steps: data is recovered, state tracking is reconciled to the restored instance, and future destruction commands on this resource are explicitly blocked. Phase 5. Long-term prevention. 1. Mandate prevent _ destroy lifecycle rules on all production databases, storage buckets, and stateful cloud infrastructure. 2. Implement CI plan checking tools, for example, confdest or OPA, that scan Terraform plan JSON outputs and fail any PR containing a /+ replacement symbol on stateful resources. 3. Require explicit two-person approval for any Terraform apply that modifies production infrastructure. Expected outcome by doing the above steps: immutable attribute changes cannot accidentally trigger resource recreation on stateful production assets.
Follow-up 1. What is the exact difference between tilde and /+ in a Terraform plan output?
Answer. Tilde indicates an in-place update, meaning Terraform can update the attribute via a cloud API patch call without destroying the resource. /+ indicates a forced replacement, where Terraform must delete the existing resource and create a new one, because the cloud provider API does not allow that attribute to be mutated on an existing object.
Follow-up 2. How does lifecycle prevent _ destroy equals true behave if someone attempts to change an immutable attribute?
Answer: if an attribute change forces a replacement, Terraform detects that the proposed operation would destroy the protected resource and rejects the plan because of the prevent_destroy lifecycle rule. The apply cannot proceed until the configuration or lifecycle protection is deliberately changed.
Follow-up 3. Curveball. You added prevent_destroy equals true, but you genuinely need to replace the database during a planned migration. How do you proceed safely?
Answer: you do not simply delete the lifecycle block and run apply. You provision the new database alongside the old one as a separate resource, replicate data cleanly, cut traffic over to the new instance, update application state, and only after validation do you remove the prevent_destroy block to decommission the old instance.
Pro tip for this production incident 26.
Never run Terraform apply without carefully inspecting the plan output for the // symbol. An in-place update tilde is usually safe, but a // on a database, S3 bucket, or persistent disk means resource replacement and carries a potentially destructive data loss risk. Protect every stateful production resource with lifecycle prevent_destroy equals true and enforce automated CI policy checks to catch replacement symbols before PRs merge.
Production incident 27. 2 separate CI pipelines execute against the same production cloud infrastructure using different remote state files. The pipelines continuously overwrite and undo each other's changes. How do you resolve state split brain?
Answer: my first priority is to freeze pipeline execution and consolidate infrastructure management under a single, authoritative remote state backend key. I would audit cloud trail logs, lock down state backend access, reconcile drift using state refresh and imports, and eliminate duplicate pipeline paths. I will follow a structured response plan like Phase 1. Symptoms. 1. Production cloud infrastructure configuration flops every time an automated pipeline runs. 2. Pipeline execution logs report resources as already exists when attempting to create objects. 3. Terraform plan output shows massive, unexpected drift on completely clean, unmodified code commits. What these symptoms are telling us: multiple state backends are attempting to manage the same cloud resources independently, creating a state split brain condition where neither state file reflects reality. Phase 2. Investigation. 1. Compare the backend configuration block and backend key settings across all pipeline repositories and execution jobs. 2. Inspect the state file lineage and serial numbers in both remote state stores. 3. Query CloudTrail audit logs to identify which IAM identities and pipeline runners are executing API write calls against the affected cloud resources. What this investigation is revealing or leading to: Pipeline A is writing state to prod/app.tf state, while Pipeline B is writing state to prod/infrastructure.tf state. Both state files contain resource definitions pointing to the exact same AWS resource IDs. Phase 3. Root cause. 1. 2 independent pipelines and state files were configured to claim management ownership over overlapping cloud infrastructure resources. Why this is the exact root cause and why not others? Both pipelines had active state locks on their respective state files. The failure occurred because the state domains overlapped, not because state locking was missing. Phase 4. Immediate fix. 1. Immediately pause all automated CI and CD execution jobs modifying that environment. 2. Select one remote state file as authoritative. On the secondary state, use Terraform state RM to remove duplicate resource references without deleting the live cloud resources. Then import those resources into the authoritative state using Terraform import and verify the resulting plan before resuming automated execution. 3. Consolidate all pipeline jobs to point strictly to the single authoritative backend state key. Expected outcome by doing the above steps: dual state execution stops, state tracking is unified, and infrastructure configuration stabilizes. Phase 5. Long-term prevention. 1. Enforce a single authoritative state backend key per infrastructure domain. 2. Use native S3 state locking use_lock file equals true for S3 backends to prevent concurrent execution against the same state key. 3. Isolate environments into distinct state files with clear ownership boundaries enforced by CI linter checks. Expected outcome by doing the above steps. Concurrent pipeline runs against the same state key are blocked at the lock layer, and duplicate state key definitions are rejected at build time.
Follow-up 1. Why does not state locking alone prevent a state split brain incident?
Answer. State locking prevents two concurrent processes from writing to the exact same state file key simultaneously. However, if pipeline A writes to app.tf state and pipeline B writes to infra.tf state, both pipelines acquire valid locks on their own respective state files. Locking cannot stop two separate state files from claiming ownership over the same cloud resource.
Follow-up 2. What are Terraform state lineage and serial attributes used for?
Answer. Lineage is a unique UUID assigned when a state file is created. If two state files have different lineages, they represent completely different infrastructure histories. Serial is an integer that increments on every state modification. Terraform uses serial numbers to detect out-of-order state overwrites and prevent stale state writes.
Follow-up 3. Curveball. Two state files exist for the same production VPC, and both contain unique resources that cannot be deleted. How do you merge them into a single state file safely?
Answer. You do not merge the files manually. You pick state file A as primary. On state file B, you run Terraform state RM on its resources to remove them from B's tracking without deleting live cloud objects. Then on state file A, you run Terraform import for those resources, pulling them cleanly into state file A's tracking.
Pro tip for this production incident 27.
State locking prevents concurrent writes to the same state file, but it cannot stop two different state files from managing the same cloud resource. Always isolate state domains. Pair S3 backends with native S3 locking use_lock file equals true, and enforce single state ownership per cloud environment.
Production incident 28. A Terraform provider dependency is unexpectedly upgraded during a pipeline run. Default resource behavior changes, introducing unexpected security group modifications across production. How do you remediate and control provider lifecycles?
Answer. My first priority is to lock the provider version back to the known good baseline and prevent automated provider upgrades from mutating production. I would inspect provider dependency blocks, review release notes for breaking defaults, pin provider constraints, and reapply. I will follow a structured response plan like Phase 1. Symptoms. 1. Terraform plan output displays dozens of unexpected resource modifications without any changes made to application IaC code. 2. Production pipeline runs fail or modify security rules after an automatic provider initialization step. 3. Execution logs show initializing provider plugins, pulled a new major or minor provider version. What these symptoms are telling us, the application code is identical, but the underlying provider plugin mutated its default behavior or API schema during auto-initialization. Phase 2. Investigation. 1. Inspect the required _providers block in the Terraform code and check .terraform.lock.hcl in version control. 2. Compare the provider version downloaded during the failing run with the version used in previous successful pipeline runs. 3. Review provider change logs and release notes to identify breaking changes in resource defaults, for example, changes to default egress rules or tag formatting. What this investigation is revealing or leading to. The code used a loose version constraint like version equals greater than or equal to 4.0 without a committed lock file, or ran Terraform init-upgrade. Terraform initialized and pulled version 5.0.0, which changed default resource attributes. Phase 3. Root cause. 1. A loose provider version constraint, combined with a missing or uncommitted .terraform.lock.hcl lock file, or running Terraform init-upgrade, allowed a new provider version with changed defaults into the production execution path. Why this is the exact root cause, and why not others. Reverting the provider plugin version instantly removes the unexpected plan diffs, proving the issue was driven by upstream provider plugin default changes. Phase 4. Immediate fix. 1. Explicitly pin the provider version in required_providers to the exact known good version for example version equals 4.67.0. 2. Update and commit the .terraform.lock.hcl file to Git using Terraform init-upgrade equals false. 3. Rerun Terraform plan to verify that unexpected resource modifications disappear and reapply safely. Expected outcome by doing the above steps. The provider plugin is locked to a known good release, removing unexpected attribute diffs and restoring pipeline determinism. Phase 5. Long-term prevention. 1. Enforce strict provider version constraints. Commit .terraform.lock.hcl to Git and mandate controlled dependency upgrade workflows. 2. Require that .terraform.lock.hcl is validated by CI pre-commit hooks. 3. Establish a scheduled provider upgrade workflow that tests new provider versions in isolated non-production environments before upgrading production. Expected outcome by doing the above steps. Provider upgrades become deliberate, tested platform changes rather than unexpected runtime dependencies.
Follow-up 1. Why is committing the .terraform.lock.hcl file to Git essential for team and CI pipeline determinism?
Answer. The lock file records the exact provider version and cryptographic checksums for every provider plugin used. Committing it guarantees that every developer machine and CI runner initializes the exact same provider binaries, preventing silent provider drift across environments.
Follow-up 2. What is the difference between required_version and required_providers in Terraform?
Answer. Required_version specifies the allowed versions of the Terraform CLI binary itself. For example, Terraform 1.5.0. Required_providers specifies the allowed versions of external provider plugins like AWS, Azure, or Kubernetes providers that translate Terraform code into cloud API calls.
Follow-up 3. Curveball. You pinned your root module provider version to 4.67.0, but an imported remote module contains version equals greater than or equal to 5.0. What happens?
Answer. Terraform initialization fails with a provider version. Constraint conflict error. Terraform's dependency solver attempts to find a provider version that satisfies all modules. Since 4.67.0 and is greater than or equal to 5.0 are mutually exclusive. Initialization halts protecting the deployment.
Pro tip for this production incident 28.
Production provider safety requires version constraints, committed lock files, and controlled upgrade workflows. Never allow untested provider updates into production pipelines. Always commit .terraform.lock.hcl to Git so every build initializes identical provider binaries.
Production incident 29. A platform team updates a shared VPC Terraform module published under a mutable Git tag v1. Dozens of production pipelines pull the update during clean CI runs, dropping network routes across environments. How do you recover?
Answer. My first priority is to lock the shared module reference to an immutable version and restore network route availability. I would trace module sources, revert the breaking change in the module repository, pin module references to immutable semver tags, and reapply. I will follow a structured response plan like Phase 1. Symptoms. 1. Multiple unrelated production environments experience network route or security group regressions simultaneously following routine pipeline runs. 2. Application teams made no changes to their environment code, but Terraform plan shows modifications inherited from remote module sources. 3. Network traffic fails across subnets due to missing route table entries. What these symptoms are telling us: the failure is originating from an external shared module dependency that introduced a breaking change into consuming pipelines. Phase 2. Investigation. 1. Inspect the source parameter in main.tf files across affected environments. For example, source equals gitref equals v1. 2. Review recent commit history in the shared module repository to identify breaking default parameter modifications. 3. Verify that CI pipelines executing in clean runner workspaces or running Terraform init-upgrade resolved the mutable v1 reference to the newly pushed breaking commit. What this investigation is revealing or leading to: the shared module repository updated tag v1 with a breaking route table modification. Because consuming pipelines initialized in clean workspaces, they fetched the newly published commit for tag v1. Phase 3. Root cause. 1. Mutable module source tagging ref equals v1 or ref equals main, allowing untested platform module updates to automatically propagate into production pipelines without explicit consumer opt-in. Why this is the exact root cause and why not others. Consuming environment code was unchanged. Reverting the shared module tag or pinning to an immutable commit instantly restores valid route declarations across all environments. Phase 4. Immediate fix. 1. Revert the breaking commit in the shared module repository or publish a corrected immutable tag, for example, v1.0.1. 2. Update consuming production environment manifest to reference an explicit release tag or version ref equals v1.0.1, or, where strict immutability is required, an exact commit SHA. 3. Rerun Terraform apply across affected environments to restore missing network routes and verify connectivity. Expected outcome: by doing the above steps, network routes are restored and module references are pinned to prevent automatic downstream mutations. Phase 5. Long-term prevention. 1. Enforce explicit release versions ref equals v1.2.3. Commit SHAs or private module registry versions for shared IaC modules, with tag immutability enforced where supported. 2. Ban the use of mutable Git branch names or major tags ref equals v1 or ref equals main in module source URLs for production code. 3. Mandate automated integration testing of shared modules in a sandbox environment before tagging new releases. Expected outcome: by doing the above steps, shared module improvements become opt-in upgrades for application teams rather than unannounced production changes.
Follow-up 1. Why should shared Terraform modules be hosted in dedicated version, controlled repositories, or private registries?
Answer: hosting modules in dedicated repositories or private module registries allows platform teams to apply strict semantic versioning, release tags, and automated testing independently of application code. It ensures that changes to shared infrastructure patterns undergo formal code review and sandbox testing before release.
Follow-up 2. How do you safely deprecate or modify an input variable in a shared Terraform module?
Answer: you follow a multi-release deprecation path. In version 1.1, you mark the old variable as deprecated, add the new variable as optional with a default, and support both in local logic. In version 2.0, you remove the old variable. This gives consuming teams time to migrate without breaking builds.
Follow-up 3. Curveball. You pinned your root module to ref equals v1.0.0, but that module internally fetches a nested remote module using ref equals main. How do you stop the cascade?
Answer: nested remote modules with mutable refs violate isolation. You must update the root module to pin the nested module source URL to an explicit immutable tag or commit SHA. Release a new version of the root module and update your production code to reference that new version.
Pro tip for this production incident 29.
Treat shared Terraform modules as production dependencies, not unversion helper scripts. Pin production consumers to an explicit release version or exact commit SHA, and enforce tag immutability where your Git platform supports it. A change to a shared network or IAM module should be a deliberate, opt-in upgrade for consuming teams, never an automated surprise during a routine run.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 30. Engineers make manual Cloud Console edits during incidents over 6 months without updating IaC. The next scheduled Terraform deployment attempts to revert those manual changes, threatening to destroy production fixes. How do you reconcile drift safely?
Answer: my first priority is to prevent Terraform from destroying live operational fixes while bringing the IaC code back into alignment with reality. I would run drift detection in refresh-only mode, Audit manual console changes via Cloud Trail, backport live configurations into code, and resync. I will follow a structured response plan like Phase 1, Symptoms. 1. Terraform plan output displays dozens of unexpected resource modifications, attempting to delete or overwrite live cloud configurations. 2. On-call engineers report that running Terraform apply will break live production security rules or routing fixes made months ago. 3. IaC repository code has not been deployed in months due to fear of breaking live infrastructure. What these symptoms are telling us: massive operational drift has accumulated between the declarative code in Git and the actual live cloud infrastructure state. Phase 2. Investigation. 1. Execute Terraform plan -refresh only to generate a plan previewing state updates needed to match live cloud resources without generating resource modification plans. 2. Query CloudTrail or audit logs to identify out-of-band manual console edits, timestamps, and the operational intent behind those changes. 3. Compare the refresh-only state diff against the Git repository code to isolate every undocumented manual modification. What this investigation is revealing or leading to: manual console edits added new security group rules and updated instance types out of band. The code is outdated, and applying it directly would destroy critical live fixes. Phase 3. Root cause. 1. Unreconciled operational drift caused by bypassing IaC procedures during emergency hotfixes, combined with a lack of automated scheduled drift detection in CI. Why this is the exact root cause, and why not others. The cloud infrastructure works correctly. The problem is that the IaC code in Git no longer represents the live environment state. Phase 4. Immediate fix. 1. Run Terraform plan -refresh only to review state updates previewed by Terraform. 2. Execute Terraform apply -refresh only to commit the accepted state updates to the state backend. 3. Backport the live manual cloud changes into the Terraform HCL code files until a normal Terraform plan produces a clean zero diff output. Expected outcome by doing the above steps: code and live state are fully reconciled without destroying operational fixes or causing downtime. Phase 5. Long-term prevention. 1. Schedule automated daily drift detection jobs Terraform plan -detailed -exit code in C to alert on manual edits within 24 hours. 2. Revoke manual write permissions in production cloud consoles using strict IAM policies, requiring all changes to go through IaCPRs. 3. Establish an emergency break glass IaCPR workflow for rapid incident hotfixes. Expected outcome by doing the above steps: manual console edits are prevented, and any break glass drift is detected and reconciled immediately.
Follow-up 1. What is the exact difference between standalone Terraform refresh and Terraform plan -refresh only?
Answer: standalone Terraform refresh is deprecated in modern Terraform because it automatically overwrote state without showing a plan preview. Terraform plan -refresh only creates a safe execution plan showing exactly what state drift was detected, allowing engineers to review and explicitly run Terraform apply -refresh only to commit the state update.
Follow-up 2. How does -detailed -exit code work in automated CI drift detection pipelines?
Answer: when Terraform plan -detailed -exit code runs, it returns an exit code of 0 if there are no changes, 1 if an error occurred, and 2 if infrastructure drift was detected. CI pipelines check for exit code 2 and automatically trigger an alert or open an incident ticket for the platform team.
Follow-up 3. Curveball. Drift detection flags a manual change, but the engineer who made it did not document why. Applying code will delete the change. What do you do?
Answer: do not run apply. Query CloudTrail logs to identify the exact timestamp and incident ticket associated with the edit. Contact the on-call engineer or team lead to establish the operational context. Backport the manual change into code first, test it, and only then apply.
Pro tip for this production incident 30.
Operational drift is silent technical debt. If engineers make manual edits in the cloud console, your IaC is no longer the source of truth. Run daily automated Terraform plan drift scans in C. So you catch manual edits within 24 hours, rather than discovering them during a high-stakes production release.
Production Incident 31. A 40-resource Terraform deployment fails halfway through due to a cloud API quota limit. Half the resources are created, while dependent resources fail. The environment is left in an inconsistent state. How do you recover?
Answer: my first priority is to resolve the root API blocker and allow Terraform to complete the remaining state reconciliation cleanly. I would inspect state tracking to verify created resources, increase cloud quotas, and rerun apply against the existing state backend. I will follow a structured response plan like Phase 1. Symptoms 1. Terraform deployment pipeline terminates with an error midway through execution. 2. Cloud console confirms VPCs, subnets, and databases were created, but dependent application clusters, or DNS records, are missing. 3. Subsequent pipeline runs fail with resource creation, or dependency resolution errors. What these symptoms are telling us: an imperative execution failure mid-apply left the environment partially provisioned, but Terraform successfully tracked the created resources in state. Phase 2. Investigation. 1. Inspect the Terraform apply execution log to locate the exact resource address where the failure occurred. 2. Check the remote state file terraform.tf-state to verify which created resources were successfully saved to state before the failure. 3. Identify the cloud API error, for example hitting VPC quota limits or missing IAM permissions that blocked the execution. What this investigation is revealing or leading to: resources 1 through 20 were created and saved in state. Resource 21 failed due to a regional subnet quota. The state backend accurately reflects the half-built environment. Phase 3. Root cause. 1. Cloud provider resource quota exhaustion during apply execution, combined with a lack of pre-flight quota validation in CI pipelines. Why this is the exact root cause, and why not others? The created resources are functional and present in state. The failure was driven strictly by reaching an external cloud provider limit during execution. Phase 4. Immediate fix. 1. Request an immediate cloud provider resource quota increase or modify code to utilize available subnet capacity. 2. Rerun Terraform apply against the existing remote state file without destroying created resources. 3. Confirm that Terraform recognizes already created resources in state and completes only the remaining missing resources. Expected outcome by doing the above steps: Terraform picks up execution from the state checkpoint, finishing the remaining resources without recreating existing infrastructure. Phase 5. Long-term prevention. 1. Add automated pre-flight quota and permission validation checks to CI pipelines before executing Terraform apply. 2. Structure monolithic IaC configurations into smaller, independent stack layers, for example, network stack, database stack, app stack. 3. Ensure state backends use real-time state locking and immediate persistence after each resource creation. Expected outcome by doing the above steps: pre-flight checks catch quota limits before execution, and modular stacks limit the blast radius of partial apply failures.
Follow-up 1. Why does not Terraform automatically roll back and delete created resources when an apply fails midway?
Answer: Terraform is state reconciliation driven, not transaction driven. Cloud APIs do not support multi-resource atomic transactions. Automatically deleting created resources could destroy live infrastructure or dependencies created earlier in the apply. Instead, Terraform saves state incrementally so you can fix the issue and resume.
Follow-up 2. How can Terraform apply -target be used safely during recovery of a half-built environment?
Answer: -target allows you to isolate and apply a specific resource or stack layer first to unblock execution. However, it should only be used as an emergency recovery tool, because targeting ignores targeted dependency diffs. Once unblocked, You must run a full Terraform apply to ensure complete state consistency.
Follow-up 3 curveball. An S3 bucket was successfully created in AWS before the pipeline crashed, but the Terraform state update was lost due to a network failure. On retry, Terraform attempts to create the bucket again, and AWS reports that the bucket already exists and is owned by this account. What do you do?
Answer: the cloud resource exists, but Terraform state tracking lost it. I would first verify that the bucket is the intended resource and is owned by the expected AWS account. Then I would import the existing bucket into Terraform state using Terraform import. Review Terraform plan for any configuration drift, and only proceed once the plan confirms that Terraform is tracking the existing bucket correctly.
Pro tip for this production incident 31.
A failed Terraform apply is not a disaster. It is an incomplete state reconciliation. Terraform persists state as resource operations complete. So after a failed apply, the state file accurately tracks successfully created resources, while remaining resources stay unprovisioned. Fix the root blocker like an IAM permission or quota and rerun Terraform apply. Terraform will reconcile the existing state and determine the remaining actions required to reach the declared configuration.
Production incident 32. A new cloud environment creation fails because the Terraform pipeline requires an IAM role and remote state S3 bucket that the Terraform code itself is supposed to create. How do you resolve the bootstrap deadlock?
Answer: my first priority is to break the circular dependency by using a staged two-phase bootstrap pattern. I would provision the foundational identity and state storage using a minimal initial bootstrap script, import those resources into Terraform state tracking, and then allow the main IaC pipeline to take over lifecycle management. I will follow a structured response plan like Phase 1, Symptoms 1, pipeline fails during Terraform init or initial authentication with an access denied or no such bucket error. 2, the IaC repository contains code to create the backend bucket and IAM role, but the pipeline cannot run without them already existing. 3, new environment provisioning is completely deadlocked on its own bootstrap dependencies. What these symptoms are telling us: the automation is trapped in a chicken and egg dependency loop, where execution depends on infrastructure objects that have not yet been created. Phase 2, Investigation 1, trace the pipeline initialization steps, backend S3 bucket configuration, and IAM role assumption requirements. 2, verify which resources are required at Terraform init execution time versus Terraform apply execution time. 3, check whether the remote state S3 bucket and IAM execution roles were declared inside the same module being executed. What this investigation is revealing or leading to: the pipeline configured the remote S3 backend before the bucket existed in AWS. The build engine cannot initialize state tracking for an environment that has no state bucket. Phase 3, Root Cause 1, architectural design flaw where foundational backend state storage and execution roles were declared inside the application IaC module rather than being provisioned by a separate, decoupled bootstrap phase. Why this is the exact root cause and why not others. The Terraform code is syntactically valid, but initialization fails before code execution can begin. This proves the failure is a bootstrap ordering deadlock rather than an IaC code bug. Phase 4, Immediate Fix 1, provision the initial state S3 bucket and IAM execution role using a lightweight, one-time local script or AWS CLI bootstrap script. 2, configure remote state. Run Terraform import to bring the bootstrap resources into state tracking and execute the main pipeline. 3, verify that remote state initializes cleanly and the pipeline completes successfully. Expected outcome by doing the above steps: the circular dependency is broken, remote state tracking initializes cleanly, and IaC pipeline automation takes over full resource lifecycle management. Phase 5, long-term prevention 1, separate platform bootstrap code state buckets, KMS keys, OIDC roles from application infrastructure code. 2, use automated account vending machines, AWS control tower, or landing zones to pre-provision state backends before IaC pipelines run. 3. Enforce architectural boundaries that prevent modules from referencing state storage that they are responsible for creating. Expected outcome by doing the above steps. Every new environment receives pre-built, secure state storage and execution roles before IaC automation executes, eliminating chicken and egg deadlocks.
Follow-up 1. Why should not you manually create state buckets in the AWS console without importing them into Terraform?
Answer: creating the bucket manually is acceptable as a bootstrap step, but Terraform must be given ownership explicitly. If the bucket exists in AWS but is absent from Terraform state, Terraform will generally plan to create it again rather than automatically adopting it. Importing the bucket establishes the state-to-resource relationship, so future plans manage the existing bucket instead of attempting to create a second one.
Follow-up 2. How do AWS Control Tower, or landing zones, solve the IaC bootstrap problem at scale?
Answer: they isolate platform bootstrapping into account creation triggers. When a new cloud account is vended, baseline S3 state buckets with native S3 lock files and IAM execution roles are automatically provisioned before any developer pipeline executes its first Terraform init.
Follow-up 3. Curveball. You created the S3 state bucket via a local script, but when you run Terraform import, Terraform fails because it needs to store the state of the import inside the bucket that it is currently importing. How do you resolve this?
Answer: you execute the import using a separate, lightweight bootstrap root module configured with a local state backend local. Once the S3 bucket resource is successfully recorded in the local terraform.tf state file, you migrate that state into the S3 remote backend using Terraform init-migrate-state.
Pro tip for this production incident 32.
Never declare your Terraform remote state bucket inside the same Terraform module that uses that state bucket. That creates a classic chicken and egg deadlock. Always decouple platform bootstrapping from workload infrastructure. Use a separate bootstrap module to create state storage first, import it, and then hand over lifecycle control to your remote state IaC pipeline.
Production incident 33. A severe cloud outage requires an immediate infrastructure modification, but Terraform apply fails with a state lock error. The lock is held by an aborted CI runner from a crashed pipeline hours ago. How do you recover safely?
Answer: my first priority is to verify that no active process is writing to the state file before releasing the lock. I would inspect the lock ID, verify runner container and cloud trail status, forcibly clear the stale lock using Terraform force unlock, and execute the emergency infrastructure change. I will follow a structured response plan like Phase 1. Symptoms. 1. Terraform apply or Terraform plan fails immediately with error acquiring the state lock. 2. The error details display a lock ID, client hostname, process ID PID, and creation timestamp from hours ago. 3. Production incident response is completely halted because IaC automation refuses to execute against the locked state. What these symptoms are telling us: the state backend lock protection is functioning as designed, but a stale lock from a dead or aborted runner process is preventing legitimate emergency changes. Phase 2. Investigation. 1. Inspect the S3 native state lockfile.tf lock, and for legacy environments, the DynamoDB lock table entry. 2. Query CloudTrail logs and container metrics to verify if the process ID listed in the lock ID is still running or dead. 3. Verify whether any other pipeline runner or developer machine is actively communicating with the cloud API. What this investigation is revealing or leading to: the CI runner container crashed due to an event 3 hours ago without executing graceful cleanup, leaving the lock file active in the S3 backend. Phase 3. Root cause. 1. Abrupt termination of a CI runner container during an active state write, leaving an orphaned lock entry in the distributed state backend with no automatic expiration. Why this is the exact root cause and why not others. CloudTrail audit logs confirm no API write requests have occurred for 3 hours, and the runner container process is confirmed terminated. This isolates the failure to a stale lock entry. Phase 4. Immediate fix. 1. Verify 100% that no process is running. Copy the lock ID string from the error message and run Terraform force-unlock lock ID to release the state file. 2. Execute the emergency Terraform apply pipeline job to complete the required production infrastructure change. 3. Confirm that the apply completes cleanly and state tracking resumes normal operation. Expected outcome by doing the above steps. The stale lock is released, state access is unblocked, and the emergency infrastructure modification completes successfully. Phase 5. Long-term prevention. 1. Configure container termination handlers in C. runners to attempt graceful SIG-term cleanup on interruption. 2. Set adequate runner memory limits to reduce crashes and establish an operational stale lock verification runbook. 3. Ensure emergency pipelines include automated lock verification pre-checks before executing force unlock operations. Expected outcome by doing the above steps. Runner memory crashes are reduced, and operational procedures ensure safe lock clearing during incidents.
Follow-up 1. Why is running Terraform force-unlock blindly without checking process status extremely dangerous?
Answer. If another developer or automated pipeline is actively writing to state when you run force unlock, you allow multiple writers to operate against the same state without coordination. This can corrupt or diverge your remote terraform.tf state file, requiring complex manual state reconstruction.
Follow-up 2. How does native S3 state locking use _lock file equals true work under the hood?
Answer. With native S3 locking, Terraform creates a separate .tf lock object alongside the state object, for example my-state.tf state.tf lock, and uses that object to coordinate state access. DynamoDB-based locking stores lock information in a DynamoDB table, but that mechanism is now deprecated. In either case, an interrupted process can leave an orphaned lock that requires verification before clearing.
Follow-up 3. Curveball. You ran Terraform force-unlock, but Terraform apply fails again 5 seconds later with error acquiring state lock from a different lock ID. What is happening?
Answer. An automated CI pipeline retry loop, or secondary GitOps controller, is actively attempting to run in a continuous loop. Force unlock released the lock for 1 second, and the automated loop immediately reacquired a new lock ID. You must pause the automated pipeline before force unlocking.
Pro tip for this production incident 33.
A state lock error is a safety mechanism, not an infrastructure bug. Never run Terraform force-unlock out of frustration during an outage. First, verify in CloudTrail or runner container metrics that the lock ID belongs to a dead process. If you force unlock while another runner is actively writing state, you can allow multiple writers to operate against the same state and potentially corrupt or diverge your .tf state file.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 34. A Terraform deployment provisions a Kubernetes cluster and attempts to deploy Helm charts in the same run. The apply fails because the cloud provider control plane, API, is not fully ready to accept requests when Helm executes. How do you fix dependency races?
Answer. My first priority is to resolve the race condition by decoupling infrastructure, provisioning from workload deployment, and enforcing explicit readiness verification. I would separate cluster creation from Helm releases into independent pipeline stages and confirm API endpoint health before deploying workloads. I will follow a structured response plan like Phase 1. Symptoms. 1. Terraform apply fails with connection refused, unauthorized, or TLS handshake timeout when initializing Kubernetes or Helm providers. 2. The EKS or GKE cluster resource reports creation complete in AWS or GCP, but the API endpoint is not yet accepting external requests. 3. Rerunning Terraform apply 2 minutes later without code changes succeeds cleanly. What these symptoms are telling us: the cloud provider control plane creation completed from an IaC resource perspective, but the control plane API endpoint was not yet fully initialized when downstream providers attempted to connect. Phase 2. Investigation. 1. Review the execution graph Terraform graph, provider initialization timing, and cloud audit logs for the EKS or GKE cluster endpoint status. 2. Check whether downstream Kubernetes resources, depend explicitly on node group readiness or control plane, API responsiveness. 3. Verify whether provider configurations evaluate dynamic data sources before cluster endpoints exist. What this investigation is revealing or leading to: the Kubernetes provider attempted to fetch cluster authentication tokens before the EKS control plane. API server finished initializing its internal DNS and IAM auth webhooks. Phase 3. Root cause. 1. Provider initialization race condition, caused by combining cluster infrastructure creation and Kubernetes workload deployment in a single Terraform state stack without explicit API readiness. Polling why this is the exact root cause and why not others. Reapplying after a 2-minute pause succeeds without code modifications, proving the failure was an asynchronous API readiness timing window. Phase 4. Immediate fix. 1. Separate cluster provisioning from Kubernetes and Helm deployment into independent execution stacks. 2. Confirm the Kubernetes API endpoint is reachable and authentication succeeds via a health check step before starting the workload deployment stage. 3. Rerun the workload deployment stage only after the API readiness verification succeeds. Expected outcome by doing the above steps: workload deployment executes against a fully responsive, verified API endpoint, eliminating connection timeouts. Phase 5. Long-term prevention. 1. Architecturally decouple infrastructure EKS cluster, VPC, IAM from application workloads Helm charts, Kubernetes manifests. 2. Use GitOps Argo CD or Flux to manage application workloads once IaC completes cluster provisioning. 3. Enforce multi-stack deployment pipelines, where infrastructure provisioning and workload deployment execute in separate, sequential stages. Expected outcome by doing the above steps: infrastructure provisioning and workload delivery operate in clean, independent lifecycle layers with zero provider initialization race conditions.
Follow-up 1. Why is combining Kubernetes resource providers and AWS cluster creation in a single Terraform module considered an anti-pattern?
Answer: Terraform evaluates provider configuration during plan and apply before resources are created. If provider authentication depends on dynamic data sources from an uncreated cluster, the initialization fails. Decoupling cluster creation from workload deployment ensures providers initialize against existing endpoints.
Follow-up 2. How can time_sleep be used as a secondary workaround for cloud API propagation delays?
Answer: time_sleep introduces an explicit state-tracked pause in the execution graph. By placing depends underscore on equals time_sleep dot wait 60 seconds on downstream resources, you force Terraform to wait for asynchronous cloud control plane DNS and IAM propagation to complete.
Follow-up 3. Curveball. You added depends_ onto the Helm release, but Terraform plan still crashes on a fresh environment with Kubernetes cluster reachable check failed. Why?
Answer: provider configuration blocks are evaluated during the plan and interpolation phase before any depends_ on resource logic runs. If the Kubernetes provider uses dynamic data sources data, AWS_EKS_ cluster that require an existing cluster, the plan phase fails. The cluster must be created first, or provider block attributes must reference static variables.
Pro tip for this production incident 34.
Avoid tightly coupling Kubernetes workload deployment with cluster infrastructure provisioning in the same Terraform state when provider initialization or API readiness can race. Prefer Terraform for cluster and platform infrastructure. Then use a separate workload deployment stage or GitOps Argo CD or Flux once the Kubernetes API is verified healthy.
Production incident 35. An infrastructure change modifies a cloud database storage engine and network security boundary. When an application regression occurs, rolling back application code is easy, but git revert on Terraform code fails because the infrastructure modification is irreversible. How do you recover?
Answer: my first priority is to stabilize the production application, while accepting that cloud infrastructure state changes cannot always be rolled back via simple code reverts. I would evaluate stateful data migration requirements, forward fix the infrastructure configuration, or execute a blue-green environment failover. I will follow a structured response plan like Phase 1, Symptoms 1, Application code rollback succeeds, but the app cannot communicate with the database due to irreversible infrastructure changes. 2. Running Terraform apply on a reverted Git commit fails with provider errors, stating that cloud storage engine downgrades or VPC peering deletions are not supported. 3. Production service remains degraded despite code version rollback. What these symptoms are telling us: the infrastructure change altered stateful or non-reversible cloud provider components. Code revert alone cannot restore infrastructure compatibility. Phase 2. Investigation. 1. Review the Terraform execution log, cloud provider API documentation for the modified resources, and database storage state. 2. Identify whether the cloud API explicitly blocks in-place downgrades for database storage engines or encrypted volume attributes. 3. Verify whether a point-in-time backup exists that can be restored into a parallel environment. What this investigation is revealing or leading to: the cloud provider API explicitly blocks in-place downgrades for database storage engines and encrypted volume attributes. Reverting code in Git cannot undo the cloud provider's physical state change. Phase 3. Root cause. 1. Architectural failure to recognize non-reversible infrastructure changes storage engine conversions. KMS encryption additions. CIDR shrinkage and treating IaC rollbacks as if they were. Stateless application code reverts. Why this is the exact root cause and why not others. The provider API rejects the downgrade operation by design. This isolates the failure to an irreversible cloud state mutation rather than a Terraform code bug. Phase 4. Immediate fix. 1. Do not attempt to force a destructive IaC rollback. Forward fix the application code to be compatible with the new infrastructure state, or perform a point-in-time database restore to a parallel legacy environment. 2. Reroute application traffic to the restored parallel database environment if application compatibility requires it. 3. Confirm that production metrics and database query latency normalize. Expected outcome by doing the above steps: application service is restored without corrupting stateful database storage or triggering destructive cloud provider rollbacks. Phase 5. Long-term prevention. 1. Classify IaC changes by reversibility before execution. Treat non-reversible changes storage migrations, KMS key swaps, as one-way migrations requiring blue-green infrastructure stacks. 2. Require explicit pre-flight backup validation before executing one-way infrastructure modifications. 3. Enforce blue-green infrastructure deployment patterns for non-reversible cloud mutations so old infrastructure remains active until new infrastructure is proven stable. Expected outcome by doing the above steps: one-way infrastructure changes are isolated in parallel environments, ensuring safe rollback paths exist before production traffic cuts over.
Follow-up 1. Why is Git revert on Terraform code fundamentally different from Git revert on application code?
Answer: reverting application code replaces a container binary. Reverting Terraform code executes cloud API calls against live, stateful infrastructure. If the cloud API does not support reversing an operation like shrinking an EBS volume or downgrading a DB engine, Terraform cannot force the provider to undo it.
Follow-up 2. How does a blue-green infrastructure strategy make non-reversible IaC changes safe?
Answer: you build green infrastructure alongside existing blue infrastructure using Terraform. You migrate data and route traffic to green. If a regression occurs, rollback is a simple DNS traffic flip back to blue. Blue infrastructure is only decommissioned after green is proven stable.
Follow-up 3. Curveball. You deployed an IaC change that encrypted an unencrypted RDS database. Application performance degraded by 50%. You try to revert, but AWS RDS does not support unencrypting a database in place. What do you do?
Answer: You cannot reverse RDS encryption in place, and an encrypted snapshot cannot simply be restored as an unencrypted RDS instance. I would first determine whether performance degradation is actually caused by encryption or another parameter. If an unencrypted database is genuinely required, I would create a new unencrypted target, migrate data using logical replication or export or import, and cut traffic over after validation.
Pro tip for this production incident 35.
Never assume infrastructure as code is safely reversible. Many cloud API operations, such as shrinking storage volumes, turning off RDS encryption, or modifying DB storage engines, are one-way state transitions. Always classify IaC changes by reversibility. For one-way infrastructure changes, build a parallel green environment using Terraform instead of mutating live production infrastructure in place.
Production incident 36. A developer deletes a code block during repository cleanup, thinking it was dead code. During the next automated apply, Terraform interprets the missing code block as an intentional deletion and removes a live production security group rule. How do you recover?
Answer: my first priority is to halt automated pipeline execution and restore the accidentally removed security group rule. I would recreate the rule via emergency IaC commit or temporary manual addition, verify microservice connectivity, and enforce PR plan checks. I will follow a structured response plan like Phase 1. Symptoms. 1. Production microservices suddenly lose network connectivity and report connection timeouts. 2. Cloud audit logs show a revoked security group ingress, API event executed by the CI and CD deployment IAM role. 3. Terraform execution log shows a rule deletion diff minus resource AWS underscore security underscore group underscore rule ingress that was merged without review. What these symptoms are telling us: a declarative removal of code in Git was interpreted by Terraform as an instruction to delete the corresponding live security group rule. Phase 2. Investigation. 1. Review recent Git PR commits to locate the code deletion. Inspect the Terraform plan output generated during the CI build and check CloudTrail deletion timestamps. 2. Verify which specific port and ingress CIDR rule was removed from the live security group. 3. Check whether the security group rule contained an associated prevent underscore destroy or deletion guard policy. What this investigation is revealing or leading to: a cleanup PR removed the AWS underscore security underscore group underscore rule HCL block, assuming it was unused. The automated pipeline executed Terraform apply and removed the rule from AWS. Phase 3. Root cause. 1. Unintentional deletion of an AWS underscore security underscore group underscore rule HCL resource block during code cleanup, combined with automated apply execution without planned diff, verification, or prevent underscore destroy safeguards. Cause and why not pass through maps and others. Declarative IaC matches live cloud state to repository code. Deleting the rule block explicitly instructed Terraform to send a deletion API request to AWS. The failure was a code review and plan governance breakdown. Phase 4. Immediate fix. 1. Immediately revert the cleanup PR in Git to restore the AWS underscore security underscore group underscore rule HCL code. Run Terraform apply and verify that the ingress rule is reattached to the security group. 2. Confirm that microservice network connectivity and port traffic are fully restored. 3. Re-verify that all production application dependencies report healthy connectivity. Expected outcome by doing the above steps: the security group rule is recreated, network port access is restored, and microservice traffic flows cleanly. Phase 5. Long-term prevention. 1. Add lifecycle prevent underscore destroy equals true blocks or deletion guard policies to critical security group rule manifests. 2. Implement CI plan validation checks, for example, conftest or OPA, that flag PRs containing resource deletion diffs for mandatory multi-person approval. 3. Establish clear team workflows distinguishing resource state disassociation Terraform state RM from destructive code deletion. Expected outcome by doing the above steps. Unintentional code deletions are caught and blocked during PR evaluation before destructive apply operations execute in production.
Follow-up 1. Why is deleting an AWS_security_group_rule resource block safer to troubleshoot than deleting an entire AWS_security_group resource block?
Answer: deleting an entire security group can fail if AWS detects active attachments, or can sever attachments on dependent EC2 instances even if recreated. Deleting a rule block modifies the rule set inside an existing security group ID, making recovery via Terraform apply fast and non-destructive to the underlying security group container.
Follow-up 2. How do you safely remove a resource from Terraform management without destroying the live cloud object?
Answer: you run Terraform state RM resource_address. This removes the resource from state tracking without sending a deletion API call to the cloud provider. Then you can safely remove the HCL code block.
Follow-up 3. Curveball. A developer ran Terraform state RM to stop managing a security group rule, but left the HCL code in the repository. What happens on the next Terraform apply?
Answer: Terraform checks state, finds no entry for the rule, but sees the HCL code block. It assumes the rule needs to be created and sends an API call. The cloud provider API fails because the rule already exists in AWS. You must either remove the code or run Terraform import to readopt it.
Pro tip for this production incident 36.
In declarative IaC, deleting code is not cleaning up scripts. It is an explicit instruction to destroy live cloud infrastructure. Never delete an HCL resource block without checking Terraform plan for minus signs. If you want to stop managing a resource without deleting it from the cloud, use Terraform state RM first before removing the code.
Production incident 37. A centralized IAM and network Terraform module is updated to add a new security rule. A variable substitution error causes the change to apply across dev, staging, and production simultaneously, severing cross-environment database connections. How do you recover?
Answer: my first priority is to isolate the production environment and restore its network, an IAM access boundary. I would revert the centralized module change, enforce environment isolated state boundaries, and implement blast radius promotion controls. I will follow a structured response plan like Phase 1. Symptoms 1. Dev, staging, and production environments experience simultaneous database connection drops following a single platform module PR merge. 2. Terraform execution logs across all environment pipelines. Report identical modifications to shared IAM policies or security group rules. 3. Cross-environment isolation breaks as shared IAM roles or transit gateway route tables are updated globally. What these symptoms are telling us: the centralized module change lacked environment isolation boundaries, allowing a single pull request to execute a global, multi-environment blast radius. Phase 2. Investigation. 1. Inspect the shared module repository, diff variable pass-through maps in environment main.tf files, and state backend configurations for each environment. 2. Evaluated var simultaneous .pipeline environment, or execution creates, and a global resource parameter. 3. Check pipeline triggers to determine why dev, staging, and production pipelines executed simultaneously on a single PR merge. What this investigation is revealing or leading to: the shared module hard-coded a global IAM resource name or security group rule without evaluating the var.environment variable, causing the production pipeline to apply staging parameters. Phase 3. Root cause. 1. Tightly coupled shared IaC module design without strict environment variable validation, combined with automated CI pipelines that executed parallel applies across dev, staging, and production simultaneously. Why this is the exact root cause and why not others. The failure impacted all environments at the exact moment the shared module PR merged. This rules out an isolated cloud failure and confirms a global module blast radius error. Phase 4. Immediate fix. 1. Immediately revert the shared module PR in Git, or override the bad variable in the production main.tf file, and execute an emergency Terraform apply on production first. 2. Verify that production IAM policies, route tables, and database connections return to a healthy state. 3. Confirm that production is fully operational before executing recovery, applies in staging or dev. Expected outcome by doing the above steps. Production IAM policies and network routes are restored, isolating production from non-production pipeline changes. Phase 5. Long-term prevention. 1. Version shared modules explicitly using protected, immutable release tags, or exact commit SHAs ref equals v2.1.0. 2. Require staged promotion dev first, then staging, then production rather than simultaneous multi-environment applies. 3. Add HCL variable validation rules inside shared modules to enforce valid environment input parameters. Expected outcome by doing the above steps. Platform module updates are deployed in controlled, environment-isolated phases, eliminating global blast radius outages.
Follow-up 1. Why should production pipelines never automatically execute at the same time as dev and staging pipelines when a shared repository changes?
Answer. Evaluated var simultaneous pipeline environment or execution creates and a global resource parameter, unbounded blast radius. If a shared configuration contains a bug, it destroys all environments concurrently. Production must always be gated behind staged promotion windows and independent state execution.
Follow-up 2. How do you enforce environment parameter validation inside a shared Terraform module?
Answer. Use custom variable validation blocks in HCL. For example, add a validation block asserting that var.environment must be in an approved set like dev, staging, or prod. This causes Terraform plan to fail immediately if an invalid or missing environment value is supplied.
Follow-up 3. Curveball. The shared IAM module change revoked the CI and CD pipeline's own IAM permissions across all environments. Now Terraform cannot authenticate to revert the change. How do you recover?
Answer. I would stop all automated applies first, then use an independently controlled break glass administrative role whose access path does not depend on the affected CI and CD identity. From that identity, I would restore the minimum permissions required for the pipeline or revert the IAM policy change, validate the resulting access, and only then resume Terraform execution. After recovery, I would investigate why the shared module was able to modify the pipeline's own recovery path and add safeguards against self-lockout.
Pro tip for this production incident 37.
A shared Terraform module is a force multiplier for platform teams, but without explicit versioning, it is also a blast radius multiplier. Never let dev, staging, and production consume a shared module via a mutable branch or main reference. Always pin production modules to explicit release tags ref equals v2.1.0 or commit SHAs, and enforce staged promotion so a bug in a shared IAM module never takes down every environment at once.
Category 3 Summary and Key Takeaways. What we mastered in IaC.
Core engineering principles proven in Category 3. 1. Infrastructure state integrity. Treat Terraform state as a critical production control plane and prevent split-brain ownership, stale locks, and unmanaged resources. 2. Destructive change defense. Detect replacement plans, protect critical resources, and never assume that reverting IaC code automatically reverses infrastructure changes. 3. Dependency and version governance. Control provider versions, shared modules, and infrastructure dependencies, so production changes are deliberate and reproducible. 4. Drift and recovery discipline. Detect accumulated infrastructure drift, recover safely from partial applies, and reconcile real cloud resources with declared infrastructure state. Reliable infrastructure automation depends on controlled state, deterministic changes, and deliberate recovery.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Focus shift from Category 3, IaC, to Category 4, Containers and Kubernetes.
In Category 3, we focused on how cloud infrastructure is provisioned, tracked, changed, and recovered through infrastructure as code. But once the underlying infrastructure is ready, The next production risk moves into the runtime and deployment layer. Containers have to pull the correct images. Kubernetes has to schedule workloads. Admission controls must allow valid releases. Configuration must reach the right pods, and deployment controllers must safely move applications from one version to another. In Category 4, we move from building and managing the infrastructure to delivering and operating workloads on that infrastructure, where image identity, Kubernetes behavior, storage, scheduling, webhooks, API pressure, and deployment mechanics can create production failures.
Category 4. Containers, Kubernetes, and deployment mechanics.
Containers and Kubernetes provide the runtime and deployment foundation for modern cloud-native applications. But successful deployment is much more than pushing an image and waiting for pods to become healthy. Production failures can occur when the same image tag resolves to different digests. Registries lag across regions. Image pulls overwhelm infrastructure. Architecture changes break workloads. Admission webhooks reject or delay releases. Configuration remains stale, or Kubernetes scheduling and storage behavior changes underneath an application. Category 4 equips you to diagnose, isolate, and recover from production incidents where container artifacts, Kubernetes control plane behavior, workload scheduling, configuration, and deployment mechanics interact.
Category 4 Incidents. Incidents 38 to 50.
Here are the containers, Kubernetes, and deployment mechanics production incidents we will cover in this category. Incident 38. Same image tag, different image digest. Incident 39. Registry replication lag, breaks regional deployment. Incident 40. Container image pull storm overwhelms registry. Incident 41. Multi-architecture image, breaks new node pool. Incident 42. Admission webhook, rejects a valid production release. Incident 43. Mutating webhook times out during release surge. Incident 44. Deployment, uses stale container configuration. Incident 45. Readiness behavior, causes a rollout deadlock. Incident 46. Platform upgrade changes scheduling behavior. Incident 47. Stateful deployment cannot reattach storage. Incident 48. New daemon set consumes application capacity. Incident 49. Kubernetes API load, disrupts deployment automation. Incident 50. GitOps controller dies, processing a massive release. Let's dive into production incident 38.
Production Incident 38. Staging and production. Both deploy image tag release 2026.08, but the workloads resolve that tag to different image digests. Staging passes validation, while production runs different container contents. How would you isolate the artifact promotion failure?
Answer: my first priority is to prove whether the two environments are actually running different image bytes, despite using the same tag. I would trace the image reference from the release pipeline through each registry and deployment manifest, compare the resolved digests, and determine where the artifact identity diverged before changing the application. I will follow a structured response plan like Phase 1, Symptoms 1, Staging and Production Manifests, reference the same container image tag. 2, Staging and Production Pods, report different image digests for that same tag. 3, Application behavior differs between environments, even though the release configuration appears identical. What these symptoms are telling us: the image tag is not providing a single artifact identity across environments. The failure is therefore likely in artifact promotion, registry mapping, or environment-specific image resolution, rather than application configuration. Phase 2. Investigation. 1. Compare the actual image digests running in staging and production and trace each digest back to its registry repository, push event, and release build. 2. Inspect the promotion pipeline to determine whether it copied the exact image digest between registries or independently rebuilt and pushed the same tag. 3. Compare registry tag metadata, image manifests, and deployment configuration for each environment to identify where the same tag acquired different content. What this investigation is revealing or leading to: both environments use the same tag string, but the promotion process did not preserve a single, immutable artifact identity. The tag was republished or resolved independently, allowing each environment to run a different digest. Phase 3. Root cause. 1. The release process promoted a mutable tag instead of promoting one immutable artifact digest, allowing staging and production registries to associate the same tag with different image contents. Why this is the exact root cause, and why not others. The source commit and release metadata are consistent, but the live digests differ between environments. That directly identifies the promotion boundary as the point where artifact identity was lost. Phase 4. Immediate fix. 1. Identify the approved release digest and verify it against the artifact produced by the release pipeline. 2. Update production to reference that exact digest and verify every running replica resolves to the approved artifact. 3. Freeze further tag-based promotion until the promotion path is corrected and the environment-specific image mappings are understood. Expected outcome by doing the above steps. Staging and production converge on the exact artifact that was tested and approved, eliminating the environment-specific image mismatch. Phase 5. Long-term prevention. 1. Promote immutable image digests between registries and environments instead of rebuilding or republishing the same release tag. 2. Record the source commit. Build ID, image digest, and promotion event as a single release identity. 3. Add post-promotion verification that compares the expected digest with the digest actually running in the target environment. Expected outcome by doing the above steps. A release has one verifiable artifact identity from build through production, making cross-environment artifact divergence immediately detectable.
Follow-up 1. If both environments use the same image tag, why can they still run different image digests?
Answer. A tag is only a reference name. It does not guarantee that the same registry object exists behind it everywhere. If staging and production use different registries, mirrors, or independently populated repositories, the same tag can resolve to different digests. The important production control is to promote the exact digest, rather than assuming the tag itself guarantees artifact identity.
Follow-up 2. How would you automatically detect this mismatch before production traffic is exposed?
Answer. The release pipeline should record the approved image digest before promotion. The deployment verification stage can then query the target workloads and compare their actual digests with that recorded value. If even one production replica is running a different digest, the rollout should fail verification and stop further promotion before the release is considered successful.
Follow-up 3. Curveball. Staging and production both deploy the same tag, but production pulls an older digest. The release pipeline successfully pushed the new digest. What would you investigate?
Answer. I would investigate whether staging and production pull from different regional registries or mirrors. If production uses a regional mirror and the replication of the new digest was delayed or failed, the registry might still serve the old digest under the same mutable tag. Artifact identity must be verified by digest at the destination, not just pushed at the source.
Pro tip for this production incident 38.
Never treat a container tag as proof that two environments are running the same artifact. The same tag can resolve differently across registries, promotion workflows, or mutable references. For production promotion, carry the exact image digest from the build through every environment and verify the digest actually running after deployment. That turns artifact identity from an assumption into an observable fact.
Production incident 39. A release artifact is successfully pushed to the primary container registry, but the deployment pipeline immediately starts a rollout in another region. The target registry has not replicated the image yet, and new production nodes cannot pull it. How would you recover the regional deployment?
Answer. My first priority is to determine whether the target region is genuinely missing the artifact, or whether the deployment is failing for another registry or authentication reason. I would verify replication status and the exact digest availability in the target region, then choose the safest deployment path without promoting an unverified replacement image. I will follow a structured response plan like Phase 1. Symptoms. 1. The image push succeeds in the primary registry, and the release pipeline reports the artifact as available. 2. Pods in the target region enter image pull failure states, because the referenced image or digest is unavailable there. 3. The same image deployment succeeds in regions that have already received the replicated artifact. What these symptoms are telling us: the build and primary registry are healthy, but the target region does not yet have the required artifact. The failure points toward asynchronous registry replication, rather than a bad image or application deployment. Phase 2. Investigation. 1. Check the target registry repository for the expected image digest and compare its availability timestamp with the primary registry push time. 2. Inspect registry replication status, transfer queues, regional replication metrics, and any failed replication events for the release artifact. 3. Verify that the deployment references the intended digest and that the target nodes have valid registry credentials and network access. What this investigation is revealing or leading to: the image exists and is valid in the primary registry, but the target region has not completed replication of the required digest. Other regions receiving the same digest successfully confirm that the image itself is not the primary failure. Phase 3. Root cause. 1. The deployment pipeline treated primary registry availability as proof of regional artifact availability and started the target deployment before replication of the required digest had completed. Why this is the exact root cause and why not others? The expected digest is available in the source registry, credentials are valid, and the target region succeeds as soon as replication completes. That directly ties the outage to missing artifact availability at deployment time. Phase 4. Immediate fix. 1. Pause further rollout in the affected region and verify whether the previous known good digest is still available there. 2. Either wait for the approved release digest to become available or deploy the previously validated regional artifact if the release process allows that rollback path. 3. Resume deployment only after the target registry confirms availability of the exact intended digest. Expected outcome: by doing the above steps, the affected region returns to a deployable state without substituting an unapproved artifact, and the intended release proceeds only after regional availability is confirmed. Phase 5. Long-term prevention. 1. Add registry replication readiness checks that verify the release digest exists in every target region before deployment begins. 2. Make regional artifact promotion a distinct pipeline stage, rather than assuming that a successful primary push means global availability. 3. Alert on replication latency and failed transfers, so deployment orchestration can react before workloads begin pulling the artifact. Expected outcome: by doing the above steps, regional deployments become dependent on verified artifact availability instead of racing against asynchronous registry replication.
Follow-up 1. Would you copy the image manually into the target registry during the incident?
Answer: only through an approved emergency promotion path. I would first verify the exact digest and artifact provenance, then copy that same artifact rather than rebuilding it. The goal is to restore availability without creating a second, independently generated image that could diverge from the tested release.
Follow-up 2. Why is checking only the image tag in the target registry not sufficient?
Answer: because the tag can exist before the required image content is fully available or can point to an unexpected digest. I would verify the exact digest required by the deployment and confirm that the target registry can retrieve that digest before starting the rollout. Artifact availability should therefore be tested by immutable identity, not just tag existence.
Follow-up 3. Curveball. Replication normally completes in 2 minutes, but today it has been delayed for 30 minutes while the production release window is closing. What would you do?
Answer: I would not bypass the artifact identity controls just because the release window is tight. I would determine whether another approved registry path already contains the exact digest, assess whether the previous version can safely remain in the region, and communicate the release impact clearly. If an approved alternate promotion path exists, I would use it. Otherwise, I would keep the region on the known good release until the required artifact is verifiably available.
Pro tip for this production incident 39.
A successful image push is not the same thing as global artifact availability. In multi-region delivery, the real deployment prerequisite is the exact release digest is retrievable from the target region's registry path. Make that machine verified gate in the release pipeline. Otherwise, the deployment system can start a perfectly valid rollout against an artifact that does not yet exist where the workload is running.
Production Incident 40. A node failure causes a large portion of the Kubernetes cluster to be replaced at once. Hundreds of workloads restart together and begin pulling large container images simultaneously, overwhelming the registry and delaying recovery. How would you control the pull storm?
Answer: my first priority is to reduce the image pull pressure before it becomes a second outage, and determine whether the cluster can recover using existing cached images or controlled workload startup. I would identify the source of the request surge, protect critical workloads, and restore capacity in a staged manner, instead of allowing every replacement pod to compete for registry bandwidth. Once, I will follow a structured response plan like Phase 1. Symptoms: 1. Large numbers of pods simultaneously enter image pull or startup states after node replacement. 2. Registry request volume and bandwidth usage spike, while image pull latency increases across the cluster. 3. Production workload recovery slows significantly even though cluster nodes are becoming available. What these symptoms are telling us: the infrastructure replacement created a synchronized image download surge. The registry has become the recovery bottleneck, so additional node capacity is not translating into application recovery. Phase 2. Investigation. 1. Correlate node replacement events with registry request volume, image pull latency, failed pulls, and bandwidth utilization. 2. Identify the largest images and highest volume repositories to determine which workloads are generating the majority of registry traffic. 3. Check whether nodes can use local image caches, registry mirrors, pull-through caches, or pre-pulled images for critical workloads. What this investigation is revealing or leading to: the node replacement event created a synchronized demand spike in which hundreds of pods attempted to pull the same large images concurrently. Registry capacity, rather than Kubernetes scheduling capacity, is now limiting recovery. Phase 3. Root cause. 1. Synchronized node replacement caused a large number of cold image pulls at the same time, exceeding the effective registry throughput available to the cluster. Why this is the exact root cause, and why not others? Registry pressure rises directly with pod restart volume, while normal scheduling and application configuration remain valid. Once image pull concurrency is reduced, workload startup recovers without application changes. Phase 4. Immediate fix. 1. Prioritize recovery of critical workloads and reduce unnecessary pod start concurrency while registry pressure is high. 2. Use available registry mirrors, pull-through caches, or pre-pulled images for critical workloads where supported. 3. Restore the remaining nodes and workloads in controlled batches while monitoring registry throughput and pull latency. Expected outcome by doing the above steps: registry demand falls to a recoverable level, critical workloads regain capacity first, and the cluster returns to service without creating another synchronized pull surge. Phase 5. Long-term prevention. 1. Use regional registry mirrors, or pull-through caches so large clusters do not depend on a single registry path for every cold start. 2. Design node replacement and auto-scaling processes to avoid synchronized cold starts where practical. 3. Track image size, pull latency, registry utilization, and cold start recovery time as deployment and platform capacity metrics. Expected outcome by doing the above steps: cluster recovery becomes resilient to large-scale node replacement, instead of making the registry the single bottleneck during a capacity event.
Follow-up 1. Why does not adding more Kubernetes nodes solve the problem?
Answer: more nodes increase the number of workloads that can start, but they also increase the number of simultaneous image pulls if the images are not already cached. When the registry is the bottleneck, adding nodes can actually increase the request storm. I would therefore stabilize registry demand, before continuing to increase cold start concurrency.
Follow-up 2. How would you reduce image pull traffic without changing the application release?
Answer: I would use registry-side caching, local node image reuse, pre-pulling for critical images, and controlled rollout concurrency. I would also identify oversized images and eliminate unnecessary layers in a later optimization cycle. The immediate objective is to reduce duplicate transfers while keeping the exact approved image unchanged.
Follow-up 3. Curveball. The registry is healthy and has plenty of bandwidth, but image pulls are still extremely slow only from one cluster. What would you investigate?
Answer: I would shift the investigation to the network path between the cluster and the registry, specifically looking for NAT gateway bandwidth saturation, or S-NAT port exhaustion. When hundreds of nodes in a private subnet pull multi-gigabyte images concurrently, they can exhaust available NAT or S-NAT capacity, or create significant contention through the shared NAT gateway, causing network-level drops that look like slow registry pulls.
Pro tip for this production incident 40.
The fastest way to make a node replacement incident worse is to let every recovering workload become a simultaneous image download. Treat image distribution as recovery infrastructure. Use caching and mirrors. Control startup concurrency. Keep critical images readily available, and design node replacement so recovery demand is spread over time. That prevents the registry from becoming the bottleneck that extends an otherwise recoverable outage.
Production incident 41. A new Kubernetes node pool using ARM architecture is introduced into production. Existing workloads that previously ran successfully on x86 nodes begin failing with image pull or startup errors after being scheduled onto the new nodes. What would you investigate first?
Answer: my first priority is to determine whether the workload image actually contains a compatible image manifest for the architecture of the new nodes. I would compare the node architecture with the image manifest, identify exactly where the incompatible workload was scheduled, and then decide whether to restore compatible placement or publish the missing architecture before expanding the node pool. I will follow a structured response plan like Phase 1. Symptoms. 1. Existing workloads continue running on x86 nodes, but fail when scheduled onto the new ARM nodes. 2. Image pull or container startup errors appear only on nodes with the new architecture. 3. The same image tag is present in the registry and works successfully on the existing node pool. What these symptoms are telling us: the image reference itself is valid, but compatibility changes when the workload lands on the new CPU architecture. The strongest suspicion is an architecture-specific image or binary mismatch. Phase 2. Investigation. 1. Inspect node architecture labels and compare them with the image manifest list or platform-specific image entries published in the registry. 2. Verify whether the failing image contains an ARM-compatible application binary and compatible native libraries, rather than only an x86 image. 3. Check scheduling changes to determine why the workload was allowed onto the new architecture, and whether architecture constraints were declared in the deployment. What this investigation is revealing or leading to: the new node pool is ARM-based, but the published image contains only an x86 image variant. Workloads that remain on x86 continue normally, while newly scheduled replicas on ARM cannot run the existing artifact. Phase 3. Root cause. 1. The production image was published without a compatible ARM image variant, while the new node pool permitted the workload to schedule onto ARM nodes. Why this is the exact root cause, and why not others. The same image succeeds on x86 nodes, fails only on ARM nodes, and the registry manifest does not contain a compatible ARM image. That directly establishes an architecture compatibility gap rather than an application regression. Phase 4. Immediate fix. 1. Prevent the affected workload from scheduling onto the incompatible node architecture using the appropriate node selection or scheduling constraints. 2. Restore the required workload capacity on compatible x86 nodes and verify that healthy replicas return to service. 3. Do not promote the ARM node pool more broadly until an approved multi-architecture image is available and tested. Expected outcome: by doing the above steps, production workloads return to compatible nodes, service availability is restored, and the new architecture is isolated until the artifact is proven compatible. Phase 5. Long-term prevention. 1. Build and publish multi-architecture image manifests containing every production-supported CPU architecture. 2. Add architecture-specific image validation to CI before allowing workloads to target a new node pool. 3. Encode supported architectures in deployment scheduling policy so incompatible workloads cannot silently move onto unsupported nodes. Expected outcome: by doing the above steps, node architecture changes become controlled platform changes, and production workloads can move between supported architectures without unexpected image failures.
Follow-up 1. How can the same image tag work on x86 but fail on ARM if the deployment manifest is identical?
Answer: a multi-architecture image reference can resolve to different platform-specific image manifests depending on the node architecture. If the published image contains only an x86 variant, the same tag works on x86 but cannot provide a compatible image for ARM. The deployment manifest can therefore remain identical, while runtime compatibility changes with the node architecture.
Follow-up 2. Would you immediately rebuild the application image for RM and redeploy?
Answer: only after confirming that the application and all native dependencies support ARM. I would build the ARM variant, run the same test and security pipeline used for the existing release, publish the multi-architecture manifest, and validate it on representative ARM nodes before expanding the node pool. The goal is to preserve the approved release behavior while adding platform compatibility.
Follow-up 3. Curveball. The container image contains both x86 and ARM variants, but the ARM pods still fail at startup with an executable format error. What would you investigate?
Answer: I would verify which architecture-specific digest the node actually pulled and inspect the binaries inside that image rather than assuming the manifest is correct. An executable format error can indicate that a native binary or shared library inside the ARM image was built for the wrong architecture. I would compare the image layers and build outputs for the ARM variant, then reproduce the startup failure directly on an ARM node.
Pro tip for this production incident 41.
Adding a new CPU architecture is an application compatibility change, not just a node pool change. A container image can be perfectly healthy on x86 and still fail immediately on ARM because of native binaries, libraries, or architecture-specific tooling. Before expanding a new node architecture into production, validate the entire image stack, not just whether the container build succeeded, and verify the actual platform-specific digest that will run on those nodes.
Production incident 42. A production release passes CI, image scanning, and all application tests, but Kubernetes rejects the deployment during admission. The application is valid, yet the release cannot reach the cluster. How would you determine whether the failure is in the workload or the admission path?
Answer: my first priority is to separate application validity from cluster admission policy behavior. Since the artifact already passed the normal release controls, I would inspect the admission rejection, identify the exact policy or webhook responsible, and determine whether the policy is correctly rejecting the workload or has become incompatible with the new release. I will follow a structured response plan like Phase 1, Symptoms. 1. CI, image validation, and application tests complete successfully. 2. The Kubernetes API rejects the production workload during admission with a policy or webhook denial. 3. The same application artifact can run successfully in lower environments where the production admission controls are not identical. What these symptoms are telling us: the application artifact itself is likely valid, while the failure is occurring at the cluster admission boundary. The investigation should therefore focus on policy evaluation and webhook behavior rather than rebuilding the application. Phase 2. Investigation. 1. Inspect the Kubernetes admission error and identify the exact webhook, policy, rule, or denied field responsible for the rejection. 2. Compare the rejected workload manifest with the admission policy requirements and a previously successful production release. 3. Determine whether the policy itself changed, whether the workload introduced a new field or security context, or whether the webhook is evaluating the request differently than expected. What this investigation is revealing or leading to: the release reaches the Kubernetes API successfully, but the production admission policy rejects a workload attribute that lower environments do not enforce. The failure is therefore at the policy enforcement boundary, rather than in the application build or image. Phase 3. Root cause. 1. A production admission policy or webhook enforced a requirement that the new workload did not satisfy, while the release pipeline lacked validation against the same production admission rules. Why this is the exact root cause, and why not others? The image and application tests remain valid, and the Kubernetes API consistently rejects the workload for one specific admission condition. Reproducing the rejection against the policy confirms that admission enforcement, not application execution, is blocking the release. Phase 4. Immediate fix. 1. Identify whether the rejected requirement is an intentional production security control or an incorrect policy regression. 2. If the policy is correct, update the workload through the normal release process to satisfy the requirement. If the policy is incorrect, roll back or correct the policy through the approved emergency. Change path. 3. Rerun the admission validation and confirm the exact production workload is accepted before resuming the rollout. Expected outcome by doing the above steps: the admission boundary is restored to a known good state, and the approved workload either satisfies the required production policy or the incorrect policy is safely corrected. Phase 5. Long-term prevention. 1. Execute the same admission policies used in production during CI validation before a release reaches the cluster. 2. Version admission policies and treat policy changes as controlled production changes with testing and staged rollout. 3. Add clear policy denial observability, so engineers can immediately identify which rule blocked a release and why. Expected outcome by doing the above steps: production releases fail early and explainably when they violate admission requirements, instead of discovering policy incompatibility only after the release reaches the cluster.
Follow-up 1. Why can a release pass security scanning and still be rejected by Kubernetes admission?
Answer: image scanning and admission enforcement evaluate different control points. A scanner may confirm that the image has no known vulnerabilities, while an admission policy may separately require a non-root security context, approved image provenance, specific labels, resource limits, or other workload properties. Passing one security gate does not guarantee that the workload satisfies every cluster admission rule.
Follow-up 2. Would you disable the admission webhook to get the production release through?
Answer: not as the default response. First, I would determine whether the webhook is enforcing a legitimate production control or has itself regressed. If the workload violates an intentional policy, the application should be corrected. If the webhook is malfunctioning, I would use the organization's approved emergency procedure with explicit authorization and compensating controls rather than silently disabling a security boundary.
Follow-up 3. Curveball. The admission webhook rejects only this one namespace, while identical workloads in other production namespaces are accepted. What would you investigate?
Answer: I would compare namespace labels, policy scope, service accounts, exemptions, and admission bindings rather than assuming the workload is different. The namespace may be covered by a stricter policy set or may have an unexpected label that changes policy evaluation. I would reproduce the request against that namespace and compare the admission decision with a successful namespace to identify the exact scope difference.
Pro tip for this production incident 42.
A green pipeline does not guarantee that Kubernetes will accept the release. Admission controls are a separate production gate that can reject a perfectly valid application because of workload-level security or governance requirements. The strongest setup is to evaluate the same production admission policies before deployment, so the release pipeline discovers policy violations before the workload reaches the cluster.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 43. A large production rollout begins, and Helm reports repeated deployment timeouts. The cluster appears healthy, but newly created pods remain stuck during admission, because a sidecar injection webhook becomes slow under the release surge. How would you isolate the real bottleneck?
Answer: my first priority is to determine whether the deployment tool is actually timing out because Kubernetes is unavailable or because an admission dependency is slowing every new object creation. I would trace the request path from Helm to the Kubernetes API to the mutating webhook, correlate latency with release volume, and stabilize admission traffic before retrying the rollout. I will follow a structured response plan like Phase 1. Symptoms. 1. Helm or deployment automation reports repeated timeouts while creating new workloads. 2. Existing running workloads remain healthy, and Kubernetes control plane health does not indicate a general outage. 3. New workload creation latency increases sharply as release concurrency increases. What these symptoms are telling us: the cluster is not broadly unavailable. The delay is occurring on the workload admission path. The timing suggests that a webhook participating in object mutation is becoming the bottleneck under release load. Phase 2. Investigation. 1. Inspect admission webhook latency, invocation counts, timeout events, and webhook pod CPU and memory utilization during the release. 2. Compare normal deployment request latency with the surge period and determine whether webhook calls increase proportionally with workload creation. 3. Check webhook endpoint availability, replica count, service routing, certificate validity, and any recent configuration changes to the mutation service. What this investigation is revealing or leading to: the Kubernetes API remains responsive, but the mutating webhook becomes saturated as release concurrency rises. Each new workload waits on the webhook, which causes the deployment automation to report timeouts even though the underlying cluster is functioning. Phase 3. Root cause. 1. The mutating admission webhook lacked sufficient capacity or resilience for the release burst, causing webhook latency and timeouts to propagate back into the deployment pipeline. Why this is the exact root cause and why not others? Existing workloads remain healthy, Kubernetes API health is normal, and the deployment failure correlates directly with webhook latency under increased admission volume. Reducing release concurrency reduces the timeout pattern, isolating the webhook as the bottleneck. Phase 4. Immediate fix. 1. Reduce rollout concurrency, or temporarily pause non-critical deployments to lower admission request pressure. 2. Restore webhook capacity by scaling its replicas and correcting any resource or endpoint problem identified during investigation. 3. Resume the release gradually while monitoring webhook latency and admission failure rates. Expected outcome by doing the above steps: admission latency returns to an acceptable range, deployment requests complete normally, and the production rollout proceeds without overwhelming the webhook again. Phase 5. Long-term prevention. 1. Capacity test admission webhooks against realistic deployment bursts, rather than only normal steady-state traffic. 2. Configure appropriate resource requests, replicas, timeout behavior, and failure handling for production webhooks. 3. Monitor admission latency, timeout rate, and webhook saturation as first-class deployment platform metrics. Expected outcome by doing the above steps: a large release can no longer turn a slow admission dependency into a cluster-wide deployment bottleneck.
Follow-up 1. Why does Helm report a timeout when the actual problem is a mutating webhook?
Answer: Helm waits for Kubernetes API operations to complete, but the API request may itself be waiting for an admission webhook to finish processing the object. From Helm's perspective, the API call is simply taking too long. The deployment tool therefore reports a timeout, even though the underlying delay is deeper in the admission path.
Follow-up 2. Would increasing Helm's timeout solve the incident?
Answer: it may hide the symptom temporarily, but it does not remove the admission bottleneck. A longer timeout simply allows each request to wait longer for a saturated webhook. I would reduce request pressure and restore webhook capacity first, then use deployment timeouts appropriate for the expected workload rather than using them to mask platform saturation.
Follow-up 3. Curveball. You scale the webhook to 10 replicas, but the rollout is still timing out. What would you investigate next?
Answer: I would verify that the additional replicas are actually receiving traffic and are not themselves constrained by scheduling, CPU, memory, network, or service routing. I would inspect endpoint distribution and per replica latency to determine whether requests are reaching healthy instances. I would also check whether the webhook depends on another overloaded service, because scaling the front-end webhook will not solve a downstream bottleneck.
Pro tip for this production incident 43.
When a deployment tool times out, do not automatically blame the deployment tool. Follow the request path through the Kubernetes API and every admission dependency involved in creating the workload. A mutating webhook can make a healthy cluster look like a deployment failure, because every new object waits for the webhook response. Monitor admission latency separately from control plane health, so the actual bottleneck becomes visible immediately.
Production incident 44. The new application image is running successfully, and its digest matches the approved release. But production continues using an old database endpoint and feature configuration. The container is correct, yet the application behaves as though the previous release were deployed. How would you trace the stale configuration?
Answer: my first priority is to prove that the container artifact is correct, and then trace every configuration source consumed by the running workload. I would compare the intended release configuration with the actual environment variables, mounted files, config maps, secrets, and configuration provider values available inside the affected pods. I will follow a structured response plan like Phase 1. Symptoms 1. Production pods run the expected application image digest and report healthy container startup. 2. Application logs show the previous database endpoint, feature value, or runtime configuration after the release. 3. The deployment manifest changed, but the observed configuration inside running containers did not. What these symptoms are telling us: artifact identity is correct, so the remaining failure domain is runtime configuration delivery. The deployment likely updated the container without successfully refreshing one or more configuration sources. Phase 2. Investigation. 1. Inspect the running pod's environment variables and mounted configuration files, and compare them with the intended release values. 2. Trace the configuration source from the deployment manifest through config maps, secrets, external secret providers, or generated configuration files to identify where the old value remains. 3. Check whether the application consumes configuration only at startup, whether the configuration object actually changed, and whether the rollout recreated pods after the configuration update. What this investigation is revealing or leading to: the new container image was deployed correctly, but the workload retained an older configuration object or consumed the configuration only during process startup. The release therefore changed the application artifact without changing the effective runtime configuration. Phase 3. Root cause. 1. The deployment process updated the image, but did not reliably refresh or propagate the configuration source consumed by the application, leaving running workloads with stale runtime values. Why this is the exact root cause, and why not others. The running image digest matches the approved artifact, while the configuration observed by the process matches the previous version. Recreating the workload with the refreshed configuration corrects the behavior, directly linking the failure to configuration propagation rather than the container image. Phase 4. Immediate fix. 1. Correct the stale config map, secret, or external configuration reference and verify that the intended value is present in the cluster. 2. Restart or roll the affected workloads manually to force them to consume the updated configuration. 3. Verify the effective runtime configuration and application behavior after the rollout. Expected outcome by doing the above steps: the correct release image and intended runtime configuration are active together, restoring the application's expected production behavior. Phase 5. Long-term prevention. 1. Inject a configuration checksum annotation, for example, checksum/config:/sh A256 into the Kubernetes pod template using Helm, or use customized hashed config map and secret. Generation mechanism. 2. Ensure that configuration changes modify the pod template or reference-generated object, so Kubernetes performs a rolling update when the configuration changes. 3. Version configuration alongside release metadata, and make configuration source changes observable in deployment history. Expected outcome by doing the above steps. Production releases cannot silently combine a new artifact with stale runtime configuration, because config changes automatically force a pod rollout.
Follow-up 1. The config map was updated successfully, so why are the running pods still using the old value?
Answer: it depends on how the application consumes the configuration. Environment variables are fixed when the container starts, so updating the config map does not change the existing process environment. Mounted configuration files can update differently, but the application may still cache the original value. I would therefore verify both the Kubernetes configuration object and how the application reads it.
Follow-up 2. Would you always restart every pod after a config map change?
Answer: not automatically. If the application supports dynamic configuration reload from a mounted file, a restart may be unnecessary. If the configuration is injected through environment variables or loaded only during startup, a rollout is required. The correct action depends on the application's configuration lifecycle, which should be explicitly documented and tested.
Follow-up 3. Curveball. The config map is correct and the pods restarted, but only some replicas still report the old configuration. What would you investigate?
Answer: I would compare the actual configuration consumed by each replica and identify whether the pods were created from different configuration revisions or are mounting different sources. I would also inspect rollout history, replica set versions, node-level caching behavior where relevant, and any external configuration provider synchronization. A mixed configuration state usually means the rollout did not fully converge or different replicas are receiving configuration from different sources.
Pro tip for this production incident 44.
A correct image does not guarantee a correct release if the runtime configuration is stale. In Helm-based deployments, inject a SHA-256 checksum of the relevant config map or secret into the deployment's pod template annotations. When that configuration changes, the checksum changes, the pod template changes, and Kubernetes automatically performs a rolling update so new pods consume the updated configuration.
Production incident 45. A new application version starts successfully, but its readiness probe never becomes healthy. Kubernetes refuses to send traffic to the new replicas, while the rollout controller keeps old replicas alive and waits for the new ones. The deployment is stuck between versions. What would you do?
Answer: my first priority is to determine whether the new application is genuinely unhealthy or whether the readiness signal is incorrectly modeling application readiness. I would inspect the probe behavior, compare the new version with the previous version, and determine whether the rollout is blocked by application startup, probe configuration, dependency, availability, or rollout settings before deciding whether to roll back or fix forward. I will follow a structured response plan like Phase 1. Symptoms. 1. New replicas start and remain running, but their readiness status stays false. 2. The rollout does not progress because the required number of ready replicas is never reached. 3. Existing replicas continue serving traffic, while the deployment waits indefinitely for the new version to become ready. What these symptoms are telling us: the containers are starting, but Kubernetes does not consider the new instances safe to receive traffic. The rollout is therefore blocked at the readiness boundary, rather than at basic container startup. Phase 2. Investigation. 1. Inspect readiness probe failures, HTTP responses, probe timing, startup duration, and application logs from the new replicas. 2. Compare the new deployment's probe configuration, startup behavior, and dependency initialization with the last known good version. 3. Determine whether the application is actually unhealthy or whether the readiness probe is checking an endpoint that changed, starts too early, or depends on an unavailable external service. What this investigation is revealing or leading to: the new application starts correctly, but its readiness endpoint does not become healthy within the configured conditions. So Kubernetes correctly withholds traffic and the rollout controller waits indefinitely. The investigation therefore points to a readiness contract mismatch rather than a container startup failure. Phase 3. Root cause. 1. The new application version changed its startup or readiness behavior without updating the Kubernetes readiness requirements, causing the rollout controller to wait indefinitely for a condition the workload could not satisfy. Why this is the exact root cause, and why not others. The process is running. The container remains healthy at the process level, and the rollout advances immediately when the readiness condition is corrected or satisfied. That directly connects the deadlock to the readiness contract. Phase 4. Immediate fix. 1. Determine whether the readiness failure is an application defect or an incorrect probe configuration before changing rollout behavior. 2. If the application is healthy but the probe is incorrect, correct the readiness configuration and roll out through the normal deployment path. If the application is genuinely unhealthy, stop or roll back the rollout. 3. Verify that new replicas become ready, receive traffic correctly, and that the old version is removed only after the new version is proven healthy. Expected outcome by doing the above steps. The rollout converges on a verified healthy version, instead of remaining indefinitely split between old and new replicas. Phase 5. Long-term prevention. 1. Define readiness as a deliberate application contract and validate probe behavior during CI and pre-production rollout testing. 2. Use appropriate startup and readiness thresholds so slow initialization is not confused with permanent application failure. 3. Monitor rollout progress and alert on prolonged readiness failures rather than allowing deployments to remain stuck indefinitely. Expected outcome by doing the above steps. Deployment controllers receive a reliable signal that reflects real traffic readiness, allowing rollouts to progress or fail clearly instead of entering ambiguous mixed states.
Follow-up 1. Why does not Kubernetes send traffic to a pod? Simply because the container is running.
Answer. A running container only proves that the process started. It does not prove that the application is ready to serve production traffic. Readiness allows the workload to declare when dependencies, listeners, initialization, and application state are ready. Kubernetes uses that signal to decide whether the pod should receive traffic.
Follow-up 2. What is the difference between startup, readiness, and liveness checks during a rollout?
Answer. A startup check protects slow-starting applications from being treated as failed before initialization finishes. Readiness determines whether the pod should receive traffic. Liveness determines whether the process should be restarted because it is no longer functioning correctly. Using the wrong check for the wrong purpose can create unnecessary restarts or rollout deadlocks.
Follow-up 3. Curveball. The readiness probe is healthy, but the new version still receives almost no traffic while the old version remains active. What would you investigate?
Answer. I would move beyond readiness and inspect the rollout strategy, service endpoints, traffic routing, replica counts, and any progressive delivery controls. A pod can be fully ready while still receiving little or no traffic because the service, rollout controller, traffic splitting mechanism, or deployment strategy has not shifted traffic as expected. I would trace the request path from the service or ingress layer to confirm where traffic is actually being directed.
Pro tip for this production incident 45.
A readiness probe is not just a health check. It is a traffic management contract between the application and Kubernetes. If the application changes what ready means but the probe does not change with it, the deployment controller can remain stuck indefinitely even though the process is running. Treat readiness behavior as part of the release contract and test the real startup to ready path before promoting a new version.
Production incident 46. A Kubernetes platform upgrade completes successfully, but workloads that were previously distributed across several nodes become concentrated on a smaller subset after the upgrade. CPU and memory pressure rises on those nodes, while other nodes remain underutilized. How would you determine what changed in scheduling behavior?
Answer. My first priority is to determine whether the workload placement changed because of the scheduler itself, node labels and taints, affinity rules, or changes introduced by the platform upgrade. I would compare placement before and after the upgrade, identify which scheduling constraints stopped matching, and stabilize the most pressured workloads before making broader scheduling changes. I will follow a structured response plan like Phase 1. Symptoms. 1. Workloads that were previously spread across multiple nodes become concentrated on a smaller number of nodes after the platform upgrade. 2. The affected nodes develop CPU or memory pressure, while other nodes remain significantly underutilized. 3. No application deployment change occurred at the time the placement pattern changed. What these symptoms are telling us: the application code is unchanged, but the scheduling result has changed. The first suspicion therefore moves toward scheduler behavior. Node metadata, taints, affinity rules, or platform defaults introduced by the upgrade. Phase 2. Investigation. 1. Compare pre-upgrade and post-upgrade pod placement. Node labels, taints, tolerations, affinity rules, topology constraints, and resource requests. 2. Review the platform upgrade notes and scheduler-related configuration changes to identify altered placement defaults or removed scheduling assumptions. 3. Check scheduler events for the affected pods and determine why otherwise available nodes were rejected during placement. What this investigation is revealing or leading to: the workload specifications did not change, but a platform upgrade altered the scheduling conditions available to the workloads. Several nodes are now excluded by changed labels or placement constraints, causing the scheduler to concentrate replicas onto the remaining eligible nodes. Phase 3. Root cause. 1. The platform upgrade changed a scheduling dependency such as node labels, taints, topology behavior, or scheduler configuration, reducing the set of eligible nodes and concentrating workloads. Why this is the exact root cause, and why not others? The placement distribution changes immediately after the platform upgrade, while workload specifications remain unchanged. Scheduler events show the previously used nodes are no longer eligible under the new conditions, directly connecting the concentration to the platform change. Phase 4. Immediate fix. 1. Protect the pressured nodes by reducing unnecessary scheduling pressure, and, where safe, temporarily adjusting the affected scheduling constraint or restoring the previous compatible node. Configuration. 2. Reschedule critical workloads onto eligible underutilized nodes and verify that resource pressure returns to safe levels. 3. Pause further platform rollout until the scheduling behavior is understood and the corrected configuration is validated. Expected outcome by doing the above steps: workloads are redistributed safely, node pressure returns to acceptable levels, and further scheduling concentration is prevented while the platform change is investigated. Phase 5. Long-term prevention. 1. Validate scheduler behavior. Node labels, taints, affinity, and topology rules against representative production workloads before platform upgrades. 2. Include workload placement distribution and node utilization checks in post-upgrade verification. 3. Treat scheduling policy and node metadata changes as compatibility-sensitive platform changes with rollback criteria. Expected outcome by doing the above steps: platform upgrades no longer silently change workload placement in ways that create hidden capacity concentration or application risk.
Follow-up 1. Would you immediately change the application affinity rules to spread the workloads again?
Answer: not before understanding why the existing rules stopped producing the previous placement. Changing workload constraints during an active incident can hide the platform regression and introduce a second change at the same time. I would first identify which scheduling condition changed, then make the smallest controlled adjustment needed to restore safe placement.
Follow-up 2. How would you prove the upgrade changed scheduling behavior rather than simply revealing an existing capacity problem?
Answer: I would compare pre-upgrade and post-upgrade placement for the same workload classes and review scheduler decisions for the same node pool. If the available capacity is substantially unchanged, but the eligible node set or scheduler decisions changed immediately after the upgrade, that provides strong evidence of a scheduling regression. I would also reproduce the placement behavior with an unchanged workload specification in a controlled environment.
Follow-up 3. Curveball. The scheduler configuration is unchanged, but workloads still concentrate after the upgrade, because the new node image removed a label that the pods depend on. How would you respond?
Answer: I would treat the missing label as the actual platform compatibility break rather than changing the workload definition blindly. First, I would restore the expected node metadata or roll back the affected node image where appropriate. Then verify that the scheduler again sees the intended eligible nodes. After stabilization, I would add node image validation that checks required labels and taints before upgraded nodes are admitted into the production pool.
Pro tip for this production incident 46.
A Kubernetes upgrade can change workload placement without changing a single application manifest. Node labels, taints, topology information, scheduler configuration, and platform defaults are all part of the scheduling contract. After a platform upgrade, do not check only whether pods are running. Compare where they are running and whether the distribution still matches the workload's capacity and resilience assumptions.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 47. A stateful application is rescheduled after a node failure, but the replacement pod remains pending because its persistent volume cannot be attached to the new node. The application was healthy before the failure, and the workload cannot start without its existing data. How would you recover without risking data corruption?
Answer: my first priority is to determine whether the volume is healthy and whether the scheduling decision is compatible with its storage topology and attachment rules. I would verify the volume, node, attachment state, and storage class behavior before forcing any detach or delete operation, because stateful storage recovery must preserve data integrity. I will follow a structured response plan like Phase 1. Symptoms. 1. The replacement pod remains pending, while the scheduler reports a volume attachment or topology-related error. 2. The persistent volume still exists, but it is associated with the previous node or unavailable in the new node's failure domain. 3. Application recovery is blocked because the workload requires the existing persistent data. What these symptoms are telling us: the application container itself is not the immediate problem. Recovery is blocked at the storage attachment boundary, so the investigation should focus on volume state, topology, node eligibility, and attachment operations. Phase 2. Investigation. 1. Inspect the persistent volume claim, storage class, volume attachment objects, and the node where the workload is trying to start. 2. Verify the volume's topology or availability zone constraints and compare them with the replacement node's location. 3. Check cloud storage and controller events to determine whether the volume is still attached to the failed node, whether a detach operation is pending, or whether the controller is rejecting the new attachment. What this investigation is revealing or leading to: the volume is healthy, but the replacement pod landed on a node outside the volume's supported topology, while the old attachment has not yet fully cleared. The workload cannot start until the storage is eligible and safely attachable to the replacement node. Phase 3. Root cause. 1. The rescheduling event moved the stateful workload to a node that could not safely attach its existing volume, combined with storage topology or attachment constraints that were not sufficiently accounted for in the workload scheduling design. Why this is the exact root cause and why not others. The application image and pod configuration remain valid, while storage events consistently reject the new attachment based on topology or attachment state. Recovery succeeds once the workload is placed on an eligible node and the previous attachment is safely released. Phase 4. Immediate fix. 1. Stop repeated attachment attempts and identify a node in the correct storage availability zone where the volume can safely attach. 2. Allow the storage controller to complete any required detach operation and verify that the volume is no longer actively attached before forcing any recovery action. 3. Start the workload on the eligible node and verify application data integrity before restoring normal scheduling. Expected outcome by doing the above steps: the existing volume is reattached safely to a compatible node, the stateful workload returns with its original data, and no unsafe storage operation is performed. Phase 5. Long-term prevention. 1. Configure your Kubernetes storage class with volume binding mode. Wait for first consumer, so topology-constrained volumes are provisioned or bound after pod scheduling and can align with the pod's eligible topology. 2. Encode storage topology constraints into your workloads, so stateful pods preferentially land where their persistent volumes physically exist. 3. Monitor volume attachment delays and repeated attach failures as part of stateful workload recovery readiness. Expected outcome by doing the above steps. Node failures no longer leave stateful workloads stranded on incompatible storage topology, as scheduling and storage provisioning are strictly coupled.
Follow-up 1. Why should not you immediately force detach the persistent volume from the failed node?
Answer: because the volume may still be in use, or the storage platform may still be completing an attachment or detach operation. Forcing a detach without understanding the actual attachment state can create data corruption risk for stateful workloads. I would first verify that the original node is truly unavailable and that the storage controller considers the volume safe to attach elsewhere.
Follow-up 2. How can scheduling rules prevent this kind of storage reattachment failure?
Answer: the workload can use storage-aware topology constraints so that the scheduler considers where the persistent volume can actually be attached. The storage class and workload scheduling rules should work together rather than treating storage placement as an afterthought. The objective is to ensure that a rescheduled stateful workload lands on a node where its existing volume is supported.
Follow-up 3. Curveball. The replacement node is in the correct availability zone, but the volume still cannot attach because the previous node is still reporting it as attached. What do you investigate?
Answer: I would investigate the storage controller and cloud provider attachment state rather than moving the pod again. I would verify whether the previous node is genuinely unreachable, whether the attachment object is stale, and whether the storage backend requires a safe detach completion before allowing a new attachment. The recovery decision should be based on confirmed storage state, not simply the fact that the previous node is no longer serving workloads.
Pro tip for this production incident 47.
For stateful workloads, node failure is only half the recovery problem. The other half is whether the storage can safely follow the workload. A pod being schedulable does not mean its volume is attachable in that zone. For topology-constrained dynamically provisioned storage, use wait for first consumer so volume provisioning and binding take the pod scheduling constraints into account. This helps prevent storage from being provisioned in a topology the workload cannot use.
Production incident 48. A new platform daemon set is deployed across every Kubernetes node. The agent appears healthy, but within minutes, application workloads begin experiencing CPU throttling, memory pressure, and evictions. The platform change itself is healthy, its resource footprint is not. How would you contain the impact?
Answer: my first priority is to determine how much node capacity the new daemon set consumes and which workloads are being displaced as a result. I would compare node utilization before and after the rollout, verify the agent's resource requests and actual usage, and reduce its footprint or rollout scope before application capacity becomes unstable. I will follow a structured response plan like Phase 1. Symptoms. 1. Application nodes show a sudden increase in CPU and memory consumption immediately after the daemon set rollout. 2. Application pods begin throttling, entering memory pressure conditions, or being evicted despite no application deployment change. 3. The new platform agent is running successfully on nearly every node. What these symptoms are telling us: the daemon set itself is operational, but it has changed the resource budget available to application workloads. The incident is therefore a platform capacity regression introduced by a node-wide deployment. Phase 2. Investigation. 1. Compare node CPU and memory utilization before and after the daemon set rollout, and measure the agent's actual per-node resource usage. 2. Inspect daemon set resource requests, limits, container behavior, and whether the scheduler accounted for the requested footprint when placing application workloads. 3. Identify which nodes and workload classes are under the greatest pressure, and whether the agent can be excluded from non-critical or dedicated application nodes. What this investigation is revealing or leading to: the new agent consumes a substantial amount of node capacity on every node, reducing the headroom previously available to application workloads. The resulting pressure is concentrated on nodes where application capacity was already close to the scheduling boundary. Phase 3. Root cause. 1. A node-wide daemon set introduced an unplanned per-node resource footprint that reduced application capacity across the cluster without sufficient resource budgeting and capacity validation. Why this is the exact root cause and why not others. Application versions and traffic patterns remain unchanged, while resource pressure begins immediately after the daemon set rollout and scales with the number of nodes running the agent. Removing or reducing the agent footprint restores node capacity. Phase 4. Immediate fix. 1. Pause the daemon set rollout and reduce or revert the agent configuration to a known safe resource footprint. 2. Protect critical application capacity by moving affected workloads where safe and preventing additional node pressure during recovery. 3. Verify node utilization, eviction rates, and application performance before resuming platform agent rollout. Expected outcome by doing the above steps. Application capacity returns to a safe operating margin. Evictions and throttling subside, and the platform agent can be reintroduced only after its resource footprint is controlled. Phase 5. Long-term prevention. 1. Establish explicit CPU and memory budgets for node-wide agents and include their footprint in cluster capacity planning. 2. Test daemon set resource consumption on representative node types before organization-wide rollout. 3. Monitor per node allocatable capacity and reserve sufficient headroom for application workloads before adding platform agents. Expected outcome by doing the above steps. Platform agents become capacity-aware infrastructure components rather than hidden consumers of application production capacity.
Follow-up 1. If the daemon set pods have resource requests, why did they still cause application evictions?
Answer. Resource requests help the scheduler account for reserved capacity, but they do not guarantee that actual usage will stay within the declared request. If the agent's real usage is significantly higher, or if node overhead and application demand leave too little headroom, the node can still experience pressure. I would compare declared requests and limits with actual consumption, rather than assuming the requests represent the agent's full operational cost.
Follow-up 2. Would simply adding more nodes solve the problem?
Answer. It can restore capacity temporarily, but I would not treat it as the permanent solution. A daemon set consumes resources on every new node, so scaling the cluster also scales the agent footprint. I would first correct or constrain the agent's per node resource consumption, then determine whether additional capacity is still required for the application's workload.
Follow-up 3. Curveball. The agent's CPU usage is normal, but memory pressure appears only on a subset of large nodes. What would you investigate?
Answer. I would compare the agent's memory profile and node memory capacity across the affected node classes. The large nodes may have different workload density, memory limits, kernel reservations, or application characteristics that make the agent's footprint more significant there. I would investigate node-level allocatable memory and eviction events, rather than assuming the daemon set is consuming the same practical capacity on every node.
Pro tip for this production incident 48.
A daemon set multiplies its resource footprint by the number of nodes. A platform agent, using only a small amount of CPU and memory on one node, can become a significant production capacity consumer across a large cluster. Before deploying a node-wide component, calculate its per-node footprint, multiply it by the expected node count, and validate the remaining application headroom on every node class.
Production incident 49. A deployment controller begins generating an unusually high volume of Kubernetes API requests during a large release. API latency rises, normal reconciliation becomes slow, and deployment automation across multiple teams starts timing out. How would you distinguish an API capacity problem from an application deployment problem?
Answer. My first priority is to establish whether the Kubernetes API is being saturated by control plane request volume, rather than treating each deployment timeout as an independent application failure. I would correlate API request rate and latency with controller activity, identify the source of the request surge, and reduce non-essential automation traffic while protecting critical production changes. I will follow a structured response plan like Phase 1. Symptoms. 1. Kubernetes API request latency rises sharply during a large release. 2. Multiple independent deployment and reconciliation jobs begin timing out even though the underlying workloads are otherwise healthy. 3. API request volume is significantly higher than the cluster's normal baseline. What these symptoms are telling us: the failures are occurring at the Kubernetes control plane interaction layer. Multiple teams seeing deployment timeouts at the same time suggests a shared API capacity problem rather than unrelated application failures. Phase 2. Investigation. 1. Inspect API request rate, request latency, rejected or throttled requests, and the highest volume client identities during the incident window. 2. Correlate the request surge with controllers, operators, deployment automation, or reconciliation loops that changed activity during the release. 3. Determine whether the request load is concentrated in a small number of resources, namespaces, or controller operations, and whether clients are retrying aggressively. What this investigation is revealing or leading to: a single deployment controller is generating a large reconciliation and polling surge, while retries from other automation multiply the request volume. The Kubernetes API remains available, but shared request capacity is being consumed by release automation. Phase 3. Root cause. 1. An uncontrolled controller or reconciliation workload generated excessive Kubernetes API requests during the release, and client retries amplified the load until normal deployment automation became unreliable. Why this is the exact root cause and why not others. API latency and request volume increase in direct correlation with the controller activity, and reducing that traffic restores normal deployment behavior without application changes. The shared control plane symptoms therefore point to API request saturation as the primary failure. Phase 4. Immediate fix. 1. Pause or reduce non-critical controller activity and stop aggressive retry loops that are multiplying API requests. 2. Protect critical production deployments by prioritizing necessary API operations, while control plane latency returns to normal. 3. Resume automation gradually and verify API request rate, latency, and reconciliation behavior before restoring full concurrency. Expected outcome: by doing the above steps, API pressure falls to a stable level, critical deployment automation becomes reliable again, and the cluster avoids another request surge during recovery. Phase 5. Long-term prevention. 1. Monitor Kubernetes API request volume and latency by client identity, so high-volume controllers can be identified before they affect other teams. 2. Introduce controller backoff, event-driven reconciliation, bounded concurrency, and RAID-aware retry behavior. 3. Capacity test large release scenarios to understand API request growth before production rollout. Expected outcome: by doing the above steps, deployment automation scales without allowing one controller or release burst to consume shared API capacity needed by the rest of the cluster.
Follow-up 1. Why can aggressive retries make a Kubernetes API overload worse?
Answer: a failed request already consumes control plane capacity, and immediate retries create additional requests before the underlying pressure is relieved. Multiple controllers can then synchronize around the same failure and create a positive feedback loop. Bounded concurrency, exponential backoff, and jitter help keep recovery traffic below the level that caused the overload.
Follow-up 2. How would you identify which controller is responsible for the API request surge?
Answer: I would use API audit or request metrics to attribute calls to the client identity, user agent, service account, or controller process where available. Then I would correlate that identity with controller logs and deployment activity during the same time window. The important step is to move from the API is slow to this client generated the unusual request volume.
Follow-up 3. Curveball. API request volume drops, but latency remains high, and deployments are still timing out. What would you investigate?
Answer: I would stop assuming request volume is the only problem and investigate control plane resource saturation, storage latency, admission webhook latency, API server bottlenecks, and downstream dependencies. A lower request rate does not immediately mean the control plane has recovered. I would compare current latency with resource and dependency metrics to identify what is still preventing the API from responding normally.
Pro tip for this production incident 49.
The Kubernetes API is shared infrastructure. One controller can consume enough request capacity to make every other deployment system look broken. When deployment automation starts timing out across unrelated applications, check shared API latency and request volume before debugging each application independently. API client attribution is one of the fastest ways to turn a vague control plane incident into a specific controller problem.
Production incident 50. A large dynamically generated Kubernetes release is committed to a GitOps repository. The controller begins rendering and reconciling the change, consumes excessive memory, and repeatedly crashes. Multiple teams lose automated deployment capability because the same controller serves their applications. How would you recover the delivery system without making the repository state worse?
Answer: my first priority is to stop the controller from repeatedly processing the oversized change and protect the delivery capability of unaffected applications. I would identify the repository change that triggered the memory exhaustion, isolate or revert that workload from the reconciliation path, and restore the controller before deciding how to redesign the release. I will follow a structured response plan like Phase 1. Symptoms. 1. The GitOps controller repeatedly restarts while processing a newly committed large release configuration. 2. Memory consumption rises sharply before each controller crash, while unaffected workloads remain healthy in the cluster. 3. Automated synchronization for multiple teams becomes unavailable because the same controller is responsible for their deployments. What these symptoms are telling us: the Kubernetes workloads themselves are not the primary failure. The delivery control plane is exhausting its own resources while rendering or reconciling an unusually large desired state change. Phase 2. Investigation. 1. Correlate controller memory growth and restart timestamps with a specific Git commit and application reconciliation event. 2. Measure the size and rendered object count of the affected release and identify whether generated manifests, Helm rendering, large values, or repeated templating are driving memory consumption. 3. Determine whether the controller is failing while rendering manifests, comparing desired state, or applying resources, and verify whether other applications use the same controller process. What this investigation is revealing or leading to: a generated release dramatically increases the amount of configuration the controller must render and reconcile, pushing memory usage beyond its available limit. Because the controller is shared, its crash removes automated delivery capability for otherwise healthy applications. Phase 3. Root cause. 1. A dynamically generated release created an excessive controller workload, and the GitOps architecture lacked sufficient resource isolation or guardrails to prevent one oversized reconciliation from exhausting a shared controller. Why this is the exact root cause and why not others. The controller remains stable before the large release commit and repeatedly crashes while processing that specific change. Rolling back or isolating the oversized release restores controller stability, directly linking the failure to reconciliation workload size. Phase 4. Immediate fix. 1. Pause reconciliation of the oversized release or revert the triggering repository change so the controller can start without repeatedly processing the problematic workload. 2. Restart the controller with sufficient capacity only after the large reconciliation request is isolated, and verify that unaffected applications can synchronize again. 3. Validate the corrected release in smaller units before reintroducing it into production reconciliation. Expected outcome: by doing the above steps, the shared GitOps controller becomes stable again, unaffected teams regain deployment capability, and the problematic release is isolated instead of repeatedly crashing the delivery control plane. Phase 5. Long-term prevention. 1. Establish repository and manifest size guardrails that flag unusually large or dynamically generated releases before merge. 2. Partition GitOps workloads across controller instances or projects where the platform architecture supports isolation. 3. Capacity test rendering and reconciliation of large releases and monitor controller memory, reconciliation duration, and restart frequency. Expected outcome by doing the above steps. One oversized release can no longer easily exhaust the delivery controller for unrelated applications, and large configuration changes are detected before they become a shared control plane outage.
Follow-up 1. Why does not simply increasing the GitOps controller memory limit permanently solve the problem?
Answer: increasing memory can provide temporary headroom, but it does not remove the workload growth problem or establish a safe upper bound. A larger controller can still eventually be overwhelmed by a sufficiently large or inefficient release. I would use additional capacity as part of recovery, while also reducing reconciliation complexity and establishing workload size guardrails.
Follow-up 2. How would you safely recover if the problematic Git commit is already merged and the controller crashes before it can synchronize a corrective change?
Answer: I would use a recovery path that does not depend on the failing reconciliation loop, such as reverting the triggering commit directly in the repository or temporarily excluding the affected application from reconciliation. The immediate objective is to make the controller stable enough to process normal workloads again. Once stable, I would introduce the corrected release in smaller, controlled units.
Follow-up 3. Curveball. You split the large application across multiple GitOps controllers, but one application still causes its controller to approach the memory limit during every reconciliation. What would you investigate next?
Answer: I would inspect the application's generated manifest size, templating complexity, object count, repeated values, and reconciliation frequency, rather than continuing to increase controller capacity. The application may be creating unnecessarily large desired state representations or causing expensive repeated rendering. I would reduce the configuration footprint or reconcile the workload in smaller logical units before adding more memory.
Pro tip for this production incident 50.
Your GitOps controller is part of the production delivery infrastructure. A repository change that is valid YAML can still be operationally unsafe if it creates an enormous rendering or reconciliation workload. Treat manifest size, rendered object count, reconciliation duration, and controller memory as release characteristics, not just implementation details. The best time to discover that a release can overwhelm the controller is before it reaches the production reconciliation loop.
Category 4 Summary and Key Takeaways. What we mastered in Containers and Kubernetes.
Core engineering principles proven in Category 4. 1. Artifact integrity. A successful build means nothing if the exact image digest is not preserved across registries, regions, and deployments. 2. Deployment gate awareness. Admission policies, webhooks, readiness checks, and configuration delivery are all part of the production release path. 3. Runtime placement and capacity. Scheduling, storage topology, node-wide agents, and architecture changes can alter production behavior without any application code change. 4. Control plane resilience. Registry pressure, API overload, and GitOps controller exhaustion can turn a normal release into a shared delivery outage. Mastering Kubernetes deployment mechanics means understanding not just whether a workload deploys, but why the entire delivery path behaves the way it does.
Part 1 Key Takeaways. The Delivery Engine.
Across incidents 1 to 50, we followed the complete path from source code to a running production workload. 1. Build and pipeline discipline. We learned how seemingly healthy pipelines can still produce wrong artifacts, become blocked, overloaded, or vulnerable to shared dependency failures. 2. Declarative release governance. We saw how GitOps, release branches, mutable references, and reconciliation systems determine what actually reaches production. 3. Infrastructure control. We covered destructive plans, state failures, provider and module drift, partial applies, dependency races, and infrastructure changes that cannot simply be reversed. 4. Container and Kubernetes delivery. We traced failures through image identity, registry distribution, admission, configuration, scheduling, storage, node capacity, API load, and GitOps control plane behavior. Part 1 was about mastering the delivery engine, how modern DevOps moves a change from code to production safely, deterministically, and under control.
Part 1 ends here. Part 2 moves into production reality.
In Part 1, we focused on how software gets built, declared, provisioned, packaged, and deployed. But getting a workload into production is only the beginning. In Part 2, we move into what happens when that workload interacts with real cloud infrastructure, networks, identities, secrets, databases, security controls, observability systems, cost constraints, and increasingly AI-assisted automation. This is where a successful deployment can still become a production incident, and where modern DevOps engineering is truly tested.
Part 2, the production reality, incidents 51 to 100.
In Part 2, we move beyond the delivery engine into what happens when production changes meet the real world. Category 5, Cloud, Networking, and Deployment Infrastructure Incidents, 51 to 60. Cloud infrastructure, networking, load balancing, deployment infrastructure, quotas, connectivity, and regional production failures. Category 6, DevSecOps and Software Supply Chain Incidents, 61 to 71. Vulnerabilities, dependency compromise, signing, provenance, scanners, build security, and software supply chain failures. Category 7, Secrets, Identity, and Configuration Lifecycle Incidents, 72 to 78. Identity failures, secret rotation, credential propagation, configuration boundaries, and production access problems. Category 8, Database, Feature Flags, and Progressive Delivery Incidents, 79 to 85. Schema changes, database deployment risks, feature flag failures, canary releases, and progressive rollout incidents. Category 9, Observability, Reliability, and Platform Incidents, 86 to 92. Telemetry failures, misleading health signals, platform dependencies, reliability controls, and production visibility problems. Category 10, FinOps and AI, Assisted Autonomous DevOps Incidents, 93 to 100. Cloud cost explosions, CI efficiency, AI-generated changes, autonomous automation loops, token economics, and emerging DevOps risks. Check Part 2, Incidents 51 to 100 link in the description.
The delivery engine is only half the story.
You now have the first 50 production incidents covering the full DevOps delivery lifecycle, from CI pipelines and GitOps to Terraform, containers, Kubernetes, and deployment mechanics. In Part 2, we take the next step. What happens when those changes meet the real production environment? That is where cloud failures, security incidents, identity problems, databases, observability gaps, cost explosions, and AI-assisted automation enter the picture. Check Part 2 from the link in the description and continue with incidents 51 to 100.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers. For 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.